So because I have actually gotten into this and managed to forget to record everything for an entire day, and it's only 2 days, so kind of lose half the material, actually 2/3 of the material. Okay, the first thing we're going to do is discuss radio and what exactly radio waves are, because the book kind of jumps into the electronics part of things, and I find that it's more important to actually start by understanding what radio is. Okay, so the first thing we're going to do is we are going to draw, and we're on page, well, we're really not on any page, but if you were to say in the book where we were on a page, in the PDF, we're actually on the 39th page, which says radio wave characteristics. But in order to understand what a wave is, this is where I kind of diverge from the material a little, but I think it's really fundamentally important. Okay, so we're going to draw, if everybody can see that, this X, right, or cross. All right, so we have two axes. We have the X-axis and the Y-axis. I know, you didn't think this was going to be a math class. Sorry. All right, so the first thing we're going to do after that is we're going to draw a crudely drawn circle around this axis. And we're going to start by numbering the quadrants. So a quadrant is a quarter. This is the first quadrant, second quadrant, third quadrant, fourth quadrant. And we're going to mark our 0 point. Let's say that we're sitting in a car that's going around a circular track. So this is the starting line, and this is the finish line. And this is the X-axis and the Y-axis. Okay, so we are going to go in the direction of the quadrants. So we're going to start at this point right here at the X. And we're going to go in a counterclockwise fashion. All right, somebody tell me, how many degrees are there in a circle?
360.
360. Okay, so when we get up to a quarter of the circle, we are at the 90-degree mark.
Right.
Okay, so now we're going to keep going around the circle. When we get down to here, we are at the 180-degree mark. Continue along the circle, continue driving. We're at the 270-degree mark. And finally, we get back to the finish line. Now, what do you notice about the finish line? What's it the same as?
Same as the start.
Same as the starting line, yeah. So basically, what this is saying is that this thing that we have marked as 0 degrees also has another name, which is 360 degrees. And they refer to the exact same point right there. The blue line, the blue X and the red X. Okay, so we can describe where we are on that circle a couple of different ways. If we say that the radius of the circle is 1, we are always 1 unit away from the middle of the track. We can say that we have gone, like, let's say we're up here at the black X. We can say that we have gone a certain number of degrees, angle theta, and we're still 1 unit away from the center. Does everyone agree with that?
Mm-hmm.
Okay, so let's say that we are actually at, let's say, 60 degrees. And let's say we continue around the circle and we mark this point over here. We can say we've now traveled 150 degrees around the circle. How far are we from the middle?
30 degrees.
Yeah, but we're still 1 unit away from the middle of the circle, right?
Yeah.
How about over here? If we're at 225 degrees, how far away are we from the middle of the circle?
1.
We're still 1 unit. We're just going around and around and around. Okay. So this is known as the unit circle. And this is a fundamental for understanding a lot about what we're going to talk about. And I don't think that most people who teach these classes go into this in as much detail, but I think it's really important to do. Here's why it's so important. Okay, so now let us say that we have a system by which we can say, all right, what is the farthest away from this horizontal line, what is the farthest away if we're riding around that track from the horizontal line that we will ever get if we go around the track?
Only
90
ever one
degrees.
unit.
1 unit, yeah. So we could get as high as 1 unit up from it. And if we were to measure this as the plus side, and this is the minus side, and this is plus, and this is minus, what is the lowest point that we would ever get?
0.
Well, no, we'd actually get all the way down to here. So we'd actually get down to -1. So if we were to draw if we were to look at the other axis and look at this axis, what is the furthest left or right that we will ever get?
-1 and 1.
-1 and 1, exactly. Okay, so we have the same limits on what we're doing. But it's probably clear that we're going to get to them at very different points in our travel, right? So let's say, as we travel around the circle, we start at the starting point and we travel in the counterclockwise direction. And we're going to measure how far we've gone on this graph and how far up or down we are. So we're going to mark these really important points. Well, here's our starting point, which is at 0 degrees. Our next important point is at 90 degrees. Our next important point is at 180. Our next important point is at 270. And our next important point is at 360 degrees. Because what happens, what is 360 also the same as?
0.
0, right, okay. So basically, it should be clear that this pattern, whatever the pattern is going to repeat itself because we're just going around the circle again. So if we were to look at how far up and down we are at given points, at the 0 point, we are right on the 0 line, right? Here's the 0 line. We are 0 units away from the 0 line. We're sitting on the ground. How about when we get up to 90 degrees? Are we above or below the horizontal?
Above
And how far above?
90 degrees.
Well, how many units? Remember, we're
1
talking
unit.
physical
1.
distance. Yep. So we're talking 1 unit above. Okay. How about when we get to 180?
0.
0. We're back at the ground. Okay. How about when we get to 270?
-1.
-1. How about when we get up to 360?
0.
We're back at 0. Okay. So this has a name. Does anybody recognize what this thing is called?
I think it's a
Sine
wave.
wave.
A sine wave.
That is a sine wave. And a sine wave is called so because the vertical displacement, so in other words, the y-axis position is called the sine of that angle. So if we wanted to know exactly how high above we were at any particular angle, let's say at 60 degrees, we could take sine of 60 degrees. And we know, okay, well, that's the vertical change, how far off the 0 we are. And it turns out this is roughly 0.866. We could take the sine of 0 degrees, and we would know that at this point, which is that we haven't moved at all, the sine is 0. And the sine of 90 degrees, which is up here at the top, would be 1. So that is why this is known as a sine wave. Basically, it is the unwrapping of a circle based on where we have gone, how far we've gone around the circle. So the nice thing about it is that it's repeating. So what would happen if we kept going? The picture would just repeat itself over and over and over. Okay, so now we're going to do another one. we're going to start with a blue dot right here at the 0. But now we're going to measure how far left and right we are of the center line. Okay, so when we start, how far left or right of the center line are we? How many units?
1.
We're 1. Okay, so we're starting up here. How about when we get up to 90 degrees at the top?
0.
We're at 0. Okay, so we're going to connect the dots with a little bit of a curve. Okay, how about when we get to 180, which is over here? How far left or right are we?
-1.
Well, -1, because the left side is the negative side. You probably see where this is going. When we get back up to 270, we're over here. And we get up to here, we're back up to 1. Right? This has a different name. This is a cosine wave. And it turns out that the displacement from the 0 line in the horizontal direction, which is the x-axis, is known as the cosine of the angle. And if I were to continue this in both directions, I would see that that is repeating. Now, what is something that you notice is really significant about those two graphs?
The cosine wave is just the sine wave shifted over like 90 degrees or
It's-
so.
Exactly. It's shifted over 90 degrees. So this is actually very important. This is known as a phase difference. It's the same picture, but it's moved a certain angle. It's moved a certain distance in angle, and that's known as a phase difference. So a cosine and a sine are actually just the same picture shifted by 90 degrees. So they have a phase difference of 90 degrees.
Mhm.
This is actually really important because we can also do this with it. We can actually go back and get some other information out of this. So we're going to pick an angle and we're going to say, okay, so this is our cosine. All right, so let's pick an angle of 60 degrees. Okay, so it turns out that the cosine of 60 is 1/2. And the sine of 60 is 0.866 roughly. Okay, so now if I were to draw this as an angle all by itself, up here in the right-hand corner, whoop, there's an angle, there's 60 degrees. And I can draw it like this. What does that look like, everybody? It's a special kind of triangle. It's a right triangle,
Right triangle.
right? So it's a 30, 60, 90 right triangle. This has a length of 1/2. This actually has a length of 0.866. And if you were to use the Pythagorean theorem, which says that x squared plus y squared equals z squared, you would find that the distance of the long part of that triangle is 1. So what we just did is we just established that the unit circle actually works, and that cosines and sines trigonometry are basically our way of explaining in pretty accurate terms where we are on the circle and how far away from the center of the circle we are. Okay, so now that we know what a cosine wave and a sine wave are, we can actually move on from this. And say, okay, we're going to combine this with something. So we're going to say, okay, we're going to draw our sine wave. So if I were to plot this out, this would be up to 1, down to -1. And this would be 0 degrees up to 360 degrees. That didn't come out looking very good. Okay, so now let us say we're going to combine something else here with this. We're going to combine something called frequency and period with this. So this is an audio thing. So now what I'm going to do is I'm going to clap, I'm going to snap my fingers, and I want you to tell me about how many times every second I snap my fingers. Hold on, let me turn this on. There we go. About how many times every second am I snapping my
Two.
fingers? Yeah, between 1 and 2. How about now?
3 and 4.
Yeah, I'll go with 3, because any faster than that, my hand would really start to hurt. But how about if I were to take this, my hand, and go like this? Maybe like 6 or 7. Maybe 8 if I did it really fast. Okay, so really important. The frequency is defined as the number of things that happen per second. That is a frequency. So more generally, it's number of things per unit time. So let's say I go to the zoo twice in a period of 5 years. How often do I go to the zoo? About once every what?
2.5 years.
Once every 2.5 years. Yeah. So my frequency would be, it could be described as twice every 5 years or one time every 2.5 years. It doesn't really matter. These are exactly the same, but they both basically represent a frequency, a how many somethings per unit time. So this could be, let's say, like there's something called the pitch drop experiment. If you've never seen it, it's really interesting. Basically, they filled a beaker or like a flask with pitch, and which is like tar but really thick. And to prove that it's a liquid, they then broke the little nipple at the bottom of the tube and let it drip out very slowly. Because pitch is basically a liquid, but it's almost solid. And it turns out they get 1 drop every 9 years, roughly. They get 1 drop out of the tube about every 9 years. There's actually a webcam. It's called the pitch drop experiment. It's very boring, but it's very interesting at the same time. That's a very low frequency. 1 drop every 9 years. Now,
Isn't there something about that experiment where, like, the original one they set up, no one's ever actually gotten to see it drop because
that's correct.
Weird coincidences?
That's correct. And then one time the webcam stopped working, and that's when it happened. So that's known as the pitch drop experiment. So that's a very low frequency. Now, do we have any musicians in the room by chance?
Yes.
Okay. Do you know what the frequency of an A is?
440 hertz.
It is 440 hertz. Very good. Okay. Well, it also turns out that there's a 220 and an 880, and those are your octaves from an A. Okay. So basically, if we were to then draw a wave that was a note called an A, which is 440 hertz, the reason everybody knows that too is because that's our basic tuning note. Is that if I were to draw a wave, independent of whether or not it's a clean sine wave or not, this would repeat 440 times every second. So that is the frequency of a note that we call an A. That's our basic tuning note. So now here's the next thing that we're going to do. If it's 440 times every second, there's another way to describe this. How long per wave? How long does it take for each wave to happen? Well, if it's 440 times per second, our period is actually 1 divided by the frequency. That is the definition of something called a period. So, in this case, it's 1 divided by 440 waves per second, which is, let me grab the calculator to make sure I don't get this wrong. 1. Helps to turn on numlock. 1 divided by 4. Oh, stop it. 1 divided by 440. 0.00227, then repetent. 0.00227 repetent. And everybody can see that? That is the amount of time that it takes for one wave to happen. So if we were to increase this and say that we're going to play the next octave up, it's 880 per second. It's still an A, but it's an octave up. That would have a period of 880 hertz. And then a frequency of 880 hertz, and our period would go down to 0.00113 seconds. So frequency and period inversely proportional to each other. Okay, so now we're going to add one more thing. What we're going to add is, let us say that we have a something or other that's just doing this and making that pattern. Well, now we're going to add another dimension to this. We're going to add velocity. And velocity is distance divided by time. And notice that divided by time comes back, right? So we would measure we would measure velocity in like meters per second or miles per hour, or this is my favorite one, furlong per fortnight. That's actually a velocity, a furlong per fortnight, because a fortnight is 2 weeks and a furlong, I don't remember, was it 600 feet? Anyway, it's still a measurement. It's a strange measurement, but it's a measurement of a velocity. So, and now what we have is we have this thing which is going up and down with a certain frequency. Now, let's say that we have a particle in space that is going up, and then it's going down back to zero, and going up and down and up and down and up and down, and it's not moving. What does its track look like if we were to draw this? And I can demonstrate this by holding my phone in front of the screen and just going up and down and up and down. What does the track that this makes look like?
A line.
It's a vertical line, right? Okay. So now, this has a frequency of, like, we'll call it cycles per second. In other words, how often does it make that vertical path? Well, now we can add another feature to this. We're going to say that velocity is measured in meters per second. So now we're going to take this thing that's bouncing up and down, and we're going to start it moving at a certain number of meters per second. Okay. So now we want to know, how far does this, as it's moving up and down, in the time that it takes to go up and back to zero and then down and back to zero again, one full cycle, how far did it go in that one period? Well, if we know that the period is seconds per cycle, and we also know that the distance is measured in velocity times time. So what we can do is we can now say we have this meters per second, and we can flip it. We have seconds per meter. And we can say, okay, well, we're going to do a little bit of creative mathematics and say if we have seconds per cycle, and we also have seconds per meter, we divide those, these cancel out, and we get meters per cycle. All right, well, this is really important because now we can say that if we have a certain number of meters per cycle, we can say that in the time in the time that it took, whatever time that was, to make one cycle, this thing has moved X number of meters. And this is actually given the Greek letter lambda, and it's known as a wavelength because we made one full wave. So this is a physical distance, which is going to be really, really important during this class. And what we have is that V is equal to frequency times lambda, where V is the velocity of the thing that's moving in space, F is its frequency, and lambda is its wavelength. All right, any questions with that so far? Speak up if you have any. Now's a good time, because remember, you're probably not the only one who's wondering. If not, we're just going to move on. Okay, so if V is equal to F lambda, and let's say that we have a 440 hertz letter, 440 hertz note that's called an A. And we know that this is traveling through air because it's a sound wave. And we're going to say that this has a velocity of about 330 meters per second. Right? That's about the sound. That's about the sound of sound waves, or sorry, about the speed of sound waves through air at sea level. Something close to that. So we're going to say that we have about 330 meters per second, and we're going to use this as our frequency, 440 hertz, and this is our velocity. And so what we can do is we can rearrange our formula and say lambda is equal to V divided by F is equal to 330 meters per second divided by 440 hertz. And a hertz is a cycle per sec. This is in the way. Sorry, I'm going to have to move that. Let's redraw that. 330 meters per second divided by 440 cycles per second. This per seconds cancels out, and we get a distance of 0.75 meters. So a note of an A being played by a musical instrument traveling through the air at sea level will carve out, if you were to map it, a distance of 0.75 meters. That is how physically long it will be. Okay, for those of you who play musical instruments, why is this kind of thing important? And I can answer it, but I know I've played instruments, so I know the answer to this. But for those of you who play instruments, why is that important?
I don't play much, but my guess is it has to do with acoustics, so you get all the best sounds.
Yeah, that's part of it. What makes a sound. If you play a guitar, or if you play a trombone, or
The width of the string?
actually the length and the tension of the strings, and how about if you play an instrument that's a woodwind or something, or a brass instrument?
Are you looking for resonance?
Yes. So the length of the thing that is making that wave has to be right. What happens if you have tuned your instrument and normally you were looking for this length wave and it's actually this long? What will happen in there? The wave that's allowed to exist will actually be this long. And what do you notice about it when you tune your instrument with an orchestra?
Doesn't sound great.
Doesn't sound great. In other words, your instrument, you've done a bad job tuning, and because your column of air that you're using in your instrument is too long, your wavelength is too long, so your frequency is too low, so you will be flat. For those of you who play music, if you tune your instrument so that the resonant column is too short, you will find that it goes like this, and it's supposed to be right here, and you will be sharp. You will be at too high a frequency. This is actually really important because this actually works into radio as well. How in the world can this possibly work into radio? Okay. All right, what is this thing called again, everyone?
Sine wave.
That's a sine wave, okay? And what is this length called? Well, in time, it's a period. And in distance, what is that Greek letter lambda called? Really important.
Wavelength.
Wavelength, okay. So lambda is our wavelength, and that's usually measured in meters. What relates our frequency and our wavelength and our period, frequency, and by the way, the units of frequency is something called a hertz. We're going to cover that all the time in this class. Time is measured in seconds, and lambda is measured in meters. We're now going to introduce something that is not a sound wave. We're going to introduce something called an electromagnetic wave. All right, it's a different kind of wave. A sound wave, what did they say about sound in space? If you're in space and something cuts your arm off and you scream, what'll happen? Nobody will hear you. Nobody will hear, other than the fact that you'll be in a lot of pain, right? But nobody will hear you because sound waves need a medium to travel through. They're a pressure wave. Now, an electromagnetic wave is a very special kind of wave. It travels in 3 dimensions. And, okay, everybody, if you can hold up your right hand, can't be your left hand, has to be your right hand. Okay, everyone stick up your thumb. And now stick out your index finger and stick out your middle finger so that all of them are perpendicular and right angles to each other. All right, so we have 3 different things happening. The first part of an electromagnetic wave is the electric part. The second part is the magnetic part. And the third one is the direction of movement. These are always perpendicular to each other and defined by what's known as the right-hand rule. So if your electric field is your thumb, your magnetic field direction is your index finger, the direction of movement of the wave is the middle finger. So if I were to hold this up and say this is my electric field, this is my magnetic field, these basically go in shapes like sine waves, like that. The magnetic field, we're going to make red. This would go up at the same time and cross here. What's really important is that my direction of flow, which is called the S vector, is in that direction. And if we were to reverse the direction of the magnetic field, the direction of flow of the energy would be the other way. So basically this means that the wave itself, the S vector, is traveling toward the right of our screen, and the electric and magnetic fields that are drawn, they're in the pattern of sine waves. They are at right angles to each other as it travels through space. What's important about electromagnetic waves is that they do not require any medium to travel. If anyone's ever heard of something called the Ethernet, the reason we have this thing called the Ethernet is because it was once assumed that, much like sound, electromagnetic waves had to have something to travel through, right? Because who ever heard of a wave traveling through nothing? So they created this thing. The scientists basically hypothesized this thing called the ether, which was this invisible thing, invisible stuff that we all live in, but that also exists in a vacuum that allows electromagnetic waves to travel. Well, as it turns out, electromagnetic waves don't require anything called ether. So it turns out the ether doesn't exist. But that's the reason we have something called the Ethernet. The electromagnetic waves travel through the ether. Okay, so as we now have this thing called an electromagnetic wave, every electromagnetic wave has an amplitude. And in fact, the electrical and magnetic portions of the wave are actually very closely related to each other. If it does happen to encounter a different material to flow through, for instance, glass or water, then the magnitude of the electrical and magnetic portions don't necessarily follow the same ratio anymore. They actually change. Traveling through space, they are very, very closely related to each other. As soon as you introduce another material, you actually can do weird things like change the amplitude, or you can actually slow the wave down, believe it or not. Its velocity actually changes. So we discuss an electromagnetic wave as having a speed in free space. So it has a velocity in this thing called free space. Free space means that there's nothing like a phone to travel through, or a piece of ceramic, or my hand, or this coffee cup, which I'm going to take a sip from. Free space is basically nothingness. And the speed of an electromagnetic wave through nothingness, essentially a vacuum, is roughly 2.998 times 10 to the 8th meters per second. Or roughly 3 times 10 to the 8th meters per second. Anyone have any idea what that speed is commonly known as?
Speed of light.
Speed of light. This has a name that we give it called c, which is the speed of light. And if we were to write this out, it would be about 300 million meters per second, which is pretty darn fast. It's basically here to the moon and back in about 3 seconds, or here to the sun in 8 minutes. And that is the speed limit that we have yet to find any way for anything to exceed. It's the reason why there's something called relativity, special relativity. Because nothing can travel faster than the speed of light as presently defined by physics. Well, since we are dealing with practical things here, what we're going to be doing is assuming that the speed of light is our speed limit. And what I want to also bring up is the fact that we now have this thing called the speed of light. There's a really important word in there. What is the important word? The important word is light. Okay. Light is an electromagnetic wave. Okay. It's electromagnetic energy traveling as an electromagnetic wave through space. Well, okay. So what is light? Basically, this is a thing called a photon with a certain amount of energy. And as it oscillates up and down and travels through space, it does this. And it makes a pattern, which means that light has a frequency. And it also has a wavelength as it travels through space. Now, it turns out that light has a very, very high frequency. And what we consider red has a wavelength of about 616 nanometers, which is 0.000000660 meters. That is about the wavelength of red light, right? Really, really small. Green light has a wavelength of about 500 nanometers, or 0.0000500 meters. Blue light, even smaller. It's about 420 nanometers. 0.000000420 meters. Okay, well, the only thing that's different about these is the energy of the photon that makes that particular thing happen. It turns out that the wavelength and the frequency is proportional to the energy of the photon. It turns out it's actually proportional to, I believe, the square of the photon, the square of the energy. Maybe it's even higher order. Anyway, what ends up happening here is that it becomes clear, well, if it's all just numbers and you have different photons that have different energies making different wavelengths, can you not have a photon that has like a lot lower energy and has a wavelength of 1 meter?
Should be.
Should be. Can you have a photon that has much higher energy and has a wavelength of 1 nanometer? Sure. If you can put enough energy into it, sure. So, what is the difference between a photon that has a wavelength of 1 meter and a photon that has a wavelength of 1 nanometer and all the different colors of light that we have? The only thing that's different is the amount of energy in it and the wavelength of the wave that it makes. That's the only thing that's different. So now, if we were to draw this, we would see that starting at really long wavelengths and going to 0 wavelength, which would be an infinite amount of energy, we would have all these lines of demarcation, and we would have a red for red color, and there'd be a yellow line, and there'd be a green line, and there'd be a blue line. And then there's purple, which I can't draw with this thing. But what are these colors that we have right here? What do we call these?
Visible light.
That's a visible light. Okay. But what's beyond that? What's over there?
Infrared. And
Actually,
radio.
it's the other way. This is ultraviolet.
Oh, I didn't see the direction.
And how about going to the left?
IR.
That's infrared. Yeah. Okay. How about beyond ultraviolet?
X-rays.
We have X-rays, and we have gamma, and we have cosmic rays, and gamma rays, and things like that that are higher and higher and higher energy. Okay, but how about to the left? This is actually lower energy, and these are higher energy.
Microwaves.
Yep, we have microwaves, and we have these things called microwaves. And how about if we go even further?
Radio waves.
And actually, at the very end, where infrared stops, all of this is called radio. That's it. That's where radio waves fall on the spectrum. So why is it that we can't see? Why do we call red red? Why do we call the color red red?
It's arbitrary, but
Yeah,
it's the
somebody
way-
somebody saw a color and said, that's red. And it just so happens that people's eyes are set, are basically wired so that they pick up this thing called red, and we call it red. So why is yellow yellow? For the same reason, right? And green is green, and purple is purple. But how come we can't see infrared? We can certainly feel it. We feel it as heat. Why can't we see it? Certain animals can see infrared.
We
I
don't
think it's
have
My
something
understanding-
about
Right. Our eyes have not evolved to be able to see infrared. And how come we can't see ultraviolet like some birds and the bees can? Because
Same reason.
right, there was no reason for us to be able to see it. We get a sunburn from it, but there's no reason for us to see it. But how do we pick up, for instance, how do we see infrared? Can we actually view infrared? And the answer is yes. Anyone ever seen something called this? Which is a FLIR camera.
for sure.
It's called a forward-looking infrared camera. And what it does is it does false coloring based on sensors that pick up different wavelengths of infrared. We use this for lots of things. We use this for lasers, infrared lasers. We use this for infrared distance detection with sensors that are not sensors that aren't visible to the naked eye. Notice we use heat detection because things that are warm generate infrared, so you can actually do thermal imaging. The same with ultraviolet. We can do ultraviolet. So what we end up having to do is we have to build sensors that pick up these different wavelengths and convert them into colors that we can understand. So can we do the same thing with radio waves?
Presumably, it's all electromagnetic radiation.
That's right. It's all the same. So if we have, let's say, from frequency of 0 to frequency of, let's say, 300 million hertz. We'll get into this too. This is also known as 300 megahertz. And we'll say that 0 is actually way down there, but we'll say this is 30 hertz. What we're going to do is we're going to mark off decades, which are units of 10, and this becomes 300 hertz. This is 3,000 hertz. This is, this has another also name of 3 kilohertz. This is 30 kilohertz. And then 300 kilohertz. And then 3 megahertz. And then 30 megahertz. And these are actually supposed to be drawn about the same width, so I didn't do quite a great job on it. But these actually have names. This area right here, this is known as HF. This is known as VHF, and this up here is known as UHF, and that goes up to 3,000 megahertz. So these are actually different parts of the spectrum. Normally we think of a spectrum as colors, but these are basically all just different colors of light that allow us to hear and see different frequencies. And we have a special device that allows us to do this. And it looks like this. And what is this thing called, everybody?
Transceiver.
That is a radio. It is a radio receiver. And what it does is it basically gives us visibility or audibility of things that we can't see because they're different colors of light. So really what we're talking about when we're learning about radio is we're learning about how we are able to transmit and receive and put information on different colors of light, which are known as radio waves. So much, much longer wavelengths. But essentially, it's really the same. This is the same basic technology that somebody would use, for instance, to to use let's say a fiber optic cable. Let me unshare that. There we go. So if you were to, let's say, have a cable that went like this, and we're going to give it a width that looked like that, and you were able to put a wave of red light into it, it would bounce around inside the cable, and what goes in bounces around, and what's going to come out the other side? You have light going in, you have light going out. That is a fiber optic cable. And it is very similar to what we're talking about. I mean, basically you have a frequency and a wavelength, and this would be, for instance, red light. You bounce it into the fiber optic cable and it hits the walls, and you have red light that comes out. So if you put information, if you modulated that signal with information, you basically did something to the signal and put information on that signal, you would get info out. That is how we are talking today. That is how we are holding this class. You know, these long haul fiber optic cables that run at really high data rates that allow us to do things like this class. It's really all the same thing. All right. I'm going to stop the share. Okay. Is everybody ready for a 5-minute break?
Yes.
Okay. Good. We'll be back in 5 minutes. And while we wait for that 5 minutes to come up, if there's anyone who has any questions, it's a good time to ask.
Well, I have questions not directly about the materials covered so far, but
Okay.
I've been shopping around for equipment,
Uh-huh.
and I noticed you pointed to the IC 7300.
Yep.
Which looks like a great unit.
I have one.
Do you? Do you like it?
I love it. And I'll tell you what, I've had my license for 38 years, and it's the first radio I've had that I can honestly say there is not something else that I would rather have.
Really? Okay. I'm kind of hanging out for a 7100 because it covers the 2 meter and 7 centimeter.
Yeah, but I'll tell you what. Depending on what you do, here's what you'll get to really like. Let me hold on a second. 14020. Okay. I mean, I also have a 7100. I should point out. I have both of them. So
Yeah,
what
you
I'm
get the 7100 now.
Yeah, I know. Well, I mean, they still make it. They're just hard to get.
Yeah.
So here we go. I would like to point out this picture. Can you see that picture on the screen?
Yeah.
Are you familiar with this? What this is called?
Is that a waterfall?
That's a waterfall display. So it's a frequency versus time display. And this happens to be a web SDR that's based in the Netherlands. So what we're looking at right now is a Fourier transform of the entire HF spectrum at one time. This is
That's
from
pretty cool.
0 to 30 megahertz, all at once.
Wow.
Yeah. And now what we can do with this is let's go down to 7020 and zoom in. And we're
And
going
that's
to look
relative to your antenna, right?
well, this is actually in Europe.
Okay, but if you had this display locally, it would be relative. So this is relative to the antenna. This is what the antenna can see, not necessarily what's there.
Right. This is what the antenna in the Netherlands is seeing.
Right, yeah.
And here's what it sounds like. What's cool about a software-defined radio is not only does it do a Fourier transform, but it can also do the decode.
Right.
So, for instance, it's lower sideband.
No, I'm not hearing anything.
Oh, I didn't share the sound. Hold on. I have to share audio. There we go. There we go. All right, so we're listening to, you're actually able to see the spectrum. Listen to the decode of it. This is all digital. And down here, another digital mode. This is called PSK.
Right.
There's another. So anyway, this is basically a visual representation of the spectrum that we were just talking about in a very specific viewpoint. You know, we could see, if you think of these as colors, on the left end would be red and on the right end would be blue because the frequency goes from low to high. We're basically using a viewer that allows us to visualize spectrum that we can't see, you know, with the naked eye.
The 7300 has that, right?
The 7300, and this is one of the reasons why I have a 7300, is because that's the waterfall display on a 7300, which is just, you know, I mean, it first came out 5 or 6 years ago already. So if you want to think of it, it's already old technology, but this is the first radio I've had in 38 years that I can honestly say there's not, you know, and it was only $1,000. I mean, that sounds like a lot, only $1,000, but the technology that's contained in a transportable box that's only like 9 by 9 by 3 inches, that's actually usable.
That's wild.
Is quite insane.
Is it 13.8 volts?
Yeah, it's 12 volts. So you just need a power supply, but essentially I have yet to find something that I can't do with it.
Now it's about, I guess it takes about like 21 or 22 amps. So do you need like a double breaker to power your power supply so it'll carry that?
No, if you
No.
we're going to get into power soon too. P equals I times
Everybody loves
E.
a straight man, right?
Yeah, P equals I times E. So 12 volts at 20 amps is only 240 watts. So
Right. Oh yeah, because it's 12 volts. at
because
20
12
amps,
volts. Okay, so now the next thing I want to share is, if I can find it, that's not it. I think I opened it. Oh, there we go. Okay. Everybody's back, I hope.
Yep.
And so what I want to share is this. Has everybody, I think I included this in all your packets. Does everyone recognize this? Do you have it memorized? Hey, got it
Yeah, oh, yeah,
memorized?
totally.
Okay.
Totally.
So notice this is just in the United States, the radio spectrum. What all those different frequencies are used for, starting at very low frequencies. So if you were to think of this, let me zoom out if I can. Zoom. fit width. There we go. Okay. These are actually, as they are shown left to right, the left to right sections, what's at the right end of one row is actually at the left end of the following row. So you'll see that 300 kilohertz is right here. 300 kilohertz also shows up at the left end of the following row. So really all of these are lined up end to end to end to end to end to end. Well, now you will also notice that this one goes from 3 to 30 kilohertz. The next one down goes from 300 to 3 megahertz, which is 3,000 kilohertz. The next one goes from 3 megahertz to 30 megahertz, and so on and so forth. So this is actually really important because the way that the spectrum is drawn, each successive band is 10 times bigger than the previous one above it. And this can actually be shown down here. Notice this says the radio spectrum. And in fact, look at that. Ultraviolet, X-rays, gamma rays, visible light. And here's the radio spectrum. This is what is shown in the sheets above. And right here, where this says 10 kilohertz, 100 kilohertz, 1 megahertz, and so on and so forth. Well, as it turns out, we start at 3 kilohertz and we go to 300 gigahertz, which giga is billion, and they're shown in factors of 10. So this, the first grouping is 3 to 30, 30 to 300, 300 to 3,000, because as it turns out, given the speed of light, that translates to, for instance, 1,000 meters, 100 meters, 10 meters, etc., which we're about to get to. But you can see that this spectrum is used by a lot of different things. And all of these wavelengths, all these frequencies behave completely differently from all the other ones. So notice this whole big area of broadcasting, 535 to 1605 kilohertz. In actuality, though, that's about 1 megahertz wide. If viewed down on this bottom one, 1 megahertz wide takes up 1/10 of the space between 64 and 65 gigahertz. No, 1 megahertz takes up 1,000th the space between these two, between 64 and 65. So that's one thing that's very important to note, is that this is not to scale. The things that are shown on the higher end are spread out a lot, kind of like a map that's really, really skewed. But no, you're not going to have to memorize all of this. It's important to know that it exists. Now, one thing that is important, not to memorize, but certain things you're going to need to memorize as you go, let me share that, is the part of the spectrum that is of interest to us as amateur radio operators. We have access to, notice that we have wavelengths and frequencies. Every wavelength relates to a particular frequency. All of these bands are actually shown on this big old chart. If you were to look at that color where it says amateur, right up here, let's see, amateur. Where's amateur? Amateur, right there, in this teal color. And you were to seek out all of the sections that are in teal, for instance, this one right here that says amateur, and oh, there's another one, amateur, and let's see, here's another one, and there's another one, and here's a few more. Notice when you're looking at these charts, they don't take up a lot of room, do they? But as far as we're concerned, that's our playground. That's where we get to play. That's where we get to experiment. And because all those frequencies are so very different from each other, for instance, we look at 160 meters. In physical terms, how big is 160 meters, everybody? How many feet long?
About 400 odd feet.
About 500 feet. So bigger than a football field. All right, how about 20 meters?
60 feet.
About 65 feet. All right. How about 6 meters?
Around 20.
About 20 feet. How about 23 centimeters? It's about this big. And we have bands that go up into the millimeters as well. Well, these are all amateur bands, which means these are all for experimentation of different kinds. Because the size of an antenna that generates, that is used to operate on a certain frequency is proportional, just like a musical instrument, to the wavelength of the signal that you're making. Lower frequencies, longer wavelengths take much bigger antennas than higher frequencies and shorter wavelengths to make. That has other implications as well. Now, the other thing is that certain wavelengths, as they travel through space, behave completely differently. Some of them get absorbed by the ionosphere, which we're going to get to. Some of them pass through the ionosphere. Some of them get reflected or refracted by the ionosphere. These are all very, very different. Some of them get used for, if something goes through the ionosphere really well, that would be good for interstellar communications, communicating with the satellite, communicating with something heading for the moon, for instance. You wouldn't want the signal that you're putting out to be absorbed by the atmosphere if you're trying to talk to something heading for the moon. Similarly, if you're trying to talk to somebody using a reflected signal that's supposed to bounce off the atmosphere to the other side of the world, you wouldn't want something that's going to get absorbed, and you wouldn't want something that's going to just shoot on through. So different frequencies are used for different things. Similarly, different antennas are basically impossible to make. For instance, if I wanted something called I'm going to draw an antenna here. I'm going to draw an antenna that has something called gain, which is something we're going to get to. Gain is basically the ability of something to concentrate a signal in one direction. I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, a 10-element Yagi, which has a driven element right here, and this has a forward gain of, let's say, 25 dB. We're going to get to decibels shortly. So it has a forward gain of 25 dB. So if I run 10 watts of power into this, effectively coming out of the front of it, I'm going to end up with something on the order of, let's see, 10 times 1,000, about 3,500 watts. Effective power. So that is why it's important to be able to do this, to understand this and take a class, because if you were to do that and point that directly at somebody, you could conceivably cause them considerable amounts of harm. So we are allowed to do this. We are allowed to do that. It is important for us to know that using a certain amount of power, you can really hurt somebody. That's really the fundamental reason why you take a class and take an exam, is the fact that you don't hurt anyone. To understand enough to make sure that we don't hurt anybody, including ourselves. So, but now let's take a look at this. Let's say that the frequency that we're operating on is, let's say, on the 33 centimeter band. All right, that's a full wavelength, and this antenna right here is about a half wavelength long, which means that it's about 16 centimeters long. 16 centimeters is roughly 5 inches. Okay, well, it seems to me that this whole antenna would be about, let's see, quarter wave, 1, 2, 3, 4, 5, 6, 7, 8, 9. This whole antenna would be about 27 inches long. Wow, that's a pretty easy to make antenna, isn't it? You could certainly do that. All right, now let us say that we wanted that same amount of oomph, right, in the forward direction, and we were operating on the 160 meter band. Half wavelength, this antenna element would be roughly 250 feet long, just for that one element. And 9 quarter waves, and this antenna would be about 1,200 feet long. Anybody see a problem with that?
Yeah, big problem.
I mean, You might be able to build it maybe somewhere, but it's not very practical, and it's certainly not self-supporting. So, there are a lot of practical reasons why it's important to understand what is possible. That's, to understand what, why a certain band cannot be used for certain things. Okay, so now that we've covered radio waves and we understand what sine waves are and stuff like that, what we're going to do really quick is we're going to talk a little bit about math, a little more math. And okay, so it's important to understand these things called prefixes. And the reason we have prefixes and scientific notation is because, let's say that I have a wavelength of 300 meters. Okay? Well, a wavelength of 300 meters is great. By the formula V equals F lambda, we're actually going to take this and replace it with the letter c, which is the speed of light. And we know that that is 300 million meters per second is equal to F times 300 meters. And we keep our units, meters per second. And we know our frequency is 1,000,000 hertz. Okay, this has a name. Well, this is actually equal to 10 times 10 times 10 times 10 times 10 times 10. There are 6 of them by scientific notation that is known as 10 to the 6th power, because it's 10 times itself 6 times. This can also be replaced by a big letter M for the prefix, which is mega. So we could then take this million and say that this is just 1 megahertz. Right? So we have this big letter M replacing all those zeros. Now we can also go the other way. We can have a value of, for instance, a capacitor, which is 0.000001 farads. Okay, well, when I go to buy a capacitor, I don't want it to say 0.000001. Right? That's a lot of zeros to maintain. Nobody wants to see that. Right? You probably forget a zero, then it's wrong. And so this is actually 1/10 times 1/10 6 times. So it's 1/10 to the 6th power, which by convention is 10 to the minus 6. And this value, which is also 0.000001, this has a special prefix that goes with it, which is micro. So I could replace this with 1 microfarad. So when I go to buy that capacitor, it'll say 1 microfarad. And this is where prefixes become very useful, because they basically allow us to eliminate a lot of zeros that don't really have any information for us. So if I have a capacitor that's 0.000033 farads, that would be, I move 1, 2, 3, 4, 5, 6 places, 3.3 is left over, and I move 10 to the minus 6th, that would be micro, 3.3 microfarads. Very important to be able to move numbers around, to eliminate and add zeros if necessary. Okay, this also can show up in other places. So let's say that I have something called gain. Okay, gain is the improvement of a signal compared to another place. The opposite of gain is called loss. Now, what we find is that, okay, we have a gain of, let's say, 2 times. That's no big deal. We can deal with that, right? Let's say we have a loss of 50%. Well, that's not such a big deal. But let's say that we are transmitting a signal from point A to point B. And this signal goes up through a piece of cable, through an antenna on this end. What is in between those two places, everyone? What do we have?
There's at least air.
There's
assuming
air.
we're on Earth.
Yep, there's air. What else is there?
Is that the ether zone?
That is the ether. Yeah. This could be a vacuum. It could be filled with air. It could be filled with nothing. It could be filled with airplanes. What else? It could be filled with birds. It could be filled with water vapor. If we're going and bouncing stuff off the sky, if we draw the atmosphere, this could be the ionosphere. In which case, some of our signal goes up through the ionosphere, and some of it bounces back down. But let's say that the amount that bounces back down, by the time we get to where we want to go, is if we had an original value of 1 watt. On the other end, we have 0.00000000001 watt of energy. And I hate to say it, everybody, but this is the kind of number that we deal with all the time. So in other words, if we put out 1 watt, we get about 1/1000th of it on the other end, depending on the path that we're following. Because the beam spreads out, a lot of it doesn't make it there. You know, the stuff that comes out to here ends up going someplace where the other person's not. So we can say that in between point A and point B, how much of our power didn't go where we wanted it to? If we started with 1 watt and we ended up with 0.00000000001 watt on the other end, where did the other 0.99999999999 watts go?
Into
Right around.
space.
Everywhere else, right? Well, okay. But notice this number is not 0, is it? It's not quite 0. It's almost 0, but it's not quite 0. So the way that we talk about this is that we can do this and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a value of 1 left over. We moved over 10 to the 12. We move over 12 spaces, 10 to the minus 12. This value has a prefix called pico. So we have 1 picowatt of energy that made it to the other end. So it's important to note what your prefixes are. We have our kilo, which is 1,000, our mega, which is 1,000,000, and then we have our giga, which is 1,000,000,000. Notice we also have lots of zeros here, right? So this is 10 to the 9th power, 10 to the 6th power, 10 to the 3rd power. And then getting smaller, we have milli, little m, 0.001, micro, 0.000001, nano, 0.0000001, and so on, pico. Each of these adds or takes away 3 more zeros to the mess. Okay, so we can use those values, but now let us say, here's the next thing. We're going to say that coming through this system right here on the other end, we are actually able to have an amplifier up here which has 1,000 times amplification on any signal that is that big or larger. Well, so by the time we get here, now, after we've amplified it by 1,000, we have gotten rid of 3 zeros, 0.000000001 watt. Well, now we can say this is 10 to the minus 9th watts, or 1 nanowatt. Okay, well, These are still hard numbers to talk about, right? There's still a lot of zeros in here. So what we are going to do now is we are going to add something to this. We are going to take a look at the number 10. The number 10 is really important because it allows us to count zeros. Now, the next question I'm going to ask is, everybody, what's 10 times 10? Just shout it out.
100.
100. Okay, another way to write this is 10 to the second power. What is 10 times 10 again?
100.
100. Okay. Oops. Why does it do that? Must have fat fingers. Jeez, look at that mess. Okay, what is 100 times 100?
10,000.
10,000. Okay, how many zeros are there in 10,000?
4.
There's 4. Okay, so I can write that as 10 to the 4th. So if we have the same base and we multiply 10 to the second times 10 to the second, clearly what happens is that the base stays the same and the exponents add. This also works negative. 10 to the minus 2 times 10 to the minus 2 is 10 to the minus 4th. And we can show that this is true by saying 1 over 100 times 1 over 100 is equal to 1 divided by 10,000. And we could count all the zeros and find that it's actually true. It does work. Okay, so what happened in the late 1800s, early 1900s, there was somebody named Alexander Graham Bell who decided that it was difficult to carry all of those zeros, and he said, I'm going to make a better way. So what I'm going to do is say 10 to the third. Let's say that's 1,000 times. And I'm going to say that I want to know just what value 10 is raised to get that. Well, in this case, it's a value of 3. And I'm going to call that unit the bell. So if I start at a value of 1 and I go up to 1,000, this is a ratio of 1,000. So this actually has another name. Going from there to there is called a logarithm. It's kind of the opposite of an exponent. It's a logarithm base 10. So let's say that I start at 1,000 watt, or I start at 1,000 watts and I start at 1 watt and I end at 1,000 watts. I have an increase of 1,000 times. That is my ratio. If I take my log base 10 of that value, that's the log base 10 of 1,000 is equal to 3. Which basically means I have had to raise 10 to the third power to get 1,000. Well, it turns out this is a really convenient way of doing things, because if I do, let's say 1,000, as we just showed, times 1,000, what's 1,000 times 1,000? It's 1,000,000. Well, if I have this as 3 bells, and this is 3 bells, these just add, and that becomes 6 bells. Because I'm just adding the exponents on that base of 10. Well, that's actually really convenient, because this says, okay, well, if I have a signal that starts here, and I have a value of 1, and I run it through this amplifier, which is 1,000 times, I end up with, this is actually really important. What's 10 to the 0 power, everyone?
1.
That's 1. Okay. So this starts at 0 bells. Because 10 had to be raised to the 0 power to get 1. At this point, I have 1,000 times. Well, that's now 3 bells. And I'm going to multiply it by another amplifier that has 1,000 times gain. Now I have 1,000,000. And this is 6 bells. So what I can do is basically every time I do a multiplication, I do an addition in bells. But it turned out that the bell was actually not the best unit of all to use because, then you ended up with something like 3.92 bells. So it was decided that they would create a new term, which most people here have probably heard of, which is called a decibel, which is a 1/10 of a bell. So a decibel is basically whatever the bell is times 10. So if I have, let's say, a starting point of 1 and I go up to 1,000, well, I still do my log base 10, which basically says to what power do I have to raise 10 to get what's in there. But now I multiply it by 10. And this is the definition of a decibel. So 10 times log base 10 of 1,000, which means I have to raise 10 to some power to get 1,000. Well, that's 3. It's just simply 30 decibels. And that is how power levels and gain and loss are measured. Everything is decibels. So what we've now done is we've now covered frequency, wavelength, and time, and distance, and gain and loss. And these are the language that we are going to be talking. So we now have the whole vocabulary that we need to discuss pretty much everything radio. This is all the terminology that we're going to need, essentially. All right, any questions? Now's a really good time. If you have any questions at all about that.
So are decibels just used for power? Because I used to hear decibels used for sound ratings. So
They
how
are.
do they?
They're used for, basically a decibel is merely a representation of a ratio in other terms that have real, numbers that we can comprehend and deal with. So in sound, there's basically something that's your baseline. It's let's say that a certain amount of sound pressure, sound energy is, quote, inaudible. That would be your reference point. That's your starting point. So everything beyond that is how loud is it compared to that? We do measurements with we do measurements with voltage as well. And it turns out that in voltage it's actually 20 times, not 10 times. But we're not going to get into that in this class. For power, it's a factor of 10. It's 10 log base 10. Yeah. I thought I heard somebody else. Maybe not. All right, other questions? Nothing? Okay, last call. Okay, so now that we have essentially the language that we need to describe all this stuff, what we're going to do is we're going to start figuring out how to make those frequencies and wavelengths and signals that we need. Essentially, the next part of the class is looking at the components that you need to generate frequencies, to generate waves, to figure out what to do with electrical signals. So now, what we're going to go into is, starting on page you know what? Let's start at the very beginning. Electrical principles. We're on page 7 of the PDF. And for anyone who's curious, it looks like this. All right. So we're looking at basic circuits now. Because a circuit is a combination of electrical devices that we're now going to use to handle electrical signals, which we've just discussed. Okay. And we're going to share this. And what I'm going to do is recreate that basic circuit. So we have this thing called a battery. And we have a thing called a resistor. And we have wire connecting them all. Okay. So now, again,
Hi.
yeah, go ahead.
Yeah. So I'm a paper person, so I have it printed out, and there are no page numbers on the printed version.
Okay.
So it was very helpful to have you show what it looks like, so that I can follow along. But when you said earlier, page 39, it was like,
yeah.
I can't find that. So
We'll get back to it.
okay, just a heads up so that when you do refer to the document, a little more guidance, like showing what
like
it
showing
looks
the
like
page.
would be helpful.
Okay, perfect.
Thank you.
Okay, so now what we're going to do, now that we've discussed, you know, what waves are and what we're actually going to talk about electricity. All right, so everybody can see this basic circuit that I've drawn, right?
Yep.
Okay, all right, here we go. We have three different things. We have E, which is voltage. This is measured in volts, named after Alessandro Volta. We have I, which is current, which is from impulse, and the unit is the ampere, named after ampere. And we have R, which is the resistance, and that's measured in ohms, named after Georg Simon Ohm. These were all 19th century mathematicians, scientists, what you'd call today electrical engineers and physicists, who came up with the basic rules and characterized the basic rules of electricity. Okay, so, well, they figured out that a galvanic cell generates a voltage because of an electrochemical reaction inside the cell. Essentially, two different metals will have different electronegativities, and you'll be able to generate a voltage. This is measured by the letter E for voltage. It's also known as electromotive force. Right? Essentially, this is the force. This is the push behind this thing called an electron. An electron, if we get down, all the way down to it, I'm going to draw a very basic representation of an atom. So here's the nucleus of the atom. This has protons and neutrons in it, and zipping around the nucleus of the atom are these things called electrons. And they operate in different shells, they have different spins and different energies, but essentially an electron is just a negatively charged particle. If we think of it as just a negatively charged, very small particle, that's enough for the think of this class. So what this ends up doing is that you have different metals inside this battery that we have on the left. It generates an electrical potential. Also can put there potential. So potential, electromotive force, or voltage. And that is the ability to shove electrons out of its terminal and back into the other side. All right, so from there, we have this thing called current. And current is the flow of electrons. Okay, now what I'm going to do is I'm going to ask everybody an important question here. What is the charge on an electron? I even drew it. Positive or negative?
Negative.
Okay, which terminal should electrons flow out of a battery from?
The positive
Negative.
side.
No, they shouldn't. Think about it. An electron is negative. So which side should they come out of? They should come out of the negative side because they're a negatively charged thing. Okay. And in fact, they do because electrons are negatively charged. Well, but let's say that you're a scientist in the 1850s and you just know that you have a battery that you hook up to something, and well, this thing called a resistor, which basically resists the flow of electrons, but you don't know what electrons are at this time. You just know that they're this tiny little thing that exists inside a battery, and it seems that if you have enough of them flowing out through a piece of wire, you actually have a proportional flow of this energy out of a battery, and it heats up this resistor, and then it seems to flow back around this thing called a circuit. And you don't know, because it's the 1850s, if they're positive or negative, because the electron hasn't been discovered yet. Well, okay, so you create a convention by which you say, okay, well, we have this positive side and this negative side, and we're going to say that the current, which is the letter I, flows out of the positive side of the battery. But you don't know that there's this thing called an electron yet. Well, it turns out that they got it wrong. And by Jove, all the way through engineering school, all the way through your entire existence in the world, as far as you are concerned, current flows out of the positive side, because they got it wrong 175 years ago and they never bothered to fix it. So, even though we know that current flows with electrons, because by definition, current is the flow of electrons. That is what current is. We are going to forget that we ever heard that, and for the sake of all of the classes that you ever take, current flows out of the positive and into the negative. And for the sake of argument, we are going to say that the negative side we're usually going to tie to 0 volts, so that we always have a positive voltage coming out on the positive side, and our negative is 0 volts. So, apologies from all the 1800 scientists who got it wrong. They were basing it on what they knew at the time. Okay, so now we're going to take a battery which has a voltage of 10 volts, and we are going to take a resistor, and we're going to take this to be 10 ohms. We're going to learn Ohm's law right now. E equals I times R. This can actually be drawn as a triangle, like this, or as a circle. I like the circle myself. Either way you do it, depending on the book that you read, you'll get something like that. Okay, the way that this works is that if you have 2 of those values and 1 unknown value, you will take the unknown value. Let's say, in this case, I don't know my current, which is true. I will basically take this and I'll black that out. And I'll erase that. I'm left with I, which is what I didn't know, is equal to E. There's already a division sign there, divided by R. Okay? So it's 10 volts divided by 10 ohms. 1 volt per ohm is known as an amp, and that is 1 amp. So I have calculated my current. I is equal to 1 ampere. And there you go. The first application of Ohm's law today. I could also use this by saying, okay, well, here we're going to draw another circuit like this. Here's my battery. This is 100 volts. And I get a magical current of 10 amps coming out of it because I measured it. So what is my resistance? Well, this is my E, this is my I, and this is my R. E, I, R. I draw my circle. I don't know my resistance. I'm left with R is equal to E divided by I, which is equal to 100 divided by 10 is equal to 10 ohms. So my unknown resistance must be 10 ohms. Basic application of Ohm's law. Okay, now Ohm's law goes a little bit further than that too. There is another thing that we can do with Ohm's law, which is kind of the second half of it. P is equal to I times E. And we could draw it the same way. P is equal to I times E. And it turns out that if we have a resistor, for instance, and a battery, and we have 100 volts right here. And we have a 10 ohm resistor. We can calculate our current. So we have the first part, E is equal to I times R, and P equals I times E. So we have our E and we have our R. We don't have our I. So the first part of it, we would take this and we would say I is equal to E divided by R is equal to 100 divided by 10 is equal to 10 amps. Okay, well, now that we have that, we know that we have 10 amps flowing through here. We also have 10 amps coming out of the battery, obviously, because we don't have current, we don't have electrons that are just flying into space off the wire. At least we're going to assume that we don't. So what we then have is, okay, what is our power? That is the letter P. That's power. That's measured in watts. The big letter W, named after James Watt, who was, I believe, a Scottish scientist. And so what we're going to do then is say, okay, we don't know our P. We have I times E. So P is equal to I times E is equal to 10 amps times 100 volts is equal to 1,000 watts, which we can also rewrite as 1 kilowatt. So that is the power that is generated by the battery and also the power that is dissipated by the resistor. This also brings up a very interesting point, which is really important for us to remember. This is, we haven't found any place where this does not apply. Energy can neither be what? Anyone know this one?
Created or destroyed.
It can only do what?
Move from areas of high energy to low energy.
Well, yeah, it can just change form, right? Energy can just change form. So in this case, what is where is the energy coming from? It's coming from a battery. So how was it stored there? It was stored in chemical form. What happens in the resistor? If we put 1,000 watts of power, because it turns out that power is energy per unit time. If time doesn't change, if the energy that we put in has to come out somewhere and we put 1,000 watts in, what has to come out?
The same amount.
The same amount. And what is the form?
Electrical energy.
No?
It'd be heat because the resistor's going to get hot.
Yep.
Oh, you're talking about the resistor. Yes, sorry.
Yep. And that's going to come out as heat. Now, what would happen if we heated this resistor up and it turned out that it started to glow red? It didn't catch fire, but it started to glow red.
You've overloaded the circuit.
Yep, unless it was designed to do that. Can you guys think of a circuit that would be designed to glow red?
Something that
LED.
needs to alert you.
How about a toaster? Right? If you look inside the toaster, you'll find that the heating element is glowing red. So not only is it heating up and emitting heat, it's actually emitting light. Right? So some of the energy is actually coming out as visible light. And if something, let's say, there are lots of other forms of energy as well. It can come out as flames. I've done that before. It can come out as sound. You hear noise coming out of something. That's another form of power, of energy. But basically, energy and power, they have to go somewhere. That's actually another fundamental part of the stuff that we teach. So let's say we have a power calculation where we have, let's say 100-watt transmitter. All right. And we come up here, and here's our antenna, and we put a watt meter right here. And that watt meter measured 50 watts of power going out to the antenna into the world. But we had 100 watts going in. What happened to the other 50 watts?
It was
Heated up our
dissipated
feed line.
somewhere along the line.
Yeah, it had to go somewhere. So where did it go?
Heated up the feed line.
Yep. So basically all this cable that we used to connect them, this was getting warm and radiating energy. Had to be coming out somewhere. And the amount of the energy coming out, the amount of power coming out of that had to be what?
50 watts.
50 watts. Yep. So it's not an overly complicated thing, but it is important to see that if we're looking at a closed system like that, and there's no power going in to the system as a whole, and there's no power going out of the system as a whole, and it has to be balanced on the inside. So that power, the extra power, comes out as heat. Has to come out somewhere. Okay, so what we're going to do now is we're going to start on that same page, and we're just going to start asking some questions and going through the question pool. Now, one thing I should note about the question pool is that the technician license question pool, now we're actually going to start talking about that a little, is I believe 435 questions. So your exam that you're going to take is 35 questions, which means that you have 435 questions in and you have 35 questions out. So these questions are all broken up into section 1.0, 1.1, etc., 4.0, 4.1, 4.9, etc., all the way up to like 9.0, 9.1, 9.2, 0.0, and so forth. They're all broken up into different groups, and inside each group there's a certain number of questions. There's a rule that says that every exam of 35 questions has to have, let's say, 2 questions out of this group, and 1 question out of this group, and 1 question out of this group. So even though the exam pool is 435 total questions, your exam will only ever give you a certain number of questions out of each area. So if there's an area that you say, you know, I really don't know the math all that well, I don't feel comfortable with it, you're not going to get an exam that's 60% math. So don't worry about that. You know, you'll have, the goal is to make sure that you basically have some knowledge in every area rather than like really strong knowledge in one particular area. So don't worry about that. It won't happen. Okay, so now we're going to start looking at the actual questions a little bit. Okay, so I'm going to share my screen here. Okay, here we go. Voltage is the force that causes electrons to flow. The electrical term for the force that causes electrons to flow is voltage. This is known as electromotive force and electric potential, the ability to shove electrons into something. The name for the flow of electrons in a circuit is current. Electrical current is measured in amperes, named after ampere, right? French term. Okay. Well, we haven't gotten to alternating current yet. So now we're going to start talking. Notice that has a sine wave pattern, right?
Mhm.
Okay. So we're going to measure. Here's alternating current. And this goes plus and that goes minus. Okay. So if we were to draw this, if we were to draw the flow of electrons in a circuit coming out of alternating current circuit, we would find that when it's plus, the plus and minus look like that.
Mhm.
When it's minus, we would find that the plus and minus look like this. So the alternating current is actually generated by an alternating voltage source. So what that means is, For half of the time, the current flows that way, and the other half of the time, the current flows that way. So it goes back and forth and back and forth. And what is this thing again? That's a sine wave. That means that every time it makes a 0 point, the current completely stops. Isn't that crazy? Essentially, you've got current that goes one way and the other, and in between switching directions, the current completely stops moving as it switches back and forth. It also means that if E is equal to I times R, and the resistance never changes, that the current and the voltage are proportional. So at which point, if I were to draw these points of interest and label them 1, 2, 3, 4, and 5, at which point in that pattern would you say that we're going to have the peak current in the direction of the black arrow? When are we going to have peak current in the direction of the black arrow?
2.
At number 2. When are we going to have peak current in the direction of the red arrow? At number 4. That's right. So, and in between, we're going to have differing levels of current flow. And what do we know about power? P is equal to E times I. Well, if they're proportional, and actually we can redraw P equals I times R as E is equal to, sorry, I did that wrong. We can draw I is equal to E divided by R. We can actually substitute this letter I in over here, and then we end up with this formula. P is equal to E times E divided by R, which is E squared divided by R. So when that's true, when we get up to these peak points, we're actually having a lot more voltage. And it turns out that it doesn't matter if it's positive or negative, because if this is negative, you square it, the minus sign goes away. So you have peak power and another peak down here. And right here, at these 3 points, you have 0. Huh. Well, that seems kind of weird, doesn't it? How do you measure that? Well, the way that we do this is we have something called an RMS voltage, which is also known as root mean square. And for those of you who are curious, because the power is proportional to the square of the voltage, what we do is we take the power curve, which looks like this, and we add all those up, and we divide it by one complete period. And then we average it out. And then we say, what equivalent voltage, DC voltage, would have been necessary to make that same amount of power? And that is known as the RMS voltage. So when we actually look at our wall voltage, so what we're going to do is we're going to share this again. Notice this alternating current waveform. This is a picture of the voltage that comes out of our wall. It's a sine wave. One cycle is 1/60th of a second. We have 60 cycles per second. That's why we call it our 60 hertz power. But here's the tricky thing. We actually call this 120 volts AC. Well, this is actually RMS. It's root mean square. So it goes through 0, and it looks like this. And here's one full cycle, and it has 0 crossings at the beginning and the end, and it has a peak up here and a negative peak down here. But again, RMS is the equivalent DC voltage. That would make just as much power. So as it turns out, in order to account for all that time that we're doing a really bad job of making power, which is this time down here because our voltage is low, we actually have to go and exceed that power, exceed that voltage to make more power so that it averages out over time. And as it turns out, if you were to go and measure using your using a voltmeter, an RMS reading voltmeter, you would get 120 volts AC RMS. That's what your meter would say. However, if you were to put this, if you were to measure this using something called an oscilloscope, which measures voltage versus time, what you would find is that you do not have 120 volts. Anybody know what you actually get?
$110 maybe?
170 and negative 170.
Hmm.
And it's actually the square root of 2 times the RMS voltage. So you get plus and minus 170 volts, which actually is really important because let's say that you have a circuit and you decide you're getting some noise somewhere and you want to put a filter capacitor on there, which is another thing we're going to get to very shortly. And so here's your plus and here's your minus, and this is your black wire and this is your white wire. So this is also known as your line, and this is your neutral, and you say, oh, I need to filter out some of my noise. And this capacitor is rated 150 volts. What will happen to the capacitor?
Pop.
Poof, you'll have a poof, right? Because as it turns out, this filter capacitor, actually, even if this was rated, let's say 300 volts, the biggest differential that you'll see, actually, let's go 150. It should be 150. The biggest differential you'll see is actually 170. So that peak will be enough to make the capacitor go poof because it's not rated for as much voltage as you'll see. Okay, so now we've covered RMS a little bit. Okay. Which of the following describes alternating current? It alternates between positive and negative directions. The number of times per second that AC current makes a complete cycle is known as its frequency. And everyone, the unit of frequency is?
Hertz.
The hertz. Okay, excellent. Okay, electrical resistance is measured in ohms. Electrical resistance is the ability of something to resist the flow of current, which is electrons. The nice thing about a resistor is that a plain old resistor does not care whether the direction of current changes or not. It doesn't care about the frequency. It doesn't care if it's direct current, which means it's always going in one direction. Makes absolutely no difference.
Yeah.
Yep. Someone said something. Oh, it could have just been ambient noise. Okay. Why are metals generally good conductors of electricity? Well, if you think about what a wire looks like, what is a wire exactly? A wire is, even if it's really, really thin, a wire is an atom and 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 an atom. And normally, these have electrons zipping around, and occasionally what will happen is they're moving due to thermal energy, and they just happen to typically stick around where they are, you know, where their home is. However, if you have an electron that pushes into a piece of wire, that will occasionally get into this area, which might make another electron push out of the first atom, and then that moves another one and another one and another one along. And what you basically get is kind of like a train where you move an electron in and you get an electron out. It's not quite as simple as that, but that's probably the easiest way to think of it. So if I move 10 electrons in, how many electrons will I get out the other side?
Whatever you put in.
That's right. If I move 1.1 1.6 times 10 to the 19th electrons in every second, how many electrons will I get out? 1.6 times 10 to the 19th electrons every second. Well, this number is actually really important. This is a coulomb. And a coulomb per second is known as 1 amp. Electrons are really, 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 really small. It takes a lot of electrons to make 1 amp. Really, really small. But fortunately, atoms are also really, really small. And there are a lot of atoms in a piece of wire. And a power supply can actually move a lot of electrons in a hurry. Okay. So, good conductors of electricity. Can anyone name some?
Glass.
Oh, no. Good conductor. A conductor allows electrons to move easily.
Metals.
Okay, good. How about salt water?
Hmm.
Very good. How about fresh water?
No.
Not so good. How about all the stuff that's inside of us?
Yes.
Yes.
Very much so.
We're very salty. As it turns out, that is one of the reasons why, for instance, if you touch your finger on a battery or something, you typically won't get a bad shock. However, if you had an electrode that's stuck in on this finger and an electron that's stuck in on the other finger, it could actually do some serious damage because it got through your skin. Your skin is a really good resistor. Your insides are not very good at being resistors at all because of all the salt. Okay, how about aluminum? Good resistor, a good conductor or bad conductor?
Excellent conductor.
Excellent conductor, but it's also very difficult to use as a conductor. Now, we make a lot of antennas out of aluminum because it's lightweight and very strong. But as it turns out, aluminum also has a really nasty habit of oxidizing very quickly. And the problem with that is, of course, that aluminum oxide is a very bad conductor. So what happens is we get a surface of the aluminum which doesn't conduct electricity very well, which is fine if you have two wires that are then tied together and they're kept away from the air. Let's say you take two pieces of aluminum and screw them together, and then you mix, and then you dip them in grease to keep the air away. That's an excellent conduction. That's an excellent point. Well, unfortunately, what happened was at the beginning of the 1970s, it was decided that aluminum, because it was easy to work with and really cheap, was going to be used for house wiring. Anyone ever experience aluminum house wiring?
Yeah.
Yeah.
I have.
Yeah, the danger with
Not
that, of
very
course.
good.
Well, it can be, but it has to be treated properly. You have to make airtight connections, because what ends up happening is the aluminum will oxidize, and then you get a connection which is aluminum oxide to aluminum oxide, and you end up with a high resistance contact, and you're carrying a lot of current. And what's that formula again? Ohm's law? P equals I times E, and E equals I times R. So P is equal to V squared divided by R. And what happens if you have a 120 volts and you have a resistance of, something? What happens is you generate a lot of P. And what does P come out as? It generates heat. And if you have that heat in a very small space in your attic, what does it do?
Catches fire.
It burns your house down. That's right. So that happened in the early 1970s. A lot of houses built with aluminum wiring, because they didn't know at that time how to properly treat the wires, ended up burning the houses down. So copper wire is better, but a lot more expensive for that reason. So aluminum wire can be used, but it has to be treated properly. Okay. Let's see. Good insulator. An insulator is a material that doesn't have a lot of electrons that can be moved along from atom to atom. So let's hear some good electrical insulators.
Glass is one of them.
Glass is great.
Rubber.
Rubber.
Plastics,
Rubber, plastic, other ones.
air.
Dry wood. Dry wood is good. Air, but okay. Another interesting story. Air. So somebody I know recently went to an island off the coast of New Zealand and put up an antenna, and every time he transmitted, it seemed with about 500 watts into his antenna, the ropes that were holding the antenna up burned up. Normally, this would never be a problem. However, it was about 45 degrees and there was a lot of sea spray. What does sea spray have in it?
Salt.
Salt. So basically, he ended up with salt-coated ropes. And what happened to his ropes when they saw high voltage?
They burn up.
They burned up. They became conductive and carried current and got hot and burned up. So ropes are usually very, very good, very good resistors, very, very good, very high, high insulation resistance, but not when they get soaked with, salt water. Okay, Ohm's law, E equals I times R. We can flip this around using the triangle. All right, so we can do some very basic calculations, which I think we just did. We can do some more if you guys want. All right, series and parallel. Okay, we're going to do series and parallel. Okay, so if you, let's say, like I'm actually watching a show called White Lotus right now. It's coming out as a series, which means that, let's say that this is me, I'm an electron, and I'm traveling along the wire. I encounter this resistance, and then I encounter this resistance. They are in series format. I have to go through one before I go through the other. I can't watch them out of order. I can't watch the shows out of order. Similarly, if I'm an electron that's moving on this circuit, I have to pass through one before I pass through the other. This is known as a series connection. If I were to draw this a different way, here's my battery. I get to a certain point, and I have a choice when I get to this point. I can go down one path, or I can go down another path, and these two lines are parallel to each other. So I actually have a connection. This is known as a parallel connection. So what is important to note about these is, let's say that I am a voltage. I have an equivalent voltage here, and I have an R1 and an R2, and an R1 and an R2. Okay, if I am the electron, if I'm sitting on the electron and I'm part of the current that's flowing through a series circuit, I have to expend some of my energy, because this is a resistance going through here, and I have to expend some of my energy getting through the second one before getting back home. Now, what if I am instead on the second circuit and I get here? Well, I'm going to have a choice. Which way am I going to go? Well, which way does water flow if it has two different options?
Path
Path
of least
of least
resistance.
Path of least resistance. Okay. So if I'm an electron, I am going to take the path of least resistance. So what will happen is that my current is going to split into I1 and I2. And they are going to be of different amplitudes, different magnitudes, based on the values of the resistors that they encounter. So if I were to measure a voltage from this point to this point, both of those resistors would see the exact same voltage, but the currents flowing would be proportional to the resistors they encounter. If I am in the other circuit, what happens is that because the current has to go through both resistances, what happens is that my voltage that I lose going through the first one and the voltage that I lose going through the second one, they have to add up to the voltage that I started with, and the voltage drop, as it's called, is proportional to the resistors that they have to pass through. So what this means is let us go and take a look at this in practical terms. So let us say that this is my home, and each of those resistances is a light bulb. So I have a circuit where I have this, and I have a light bulb, and I have a light bulb, and I have a light bulb, like this. Okay, this is a series or parallel circuit, everybody?
Series.
That's a series circuit. What happens in this case if I decide I'm going to do this and add another light bulb? The same current flows through everything, but now my voltage is split even further, right? I had R1, R2, and R3, and now I've added R4. So if power is I times E, and the current is the same, and the current is exactly the same, what is going to happen to my E that is experienced by every one of those light bulbs? It's going to get smaller. Well, as it gets smaller, what happens to my power?
It drops.
It drops. So what happens to the intensity of my lights?
They drop too.
Yeah, my lights get dimmer. Well, who wants that? So that's not how we wire houses. That's also the classic Christmas tree light conundrum, where if all your lights are in series and you have one light blow out, what is the resistance of a blown out light bulb?
Essentially infinite.
It's infinity resistance. Well, if E equals I times R, and you don't have infinite voltage available, and you have I times infinity, well, then your I is 0, which means you have no current flowing and you have no power at all, and all your lights go out. So if you lose one Christmas tree light, all the lights go out. So this is not how we wire our houses. What we do with our houses is we do this. Here's a light bulb, and here's another light bulb, and here's another light bulb. And does any light bulb care what the other light bulbs are doing?
Don't think so.
No, they don't, because if you have the same E available for all of them, and you have R1 and R2 and R3, and you make this one go away, the only thing that matters is that the wire that is connecting everything together is big enough to deliver the current to all of the devices. And if it's not big enough, then you'll start a fire. Which is where we now bring in another interesting thing. Okay, so let's draw this. All right, and let's say that as designed, this device, this is a 4 amp light bulb, this is a 4 amp light bulb, and this is a 4 amp light bulb. Right? So when they are at full brightness, each of them is using 4 amps of current. How much current is being passed through this wire?
Of amps.
That would be 4 amps, right? Because 4 amps is going this way. So going here, there'd be 8 amps going into here, and there's 4 amps going here. So there's 12 amps going into here, because the currents going into and out of a single point have to be equal to 0. They have to sum up to 0. So if you have 4 going this way and 4 going this way, you have to have 8 going in. If you have 8 going out and 4 going out, then you have to have 12 going in, which means that this circuit is providing 12 amps. Okay, so now let us say that you have built this circuit so that this wire is good for 12 amps. It has a diameter that is suitable for carrying 12 amps of current. And then somebody decides, well, you know what, let's add another light bulb over here at 4 amps. How much current is now going in if this is using 4 amps? You now have 16. So this power supply is now 16 amps, but nobody bothered to change that wire. And how many amps did we decide that wire was capable of handling? 12 amps. So what happens to the wire?
Burns up.
Because P is equal to I times E. That same thing again. E equals I times R. I work in this, I work in industry. I build machinery for a living. I do all the electrical stuff. And 90% of the problems that I encounter are direct applications of Ohm's law. No matter how technologically complex a system is, 90% of the problems you encounter are Ohm's law. Goes back to the basics. Somebody forgot to check something. Somebody didn't do the calculation. So you don't want, obviously, something to catch fire. So there's a couple of things you can do. You can take this wire and beef it up. Or you can say, we need to protect ourselves against people doing stupid things. So we're going to add this thing called a fuse. What a fuse is a device that is designed to be a sacrificial element in a circuit. In case somebody decides they're going to draw, or because there's a failure, let's say that there was a problem in this light bulb and it developed a short. A short is 0 ohms. A 0 ohm circuit, how much current would that draw by Ohm's law?
All of it.
All of it. That would be infinity current. Well, if that happens, then this wire, if nothing blows, this wire is going to be forced to maybe handle, to deliver 50 amps, 100 amps, which will make the wire catch fire. So what you do is install a fuse, which is designed, if the current exceeds, let's say 12 amps, to blow. Essentially, it has a very carefully calibrated piece of wire inside where if too much current flows, it gets hot. And when it gets hot, it melts. And when it melts, it becomes an open circuit. So that's known as a fuse. Okay, so we have series and parallel circuits. There's a series circuit again. Here's a parallel circuit. In a series circuit, the current passes through both devices in series. In a parallel circuit, the current gets to decide which way it's going to go. Okay, DC power. What is the unit of power, everybody?
Watts.
The watt. Okay, very good. Now, for those of you who have been on a bicycle, for instance, and you're climbing a hill, what do you have to generate in order to climb a hill?
Speed, I imagine.
How do you generate speed? How do you generate, because you're climbing a hill, you're
Resistance.
increasing your potential energy. What do you have to generate? You have to generate power.
Mechanical engine. Yeah.
Mechanical energy. Okay. What is the unit of mechanical energy per unit time that you have to generate called?
Watt.
It's called watts. Okay. And where does that power come from to generate that energy?
Ultimately from the sun via the food you eat and
That's
via your
right.
muscles.
That's right. So basically you can go back to saying it's chemical energy that's stored in your body, which you then burn up. And where did that energy come from? It came from the food that you ate, which is then grown from, it's either animals or plants. And if they were animals, then the animals ate the plants, which absorbed energy from the sun. So basically, watts are watts. Power is power. Energy is energy. It just changes form. So electrical energy and chemical energy and mechanical energy are all really just the same thing. They're just different forms of storage. Okay. Yeah.
I've got a question.
Yeah.
So this is probably, I can't find the time element. You said its power is something over time,
Yep.
energy over time.
Yep.
But I don't see time in volts or amps.
Nope.
Am I missing something?
Nope. A watt. Okay. And 1 watt is a joule per second.
It's also a volt amp. Is
Yes.
that
Yes. It's
Okay.
also 1 volt amp.
okay? So which
which is
does the-
actually
does
a
volt have time or amp have time?
amperes, because an ampere is a coulomb per second.
Okay. That's where I was missing it.
Yeah,
Okay.
and a coulomb is a unit of charge,
Okay. Yep.
which is roughly 1.6 times 10 to the 19th electrons.
Okay. So why do we measure things in kilowatt hours? Why do we
Well-
add another time? And that's not power.
No, that's actually energy, because a kilowatt hour, because we use so much energy,
Uh-huh.
that seems to make it make sense.
Okay.
So, for instance, 1 kilowatt hour is equal to 1 kilowatt times 1 hour. So
Okay.
that's 1,000 watts times a period of 1 hour.
Okay.
We could also do 1 watt second,
Yeah.
which is a much smaller thing.
Okay. Thank you.
Okay.
I now see the time element in there.
Excellent. Okay.
So is it fair to say then that a watt is instantaneous measure
Yes.
of the consumption of energy?
Yes, a watt is a joule per second, and a joule is a unit of energy. So, for instance, if you talk about kilojoules, that's 1,000 joules. If you talk about a calorie, everyone's eating calories, right? Food calories, what is it? 4.18 kilojoules per kilocalorie, I think. So there's a translation between calories and joules. And in fact, if you go to Europe, your food is not measured in calories, it's measured in joules of energy. Because they use the metric system, and we kind of don't. So okay, and now we have current and power, and we've done math for electronics and conversion of units. Notice we have our giga, mega, and so we're on the let's see, which page is this? We are on the 18th page of the PDF file. Math for electronics and conversion of units. So here's our giga and mega and kilo and milli, micro, nano, and pico, with all those extra zeros and the exponents and powers. And there are lots of examples on converting things, so let's just pick one for the heck of it. 500 milliwatts, and we want it to be converted to watts. So we will start with, it works both directions, 500 milliwatts. We know that a milli is 0.001. That is the definition of the term milli. So this is 500 times 0.001 watts equals 0.5 watts, or half a watt. We can do another one. 3,000 milliamperes. Milliamperes. And we can say, okay, milli, 0.001. 3,000 times 0.001 is equal to 3 amperes. So that's just another way of representing it. We can also go the other way. Let's say we have 22 amps and we want it in milliamps. So we can always multiply by 1, right? Everyone agrees we can always multiply something by 1, right? We're always allowed to do that. So I'm going to choose to multiply this by 1,000 and by 0.001. Because this times this, that's 1. I'm allowed to do that. So our goal is milliamperes. Well, that's milliamperes. So I can replace this part of it with the letter M, and I get 22,000 milliamperes. And I think that's one place where people sometimes get confused. The fact that if you want to convert something into something else, you can always multiply something by 1. If I have 16, let's say 16 volts, and I want to represent it for some weird reason in microvolts, well, I can always take 16 times 1,000,000 and 0.00001 like that. Well, that times that is 1. So I haven't done anything illegal. And I want it in microvolts. Well, that's my micro portion right there. So that's 16 microvolts. So there's my conversion. Can always do that. So long as I'm multiplying by 1, I can do anything I want. Okay. So there's conversion of really small things. There's picofarads, microfarads. And it's basically just multiplying by 1 and then figuring out which thing you want to keep. All right, decibels. So we're covering decibels. So we talked about what decibels are. So now we're going to just circle back to it and say one more time that a decibel is 10. This is the formula, 10 times the log base 10 of P2 over P1, where this is your starting point and this is your ending point. So it's basically looking at a ratio of two things and finding a convenient way to explain how much bigger something is than something else using exponents. So 10 to the something power. So if I went and said, okay, my ratio is 10 to 1, I can write this out and say 10 log base 10 of 10 over 1, which is 10 log base 10 of 10. So to what power 10 to the what is 10? Everybody? 10 to the what is 10?
1.
1.
That's 1. So that becomes 1 is equal to 10 times 1 is 10. So what I have is that a change by a factor of 10 is 10 dB. And if I were to take this and instead make this that my starting point was 10 and my ending point was 1, then I would basically have 1/10 here. And by convention, 10 to the what power is 1/10, not 1 anymore. That's minus 1. So now, instead of 10, I get negative 10. So this would be known as a loss. So a loss of 10 times is negative 10 decibels. A gain of 10 times would be positive 10 decibels. So let's say that I have a system by which I have, let's say 1 watt, and I put it through a 10 times multiplier, and then I have a something or other which is a magic box which attenuates the signal and leaves me with 1/10 of the signal. Just empirically speaking, how much am I going to have coming out if I start with 1 and multiply by 10 and divide by 10?
1.
You're going to have 1. Okay, but let's look at it in decibels terms. So let's start with this as, we'll call it 0 dB. That's our reference point. If I go up by a factor of 10, 10 times is 10 dB. All right, so we now have plus 10 dB. Well, a loss, 1/10, is negative 10 dB. And what do those add up to? Plus 10 and minus 10.
0.
0, which is exactly where we started. And guess what? We are really exactly where we started. But now let's just take this and make this a little more complicated. And we're going to add, instead of those, we're going to add something that is, let's say, an amplifier, which is 92 dB, and a loss of cable, which is 11 dB. We start at 0 dB and we end at 0 dB. Okay, so we have 0 plus 92 minus 11. And we don't have 1 anymore. We have something different. Okay, if we have 0 plus 92 minus 11, what do we end up with?
81.
We end up with plus 81 dB without carrying all those zeros. And herein lies the power. We could double check it, using exponents and lots of zeros, but we don't have to. And what's cool about this is that we now have something that we can use as a tool. And let's say, let me pull up an antenna. We're going to pull up a 13B2 antenna. Okay, here we go. Here's a 13B2 antenna. All right, this is a well-known antenna, and notice it has it has a lot of elements along a single boom, as it's called. And we're going to try to open up the website for. Oh shoot! Come on, really? Okay, 13 dB description. Yeah. Okay. Let me look up 13B2. Here we go, 13B2. And notice how this is, if we look up the product manual. Can everybody see that?
Yep.
Okay, so what do we have here? Frequency, number of elements. What is this right here? Forward gain. Everyone see that? It's measured in dBd. That is a ratio of how much better than a dipole, which is a basic antenna, this antenna works in the forward direction. That's measured in decibels. Does it matter how much power is going into it so long as it's not so much power that you damage the antenna?
No, it doesn't.
No, it's a ratio, exactly. Front to back ratio. This is a ratio of how much power comes out the front versus how much goes out the back. Does it matter how much power goes in so long as you don't damage the antenna? It doesn't, because it's just a ratio. Every antenna, every piece of cable, everything that you see will be measured in decibels. Notice the side lobe attenuation. E plane, that's the electrical plane, measured in attenuation in decibels. In other words, how much power comes off the sides of the antenna versus what goes out the front. You're going to have at least 60 dB less, which is 1,000,000 times less energy at minimum. It could be even less.
Is it safe to say that the width of your transmitted beam is related to the gain? The higher the gain, the narrower the beam?
It is very true to say that. And the reason that we do that is actually, well, now that you bring that up, so we're going to draw an antenna that has a forward beam that looks like that, and an antenna that has a forward path that looks like that. So the way that we do this is we measure the peak right here. And let's say this is 20 dB. And let's say on this one, it is 32 dB. So what we do is we will actually have these concentric circles that look like this, and another one that looks like this. And we reduce these. We have additional circles that are.
Hey, Scott.
Yes.
I think you might still be zoomed in. I'm not seeing the whole picture.
No. Well, I didn't make it all the way to the end. I did that on purpose.
Oh, okay.
So let's say you have additional circles that look like this. So right here, let's say this is the 17 decibel point. So basically, at this point right here, how many decibels lower is your signal than the peak?
3.
3 dB. This is actually a magic number. 3 is a magic number, right? This actually defines right here. Okay, so if if we look at the math, we find that 3 decibels is equal to roughly 2 times. And minus 3 dB is roughly equal to 1/2 times. So if 3 decibels translates to half the amount of power, it turns out that this magic point, these are known as the half power points. We use these throughout engineering to define what our beam width looks like, what a filter looks like, things like that. These are known as half power points, and there's 2 of them. There's one on the top and one on the bottom. Now, if I were to do the same thing here, and the peak is 32, my next curve would be at 29. Well, it turns out that, okay, maybe the peaks are here and here. Well, intersect the lines. So what do I find? That my beam width for this antenna is this big, and my beam width for this antenna is only that big. So a higher gain antenna with a narrower pattern is going to have a narrower beam width, because you're taking your energy and you're shooting more of it forward. In other words, what you're doing is you're borrowing the energy that would have been going in all these other directions, and instead you're managing to throw it in the forward direction. Does that make sense?
Yeah, so there's nothing for free. You can't have a high gain you can't have a high gain antenna that's omnidirectional.
Mm-mm. Nope. You can't make power out of nothing. I wish you could, but you can't. So now what we're also going to do is show things that have loss. Coaxial cable loss calculator. Okay. Oh, that's not what I wanted to see. Darn it, I picked the wrong thing. Wouldn't you know I picked the wrong thing? Would you know I picked the wrong thing again? Come on. Sorry, this is embarrassing. Okay, there we go. Okay, so if you use a piece of cable at a given frequency, at a given length, notice what the losses are measured in, everybody. There it is. So, yep. So for instance, if you are using RG58, which was another thing we're going to cover, on the 2 meter band, 2 meter band is 144 to 148, and you have 100 feet of it, you're going to lose 11 dB. That's actually an enormous amount of power, because what is 10 dB we just determined?
Order of magnitude.
Yeah, well, here we go. There's really only 2 numbers you need to know. There's only 2 numbers that I know offhand, even, with the lifetime spent doing this. 10 times is 10 dB, and 2 times is 3 dB. Those are really the only 2 things you need to know. And you need to know that gain is positive and loss is negative. So what this means is, let's say that somebody quotes a gain of 22 decibels. Okay, how can I break that up into 10s and 3s using addition? Well, there's 10, and I could do another 10.
Plus 1 times 2.
But that leaves a 2. All right, I don't have a 2, but I have a 3. Well, and a 3, and a 3, and a 3. And guess what? That's exactly 22. Okay, so now 10 dB is how many times?
10.
10 times. 3 dB is
2.
2 times. 3 dB is, okay, and 3 dB is 2 times, and 3 dB is 2 times. And what's 10 times 2 times 2 times 2 times 2? 2 times 2 times 2 times 2, that's 16 times 10 is 160. So, in practical terms,
you got one too many 2s there. 2, 4, 6, 8.
2, no, because they're multiplying, they're not adding.
2 times 2 is 4 times 2. Oh, right. They're
Okay.
multiplying each time. That's
Yep.
right.
So I get 160 times. So if I put in 1 watt of power, what will my effective power in that forward direction be?
160.
160 watts. If I put in 100 watts, how much power will I get in the forward direction? 16,000 watts. If I put in 1,000 watts, how much power will I get in the forward direction? The equivalent of 160,000 watts. So why is this important? Let us say that I were to manage to build, which I can, a dish antenna, or I just found a surplus one, which had a forward gain of 33 dB. It's a fairly big dish, but I'm using it at a high frequency, right? So my gain is actually pretty darn good. So here's my forward gain of 33 decibels. And I take 1 watt going into it. Well, how do I break up 33 decibels? 33 equals 10 plus 10 plus 10 plus 3. Okay? And what's the first 10? How many times? 10 times. And the next one?
10 times.
And the next one?
10 times.
And the 3 is how many times?
2.
2 times. Okay, 10 times 10 times 10 times 2. It's 2,000 times. Okay? So, if I transmit at a power of 1 watt, what is it? How much forward energy am I putting out?
2,000 watts.
2,000 watts equivalent. What if that is pointed right at somebody?
Oh, you don't want to do that.
You don't want to do that. That's right. What if, okay, now, how much power are we as amateur radio operators legally allowed to run on most bands?
200. Oh, 1,500 is the
1,500 watts. So let's say I managed to acquire somehow, and I have components that are able to handle 1,000 watts of forward energy, right? 1,000 watts of power. What is my effective power in that forward direction? If I have a 2,000 times gain.
2 megawatts.
Yeah, I have 2 megawatts in the forward direction. If there is somebody there or a bird that flies through the beam, what is going to happen?
They might get hurt.
They might get seriously hurt. Now, when would I actually want to do something like this? There are applications for this. People do it. And I will show you a picture of what it looks like.
A microwave oven.
Yeah, it's a microwave oven, but an even better one.
Is that a space telescope?
Earth, moon, earth.
Somewhat like it. Yeah, what was that?
Earth, moon, earth.
That is called EME. EME is called Earth, Moon, Earth, where we take signals, often at like 1,296 megahertz. We put them through a very high gain antenna at very high power, and we bounce the signals off of the biggest reflector in the sky, which is the moon, and we have people on the other end try to catch them and send signals back out to us and make contacts using the moon as a reflector. That is known as EME. People do that. We are allowed to do that. Sometimes you will have people that are running full 1,500 watts with 35 dB of gain. That is why, even though you say, well, you know, why do I need to get a driver's license? You know, why do I have to be tested for all of this? Well, because you could go out and you could buy a Ferrari, right? There is no saying. I have never, for instance, wanted to run a 1.5 kilowatts with a 35 dB gain antenna to bounce signals off the moon. But my license says I can't. So basically, that's why we need to, if the license says you can, we need to be tested to make sure that we don't hurt anybody, including ourselves. Okay, everybody ready for another 5-minute break?
Yes.
Everybody having fun?
Yep. This
Yes,
is
are
good.
we having fun yet?
Good. I'm having fun.
Yeah, very nicely done so far. I really like it. Thank you.
Rigmaster. Rigmaster antenna. Rigmaster portable antennas for ham radios. Gigaparts.
Okay. Anyone with any questions?
I have one. It may not quite related to radios, but what we were talking about in the last few moments. There are science kits I think I've seen where you can transmit energy from one part of the room, send the energy through space, light a light bulb on the other side.
Yep.
You don't want to be standing between the light bulb and the source, do you? I mean,
it won't go through you very well.
Yeah.
Depends on the frequency. Now, one thing that was kind of a cool thing to do is to do something like this, where you have a laser, which is a red laser, a visible red laser, and you have inside the laser a battery and a battery. So you have a 3-volt battery, and you wire in series with this a speaker. All right, so far so good.
Yeah.
You wire a speaker in series with the battery, and so long as the speaker doesn't get destroyed, everything's fine. You could, I assume, you could probably decouple that using a capacitor as well. But by doing that, what that does is it very slightly changes the voltage that the laser sees, which essentially makes the amplitude of the beam increase and decrease. If you then have on the other end a photovoltaic or a photocell, which generates a voltage from light, and you can play this through a speaker, what you end up with is demodulating your amplitude modulated voice, and it comes out on the speaker.
Wow.
That's essentially modulating a light beam.
Mm-hmm.
I've actually seen that done. That's very cool.
It sounds cool.
Yeah. All right, here we go. Resistors. So we are now on to, we pretty much covered this, but we're going to cover it here anyway. We are on the 23rd page of the manual. Resistors. Okay. Very quickly, the electrical component that opposes the flow of current in a DC circuit is known as a resistor. An adjustable volume control is called a potentiometer, or a pot for short. A pot basically is a very special looking device which looks like this. This is a resistor, right? Now it may actually be that a resistor is built like this with a bunch of windings. By taking a wiper and putting it in a variable place, for instance, that changes the amount of the circuit that gets shorted out, which changes the overall resistance. That can be drawn like this, or it can also be drawn like this. All of those are potentiometers, or a pot, or pots. A pot. Okay, let's see. Okay, next one, capacitors. Okay, a capacitor is a much less boring device. The reason that we have this thing called a capacitor is because we have these things called electrons. So if we draw two parallel metal plates and we put positive charges over here, what do we know about positive and negative charges? Opposites attract, like repels. If we put positives on one side, all the positives will try to get away as far as they can, and all the negatives will try to get away from here. So we will basically try to develop a balance in between here. Well, these are actually trying to get together, to actually combine with each other, but they're being physically held apart by this space. The force that is applied through that space where they're trying to pull those plates together, that is actually a force that they're physically trying to apply. This is called an electric field. They actually have a voltage differential that exists between them. So this would be on the positive side, and this would be on the negative side. So this actually generates this thing called an electric field in between the plates that's trying to pull those sides together. So the stronger the electric field, the more they're trying to pull toward each other. The stronger the electric field, the more energy is stored in between them. So if you have a lot of pluses and a lot of minuses, you might have a lot of voltage across the capacitor, where they basically are pulling really hard to get together. So a capacitor is an energy storage device that stores electric field energy. It stores energy in an electric field. Now here's another device that we have called an inductor, which is sort of the analog to a capacitor. Well, if this stores energy in an electric field, this stores energy in a magnetic field. The reason being, if everybody holds up their right hand and wiggles their thumb, your thumb is the direction of current flow, and you take your fingers and wrap them forward. It has to be the right hand. I'm sorry if you're left-handed. If you roll your fingers forward, that is the direction of a magnetic field. So if you have a current flow that goes this way, you have a current that sort of wraps around the wire. So if you have a coil, what this does is it generates a continually changing direction of magnetic field, and we can actually draw this by going like that. This is also known as a solenoid, and a capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. So this is a capacitor, and this is an inductor. So this is an electric field. This is a magnetic field. Okay, now Herein lies the issue with these two devices. This is where everything gets really interesting. So let's say we have a capacitor and we hook this up to a battery, which has pluses and minuses. What's going to happen is that the pluses show up over here and the minuses show up over here. What happens if we then completely disconnect the battery? Where do the pluses and minuses go?
They stay there.
They stay there. This actually keeps the capacitor charged, which you can then, if you, for instance, have a resistor that you insert into the circuit that looks like this. What will happen to the energy that you've stored? It will generate a current that flows through the resistor. This is the basis for something called a supercapacitor or an ultracapacitor, which is basically like a battery except that it's a temporary storage of energy. This is also the basis that we use capacitors for something called filtering. So for instance, if we have a voltage that is varying, what will happen is that when the voltage goes to its peak, it will charge the capacitor. As the voltage drops, the capacitor will exchange some of that current and tend to smooth out the result. Capacitors work really well for filters for that very reason. But now let's draw an inductor. Well, actually, let's take a look. One more thing on a capacitor. So now we've charged up the capacitor, but now we're going to play a trick on the capacitor. We're going to switch plus and minus. So plus is now over here. What's going to happen to all the positive charges that are already in the capacitor when they suddenly see themselves hooked to a negative terminal? They're going to flow. Everything's going to flow back to the source, right? Everything's going to flow back to the source. And then what's going to happen? And the longer we leave it charged, this becomes minus, and the new minus, and this becomes the new plus. Well, what happens if we then switch this and we reverse it again, and this is the plus and this is the minus? What's going to happen again?
The opposite.
Yeah, well, you're going to end up with these disappearing and being replaced yet again. Right? So the capacitor basically becomes this little compliant thing that if you're switching the voltage fast enough, it kind of acts like, well, okay, I'll go along with it. What is it called when you switch a voltage back and forth?
Reversing polarity.
That's called AC. Right? That is alternating current. If I switch my power supply back and forth and change the polarity over and over and over, that is the definition of AC. So now what happens to this capacitor is the capacitor charges up and then discharges and charges the other way and discharges. And what happens is, now let's say I draw a curtain and I cannot see what is on this side of the curtain. Okay? I can't see what's on that side of the curtain. But every time I switch the polarity of my source, the current moves back and forth. What does it look like, as far as I'm concerned, is on the other side of that curtain? If it acts just like a piece of wire. It might as well be that. And what is that? That has a name. What is that thing?
Short circuit.
That's a short circuit. So for a high frequency current, AC, for a capacitor, does what? It looks like a short. Well, similarly, if I were to just leave it hooked up, and there's actually a capacitor on the other side of this wall, and here's my plus and here's my minus, the capacitor goes to plus and minus like that. And then what happens when it's full?
Current stops.
It stops. Well, if I know, all I know is that there is no current flow, what is that the equivalent of?
Open circuit.
An open circuit. It might as well be this. So for DC, a capacitance is an open circuit. So now we're going to draw an inductor. All right. So if I hook up an inductor to a battery like that, what is an inductor? An inductor is a coil of wire. What does a coil of wire look like? Just a piece of wire, right? If I'm at DC, it just looks like a piece of wire. So L is my inductance, it's called. This is C, this is an L. For DC, this looks like a short. And how about for AC? What happens in here is if I have a coil, how does an inductor store energy? In a magnetic field, right? It generates these magnetic field lines around the coil. What if I take this inductor and I get rid of the battery? First of all, what happens if I do that? Where does the energy go?
Doesn't go anywhere.
Well, that's right. Well, but the thing that was making the energy in the first place is no longer there. It required current to be flowing because a coil, right? A current makes a magnetic field. A magnetic field can make a current. Well, in this case, what happens? Now we have this magnetic field floating in space. So what happens to it? It either dissipates somehow, or it says, I got all this energy. I have nowhere to put it now. It can't store it. So what happens is it says, okay, well, I have all this energy. I better figure out a way to do it. So the voltage across these terminals increases until you get one of these. And I should draw it in blue. And it looks like that. And that is known as a spark. So you basically have a lot of voltage generating a current to dissipate that energy. And that's what happens if you remove the current suddenly from an inductor. So clearly an inductor is not very happy with change, right? Inductors are really, really great with just staying the way they're going, but not so much change. This is actually the basis for old ignition systems in cars. You'd basically charge up a coil and then suddenly disconnect it. And then when you suddenly disconnect it, all that energy, magnetic field energy, has nowhere to go. But then you give it a path, which is known as a spark plug. And you allow it to generate a spark and dissipate. So instead, what we're going to do is say, okay, well, we're gonna do this with the inductor. We're going to take the voltage that it's connected to, and we're going to reverse it. And so now here's our plus and here's our minus, and it wants to change the direction of the inductor's magnetic field. So in other words, now it doesn't just have to dissipate it, it actually has to try to dissipate it and then reinitialize it in the other direction, which means all that energy is going to get dumped into the battery and then thrown back the other direction. It's actually, I mean, if you think about it, it's very hard on the source. The easiest way for the inductor to do this is to say, well, if it's changing, I'm just not going to respond at all. And if it doesn't respond at all, it's like it's not even there. And what does that look like again?
Open circuit.
An open circuit. So for an AC, an inductor is an open circuit. Or in the extreme, it looks like an open circuit. And this is why capacitors, which are measured in farads, and inductors, which are measured in units of henries. Inductors use the letter L, capacitors use the letter C. This is why resistors are boring. Does a resistor care what frequency is going through it?
No.
Nope. Doesn't care what, it doesn't care how much you do through it. Doesn't care whether it goes this way or that way. Capacitors and inductors do care. It actually matters what frequency goes through them. And if the frequency, and I should say for AC, which is actually infinity frequency, and AC infinity frequency, and DC, which is 0, that's what they turn into. Well, what makes these devices really, really, really interesting is the fact that it's not an absolute thing. That for a capacitor and for an inductor, we now have a new term, which is called impedance. Right? So if you think about resistance, they already had that one term, which is to resist current flow. Well, they had to come up with a new and similar term, which is to impede current flow, right? They kind of mean the same thing. They both mean something's getting in the way. Resistance is specifically for DC. Impedance is specifically resisting the flow of AC current. For a resistor, they are equal. Excuse me. This is the letter R. This is the letter Z. And confusingly, they're both measured in ohms. Ohms. For a resistor, they are equal. Z equals R. However, as we just saw, for capacitors and inductors, they are definitely not. And as it turns out, for a capacitor, ZC is minus J over 2 pi FC. And for an inductor, it's 2 pi FL. And this is a capacitor, and this is an inductor. Notice the values, C and L, actually show up in there. What else shows up in there? Everyone see that little letter F? We just talked about that this morning. What is F?
Farad.
Nope.
Frequency.
Frequency, which means that the impedance that each of those devices applies to the circuit is dependent on the frequency of the frequency of the energy going into it. Ah. Wow. Okay. Well, so now basically we have a frequency dependent circuit. Can anybody think of any way that we might be able to use this to our advantage? Well, if we have Z is equal to minus J over 2 pi FC, and then we put in series an inductor, Z is equal to 2 pi FL, J2 pi FL. What do you notice about this minus sign and the lack of a minus sign right here? Well, this is negative, and this is a positive impedance. Could we make them equal and opposite? What do you think? Could we make them equal and opposite?
Should be able to.
Yep. So we can. And we say, okay, we're going to make them equal and opposite. So 1 over 2 pi FC is equal to 2 pi FL. Which means we can solve for frequency and get 1 over 2 pi square root of LC. This is really important as you continue on in your studies and understanding of resonant circuits. This right here, frequency is equal to 1 over 2 pi square root of the inductance times the capacitance, is also known as a resonant frequency. This is the natural frequency of resonance for a circuit that has a capacitor and an inductor in series. And what that means is, since they cancel, if I have a chart of frequency from 0 to infinity, there will be a specific point, and if I have my impedance right here, where it will be really, really high, and then all of a sudden, it'll go like that. And what does that mean if I have 0 impedance at a certain frequency? What does that mean? If you think about it.
High current flow.
You get high current flow. At how many different frequencies?
very, very narrow band.
Very narrow. You get basically one good frequency. And as you get further away from that frequency, its ability to pass different frequencies gets worse. Can you think of anything that you'd like to use that for, maybe? This is known as a filter. We use them everywhere. These are used in every electronic device. You have many filters inside your phone. They're used for audio filtering. They're used for RF filtering, for radio frequencies. They're used to make sure that your phone actually works at a given frequency and doesn't produce all kinds of noise that would trash aircraft, for instance. You know, that's when they say, make sure you turn your phone off, et cetera, in airplane mode. In reality, your phone is pretty well designed. They're protecting against the ability of they're basically protecting against the fact that there might be something that isn't designed properly, that isn't filtered properly, that will cause interference. But essentially, capacitors and inductors are the devices that give us the ability to operate within certain frequency bands and not have everybody wiping everybody else out who are using the radio. So really important stuff. Okay, so capacitors. Let me share this. Okay, what type of electrical component consists of conductive surfaces separated by an insulator or a space? That's a capacitor. Stores energy in an electric field. What describes the ability to store energy in an electric field is called capacitance. The unit of capacitance is the farad. Okay, so inductors. The electrical component, typically constructed as a coil of wire, is an inductor. It stores energy in a magnetic field. The ability to store energy in a magnetic field is called inductance, and the unit is the Henry. Okay, so now we're into batteries. There are a battery is basic.
Scott,
Yes.
just before we do that, can I just ask a quick question?
Sure.
I don't want to take you too far afield, but just if you can answer briefly. I'm guessing that the J that you had in the formulas for the capacitor and the inductor is what mathematicians would call I. It's the imaginary unit.
Yep.
Would it be safe to say then that inductance actually has a real and an imaginary component, and the impedance has a real and imaginary component, and the real component is a resistive component, and the other one is imaginary, and that's what comes from inductors and capacitors.
There you go. There it is on the screen. So here's your real, and here's your imaginary. So here's your X, and this is actually known as reactance. So real is always in the plus direction, and reactance is always up and down. So that's why you have the J, it's in the imaginary direction, which is not really imaginary. It just means that it's orthogonal to it, right? So, but what that also means is that you can have, in the positive direction, you can have inductors. You will have inductors. And in the negative direction, you'll have capacitors. And they can cancel each other out. And the other cool thing about impedances is that it actually redraws Ohm's law. Instead of E equals I times R, what we will find is now we've replaced it and is equal to E equals I times Z. Right? It's just a different letter. But if we go back to the trigonometry, you'll find that if your Z looks like this, let's say it's 100 ohms. It also has an angle so that you have a real component and an imaginary component. And they are defined by the Pythagorean theorem. Z is equal to square root of x squared plus r squared. That's the magnitude of Z. And the angle, the angle theta is equal to the arctangent of x over r.
So what that does is, because now your formula is E equals I times Z, what happens is if you have a current which looks like this, then you multiply that by a Z, which not only has a magnitude, but it also has an angle. What you will end up with is if this is your current, let's say it adds a positive shift, what you'll end up with is a phase shifted voltage, depending on whether it's capacitive or inductive. And you'll get into that in the general and the extra exams.
So just quickly then, does the imaginary component represent energy stored and the real component represent energy dissipated?
No, it really is. It really is a phase shift. It's a phase shift between current and voltage. It's a way of showing that it generates a phase shift between current and voltage. And the reason that we have this thing called VAR versus watts, volts amps reactive, is because of the fact that, so now if I were to do, let's say the formula P equals I times E, well, I would have I times let's see, E, that would be I times Z, but it's the magnitude times the angle of the phase shift. So that angle of the phase shift basically means that some of the power is not in phase, because this has an angle as well. So does this. So basically the power that isn't in phase doesn't turn into actual power. You know what it's hard, kind of a little hard to explain, but basically if you get into something called power factor, that is the cosine of the phase angle. And the reason that it's important is because if you have, let's say, a voltage, if I were to draw this, if I were to have a voltage and a current that were out of phase, like let's say that here's the voltage and here's the current, they would generate no actual power when multiplied together. They would generate no power whatsoever. But if you ask the power company, how much current do they have to deliver? They still have to deliver current. And that's why electrical power companies find it very important to have power correction. They try to get these two quantities down on the same axis, because that becomes real power. So basically the power that you're using to run your factory is the same amount of current that they're delivering. It costs them money to deliver current. So the less you're wasting, the more efficiently you're using it, the more efficiently they're delivering it. Does that make sense?
Mm-hmm. Yeah. Thank you.
Sorry. Like I said, tangents, but maybe somebody learned something from one of those tangents. And if you didn't, I'm sorry.
Certainly did. Thank you.
Okay. Other questions before we move? Nothing? Okay. Batteries. A battery is a chemical storage device for storing energy. Some chemistries are not rechargeable, like your standard old carbon zinc battery, your silver oxide air. Basically, when they're dead, they're dead. A standard lithium metal battery, kind of like your button cell that's inside inside your old watch, which is designed to run for 5 years, and then you basically get rid of it and get a new one. That's a non-rechargeable battery. There are a lot of batteries that are rechargeable, like nickel metal hydride, NiCad, lithium ion, lead acid. Lead acid is your car battery, basically. Okay, so now we're into diodes. So we're going to start drawing circuits now. Okay, a diode is a very important device. This was developed in, I want to say probably 1920s, maybe a little earlier, where you basically have a device that consists of two different pieces of silicon, silicon being element number 14, which is halfway between one end of the chart and the other end of the chart. In the outer valence shell of electrons, it has 4 electrons, and anything between 0 and 4 kind of acts like a metal, and anything between 4 and 8 acts like a non-metal. So it kind of acts like something in between. We can also use something called germanium. Germanium is in the same boat. So what we can do is, since it's not really a conductor or not a conductor, we can basically throw in some additional things. We'll throw in additional electrons on one side, and we'll take some electrons away, and we'll call that a hole. And we do this by adding some impurities that have extra or a lack of electrons. And what we do is we kind of tip the scale a little bit. And by doing this, we make it easier for current to flow in one direction than the other. So we have something called an anode and a cathode. This is the anode, and this is the cathode. This is the negative terminal. This is the positive terminal. And a diode is a special device that if we have a voltage that's higher on this side than on this side, it allows current to flow. If we have a voltage that is lower on this side than the other side, it does not allow current to flow. So it is like a one-way street. So this is really, really important for electricity, because what happens is, let's say we have a voltage that looks like this, where it's positive and negative. What happens when it's positive? We get the current flowing. But what happens when it goes negative?
Stops flowing.
It stops. And what happens when it flips back positive again?
Starts to flow again.
And when we lose it?
Same over.
Yep, same thing, over and over and over. So what happens is that this part disappears, and we end up with a voltage that goes up and then flattens out, and then goes up again and flattens out. Because it's always flowing in the same direction. What is this called? This is known as DC. And what did we have originally going in? We had this. What is this called? That has a name. That is AC. So what have we just been able to do by using a one-way device, everybody?
Change AC to DC?
We change AC to DC like magic, right? So we basically have, this is known as rectification. And if we use 4 of these diodes, we could actually take what's down here on the bottom and flip it so that we actually use more of the waveform. The first way was known as half-wave rectification. What you see here is known as full-wave rectification. This is at the heart of every DC power supply known to man. If you have a DC power supply, it relies on this thing called a diode to make it work. Now, what we now have is this thing called a diode, which looks like this, which is a one-way street. We can then hook this up to an AC power supply that looks like this. We're going to draw this thing called a ground, which is our 0-volt reference. So again, we have a voltage that goes up and down and up and down. Coming through the diode, we now block all the negative side stuff, and we have a voltage that looks like this, which is a crude DC voltage. We can then take this and use the peaks to charge up this capacitor. So we take all the big peaks and use it to charge the capacitor. Then when it drops off, the capacitor dumps its energy back, and we end up with a smoothing factor. They said capacitors can act as filters for noise. And then we can take this and run this through a resistor, a variable resistor, and through another resistor, and then we can run it through something called a Zener diode. A Zener diode is like a regular old diode, except that it's reversed. It's made to run backwards. It acts as a voltage reference. So what this does, it basically takes this ugly waveform, which looks like this. Try putting that into your computer and see how happy your computer is. So what it does is it says anything over this line, I'm going to just throw away. So it basically scrapes all the stuff at the top and scrapes it off. And what do you end up with? Nice, clean, direct current. And this is known as a power supply. And it relies on the diode for allowing it to do it. A diode is a semiconductor made of two differently doped pieces of silicon typically. One is positively doped, one is negatively doped. Okay, let me go back to this. Okay, so if you find a diode is going to look typically like a little black tube with a stripe on one end. The stripe is the cathode, and it's going to be the negative terminal. Okay, one thing about diodes is that a diode does not work at 0 volts exactly. It takes a little bit of forward voltage available to turn it on in the first place. So that's known as its bias. A silicon diode requires 0.7 of a volt to make it turn on, to sort of get over that hump. Germanium diode is typically about 0.3 of a volt. A very special type of diode looks like this. Everybody see that bright light? This is just on my, okay, let me unshare that. There we go. Everybody see the annoyingly bright light on the picture of me? All right, that's a light emitting diode. It basically, instead of just turning on, one of the byproducts of it being forward biased is that it emits light. By changing the chemistry and by changing the material that makes up the diode, you can change the color. You can make a red one, you can make a green one, you can make a blue one. Okay, a transistor is another type of semiconductor. Again, a semiconductor is typically made of silicon. And if you think of a diode, again, which looks like this, which is a sandwich of two different materials with nothing in between, a transistor is a sandwich made of two identical materials. So let's say we call this an N, and that's N, silicon. And the sandwich, the meat of the sandwich is a P. Now, this could also be reversed, where you have a P, the bread is the P, and the N is the material inside the sandwich. What this allows us to do is, if we stack this vertically instead of horizontally, we do something that looks like this. So we have our N and we have our P. So this is actually known as an NPN bipolar junction transistor because we look at the different layers. There's an NPN. What we do is we bias this to here, and we put a small voltage here, and that allows a current to flow through this channel. And by hooking up another voltage here, that allows a large current to flow that is largely proportional to what goes into here. So this has some very, very important implications. Number one is that if we look at how a transistor works, it basically takes a certain amount of voltage and current to turn it on. Once it gets turned on, it levels out. So here's our input and here's our output curve. And at some point, no matter how much more you put in, you can't get any more out. So there's 3 different areas of operation. This is called cutoff. And this is called saturation, meaning you can't put anything else in. And this is known as the linear part of the curve because it's basically a straight line. What's great about transistors is that depending on where you decide to use it, this determines how you can use it. So if I want to make an amplifier, I could say that here's my 0 point, and my signal goes a little bit bigger and a little bit smaller, and here's the output. Here's my 0 point, and when it's smaller, it's way down here, and when it's bigger, it's way up here, and hopefully this is proportional, and I can make a nice copy of the signal that went in. This is known as an amplifier, and it relies on the linear portion of the transistor curve. If I instead say, you know what, I don't care about that linear portion. I either want it to be solidly off or solidly on. So here's in, here's off, and here's on. This basically will say when I'm off, I'm off. Nothing comes out. And when I'm on, everything comes out. This is known as a switch. This is how computers work. Basically, you don't want that in-between stuff. You know, a computer operates digitally. The values are either ones or zeros. You don't want you don't want a value of a half in your computer, right? You want either a 1 or a 0. This is the way to make sure that you get either a 1 or a 0, by either slamming it off or opening the door completely. So that's why a transistor can be used as a switch or as an amplifier. So a transistor has a special circuit representation that looks like this. This is, again, a bipolar junction transistor. It's called. It has 3 terminals. This is a collector, a base, and an emitter. And by putting a voltage over here, we're going to ground that. A small current there will generate a really big current there. Allows us to operate both either as a switch or as an amplifier. Now, an important thing to note about this is, how do I remember which is which? If you look at the arrow, this is not pointing in. N, P, N. It's a nice little mnemonic, right? So this is obviously an NPN transistor because it's not pointing in, the arrow is pointing out. Now, if I were to reverse it, that would be a PNP transistor, but this is the easiest way to remember it. There's another type of transistor which looks something like this. This is actually much more commonly used in, well, most of electronics these days. It turns out that a bipolar junction transistor is not terribly efficient. This is a lot more efficient. Okay, so I'm going to ask everybody to look at what's right there. What does this thing look like? We just drew it about half an hour ago. That looks like a capacitor, yeah. So if I put pluses over here, what's going to happen to the other side? What am I going to get?
Negatives.
I'm going to get negatives, yeah. So those are controlled by an electric field. This is actually a field effect transistor. So by merely placing a voltage on this side of the transistor, that determines what happens in the channel. So by putting a voltage here, that determines how much current can flow through. This is known as the gate, and this is the drain, and this is the source. And current then flows through the channel. And depending on how it's built, you can have an N channel or a P channel. And usually there's an arrow right there indicating the direction of the channel. But what's important to note is that this is a much more efficient transistor than a bipolar junction transistor. And again, this is known as a FET or FET. Most power amplifiers today Most switching circuits are based on FETs instead of bipolar junction because of the much better efficiency. I think, to be totally honest, they're actually a lot easier to build if you're building a computer chip. You know, if you're doing a large wafer fab, it's much easier to build these as well. So you can put, this is typically when they say, you know, we've got 1 billion transistors on a chip, this is typically what you get. Okay, so what we're going to do is share this again. And we're going to share, stop sharing, yes. Okay, here we go. Okay. Which of the following can be used as an electronic switch? Well, it's a transistor. It can also be used as an amplifier. What is gain measured in, everybody?
dB.
dB, decibels. There it is again. A transistor can provide power gain. Three pieces of silicon, of semiconductor material, is a transistor. Again, those terminals, emitter, base, and collector. A FET stands for a field effect transistor. And then you have a gate, drain, and source. That's in the field effect transistor. However you want to remember it, you know, there's no easy mnemonic to remember that I've ever seen. All right, so now instead of redrawing this, we're just going to look at this. This is schematics, schematic symbols, component functions, and things like that. Okay, the difference between a schematic and a wiring diagram and like a construction diagram is that a schematic is not a representation of how things physically look on a circuit board. A schematic is basically a drawing of all the things that are in your circuit using standard electrical drawing, you know, standard electrical looking components. So for instance, like a resistor, element number 1 here is a resistor. Like right there, I would not actually look on a circuit board and expect to see a device that looked like that, right? That's the representation of what a resistor should, you know, look like on a schematic. Same thing with number 2. Anyone know what that is?
Switch.
In particular, what kind of device is it? We just drew one.
BJT.
That's a bipolar junction transistor. And is it PNP or NPN?
NPN.
Because?
Or
And why is it NPN?
Not pointing in.
It's not pointing in. That's right. The arrow is pointing out, not pointing in. And this basically is, in fact, a switching circuit. And if I zoom in, and let me see if I can modify this at all. I don't know if I can. Oh, I think I can. I should be able to annotate it. Maybe it's not going to let me annotate. Okay, it's not going to let me annotate it. Okay, the left hand of the circuit, if we were to draw a... I'm going to have to draw it after all. Darn it. Okay.
I think actually when you have that program open, if you open up the comment section, if you like open it in full, there's the ability to draw on the PDFs with the pencil.
Okay. Well, I'm just going to do it by hand for now. But yeah, I'll have to play with that. It seems spotty whether or not it works. Okay. So what we're going to do is take this transistor and we're going to split it down the middle like that. Okay, so essentially we've got the left-hand part of the circuit because if you remember, this is the base, this is the collector, this is the emitter. We get bias that goes from the base to the emitter. So if we get a little bit of voltage flowing through there, this other circuit on the right-hand side, which goes from 0 volts through a battery, through a light up top, will then allow current to flow down through here. And if current flows down through here, that means it also flowed through the light. So by splitting this circuit in half, what this allowed us to do is basically put a signal here, which is an on or an off. And when it's on, we get the light being on. And when it's off, we get the light being off. This is a remotely controlled switch using a transistor in its cutoff and saturation state. So this is a remotely controlled switch. Okay, next. Okay, can everybody see that?
Nope.
How about now?
Yeah.
Okay, good. Okay. All right, so what we have here is the next circuit. Here we go. Okay, so item number 1, this is an AC power supply. Item number 2 is a fuse. Item 3 is a switch. How about number 4?
Resistor.
It's not a resistor.
Transformer.
That's a transformer. All right, a transformer is basically 2 inductors wound back to back. Now, what we determined about what we're going to do is use what we know so far and say we're going to make this core. We're going to wrap a wire around here and a wire around here. This is our in and this is our out. So every piece of wire that's carrying a current makes a magnetic field. Agreed?
Mm-hmm.
Okay. Every magnetic field passing through a piece of wire should make a current. It works backwards, right? So what we do here is we put current into this coil. This core is actually made of usually iron or steel, some material that is able to carry a magnetic field really well. Essentially, it concentrates the magnetic field inside it. And when you do manage to switch the current back and forth, what happens is that the magnetic field will change direction. You can actually do it if you push hard enough. So by changing direction, what that does is if my current coming into the inside changes direction, the current going out of the outside changes direction also. Well, the voltage that is made by a coil is actually proportional to the number of times you have wire wrapped around it. So if I have 10 wraps of wire around this side and 100 wraps of wire around this side, and I have, let's say, 120 volts AC, this only works with AC, going into this side, I will have 1,200 volts AC coming out this side. And it's totally reversible. So if I were to flip this around and say that I had, this is my new input, and this is my new output, and I had 120 volts going in on this side, I would have only 12 volts coming out on this side. This is the basis for power conversion. This is how the power company will take your power line at 12,400 volts and convert it down to 120 volts so that you can run all your appliances in your home. This is also how the power company will take, let's say, 1,000 volts out of their generating station and generate 765,000 volts to send all over the world, or at least all over North America to use. The reason that they do this is because what do we know about energy? Energy can neither be
Created or destroyed.
created or destroyed. It just changes form. The transfer efficiency of a transformer can be like 99%. So you have very, 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 very little loss of energy in a transformer, which is great. Essentially, it gives you almost perfect conversion of energy. And if I need to transmit, let's say 100,000 kW of power, or kW of power, and I do it at 1,000 volts, you start looking at the current, and it's, let's say, 100,000 amps. Whereas if I can raise it to 765,000 volts, it might only be 200 amps. Well, what's another thing we can't get away from? Ohm's law, right? E is equal to I times R, and P is equal to I times E. If my current is big, my voltage drop is big. If my current is big, my power loss is big, which basically means that it behooves the power company to bump up that voltage as much as they can before sending it out. That's why the power line out on the street is 12,000 volts instead of 120 volts. It also means, because they have to carry much less current, that they can use a lot smaller wire. They just have to increase the spacing so that they don't short together and cause a big spark. So back to our transformer. So what we have here is a transformer that steps down the 120 volts coming out of the wall to something more usable, something like 12 volts DC. We then have number 5. What is that, everybody?
That's a diode.
That's a diode. Number 6 is a
capacitor.
The capacitor serves to smooth out the voltage that the diode has now made. This is actually the beginnings of a power supply. All right. This right here, 7 and 8. Number 8 is a special looking diode with arrows coming out of it. That would be light, so that's a light emitting diode. This is our indicator showing that the power is on. Number 9 is for voltage and current limiting. And number 10 is our Zener diode, giving us a stable voltage reference for our DC power supply, which now runs our computer. Okay.
Could I ask a quick question about
Absolutely.
transformers? Are there any transformers that have equal numbers of windings on the input side and output side?
That would be known as an isolation transformer.
Right. And what is the purpose? How and why are they used?
Because some transformers, they actually have impedance. And if you think about it, if you wind a transformer, let's say, what type of frequencies are you using when you're talking about power?
Very low frequency.
What frequency? The wall power.
60
hertz. Well, okay. So because an inductor is a frequency specific component, right? Inductors look really, really good for low current, for low frequencies. What happens when the current gets really high? Their impedance goes up by a lot. So what happens if you have a combination of, let's say, 60 hertz power with like RF, like at a megahertz? What happens when you put it through the transformer? The 60 hertz will pass through. And what happens to the RF?
It's filtered out.
It gets filtered out. It just basically turns into heat, which basically cleans up your power. And we use that. We actually use that in industry. It's called an isolation transformer for that very reason. The other thing we can do is we can actually intentionally pick a transformer and wire it as an isolation transformer so that it works at RF and not at any other frequency. And that would be a transformer type known as an un-un, or an unbalanced to unbalanced at one particular impedance that doesn't change. We can do that on purpose. Okay, something about switches. What type of switch is represented by component 3? That's a single pole, single throw. So the fact that it's single pole means that there's only one circuit. Single throw means that it's either open or closed. If we had 2 of those in parallel, that would be a double pole single throw because it would be 2 circuits. If we had 3 of them in parallel, all connected to a switch, that would be a triple pole single throw. If there were, for instance, if anyone has a 3-way light switch, where you can go one way, or and there's a center position, and then there's go the other way, that would be like a double pole single throw, or sorry, single pole double throw. So, because it's only one circuit, but it can operate in one way or the other. Okay, transformer. Okay, which of the following devices or circuits changes an alternating current into a varying DC signal is known as a rectifier? We talked about capacitors. Filter capacitors filter out remnants of AC. They're great for that. Okay, now we're into creative use of inductors and capacitors. And after this, we're going to go get lunch. So, okay, here we go. Creative uses of inductors and capacitors. Okay, the fact that each of those devices that you see there, well, we'll look at 2 and 3. Number 4 is an antenna. Number 1 is a source of RF. But 2 and the unnamed component, those are basically identical. Well, those are capacitors, but notice the arrow going through them. That means it's a variable capacitor. And in particular, the most common look for something like this is something that looks like this. Let me unshare that. And you may have seen something like this before. Anyone ever seen anything that looks like that?
Yeah.
In
Okay.
old-time radios.
Yep. Okay. This, notice it says a variable capacitor. Well, a capacitor's value is determined by the amount of plate of one side that is right next to the amount of plate from the other side. If I take 2 plates and I mesh them completely, I have increased the area that are opposite each other. If I unmesh them, each of those is like a hemisphere or semicircle. If I unmesh them, I've reduced the amount of plate that's parallel. So basically what this allows us to do is by meshing more or less of the plate materials, that changes the capacitance of that device. Now, there's also something called a roller inductor. All right, so this is a roller inductor. An inductor is just basically a coil of wire. But now, a roller inductor is a device that has a wiper which allows you to basically short out a piece or a whole section of the inductor by moving the wiper along by virtue of a hand-operated crank. So this is the inductor analog to the variable capacitor. Now you can also just have a plain old inductor that has soldered taps that have different wires and a switch to select the tap. What these allow us to do is, if you'll remember the fact that, I know this is a lot, but if you remember that impedances are, for a capacitor, minus J over 2 pi FC, and for an inductor, J 2 pi FC, the fact that, J 2 pi FL, the fact that, so this is ZC and this is ZL, the fact that these values show up here and here, they impact, these values and the frequencies impact the impedances. The values of the capacitor and the inductor change the impedance. And if I have a capacitor that looks like this on one side and the other side looks like this and they're totally unmeshed, thus has almost zero capacitance. But if I were to rotate one so that instead it looked like this, here's the other side. If I rotate it so that it's completely meshed, that is maximum capacitance. And everywhere in between is a different value. What that allows me to do is change the value of that capacitor and thus change the impedance. And by doing that, what I can do is, if I draw this circuit that they've drawn, which looks like this, this is an inductor and 2 capacitors. Here's my antenna. Here's my transmitter over here. This is my antenna. This has some impedance. We'll call it Z unknown, because it might be unknown. Okay, this is something we're going to cover. A transmitter today looks for an impedance of 50 ohms in the world. When it puts out power, it's looking for the system in the real world to have an impedance of 50 ohms, pure resistive, ideally. In other words, it's looking for it's looking for 50 plus J0 ohms. So no imaginary reactance at all. It's just looking for 50 ohms, pure resistive, to put energy into the world. Well, this is Z unknown. That's a problem, isn't it? Well, if I then take this capacitor and I adjust it so that it's, we'll call this one C2. If I adjust it so it has some Z C2, and I put that in series with Z unknown, I get the sum of the two. Well, I can then take those and put those effectively in parallel. These look like they're actually in parallel. This kind of looks like an endpoint. So now I have these in series in parallel with this one. And then I take the combination of all of those and I take ZC1 and I put it in series with that. And if I adjust them properly, I can actually tweak it in most cases so that the end result looks like 50 ohms pure resistive. And essentially through capacitors and inductors, I have done what is basically equivalent to magic. This is actually known as an impedance matching device. More commonly, it's called an antenna tuner. And what it does is it takes this unknown antenna impedance and makes it look like 50 ohms pure resistance.
Makes it look like that to the transmitter. Right?
To the transmitter. It doesn't actually fix anything, but what it means is that the transmitter can transmit power out into the world, and what ends up happening is that you end up with some mismatches out here where signals are sort of bouncing back and forth, but eventually they'll either dissipate in the cable or they'll go out of the antenna. And the transmitter itself is fat, dumb, and happy, as they say, transmitting full power, and a lot of it's going out. Now, what ends up happening is it's really, it's being tricked into thinking that the world is perfect, but it works well enough, and that's what an antenna tuner does. And when you actually
When you say it transmits full power, does that imply that there are conditions under which the transmitter won't transmit full power?
Oh yeah, if you have a mismatch. So let me pull up MFJ949E. Okay, so this is a very basic, but very nice. I have like 4 of them. Here we go. Let's see if this comes up. I'm striking out today. I just want to see a picture of the inside. Okay, there we go. So there's the inside. And you may notice some somewhat interesting looking components. You have the coil in the center, and then you have these 2 air variable capacitors to the right, which are meshing plates. And this is known as a T-type tuner because the two capacitors and the inductor form together to make what looks like a T shape on the schematic. And this is what it actually looks like inside. And they work remarkably well. And in order to tune it, basically, you end up with something that looks like this. You have a meter which measures forward and reflected power. Oh, look, there's a good picture of the inside. And by measuring forward and reflected power and adjusting your inductor and 2 capacitors, you can basically make the transmitter happy. Now, when I say make the transmitter happy, literally I mean make the transmitter happy. The reason you want to make your transmitter happy is because, let's say you have a transmitter here which uses transistors for its power generation, and it goes out into the real world. And in order to do this, your transmitter, let's say it needed to see 42 volts it's making a 42 volt signal as a sine wave with peak of 42 volts. Well, it gets out here, and let's say your cable has a characteristic impedance of 50 ohms, and your antenna is unknown. Well, this is kind of the analog of taking a rope and tying it to a doorknob and taking the rope and pulling it taut and then grabbing it in your hand and whipping the rope. If the rope were infinitely long, the wave that you made would travel down the rope and disappear and you'd never see it again. But if you have a mismatch, which is basically a rope tied to a door, what will happen is the energy will reflect back. Some of it will rattle the door, but a lot of it will come back if you were to do this. What happens is in this system, if you were to put out, let's say, a pulse of energy, some of it would go out and some of it would come back because you have an unknown impedance out here. And what ends up happening is that this signal that comes back is going to be shifted in amplitude and phase, and you can't really predict what it's going to be. And if it happens to look like this and is in phase, what will happen is that if you're already generating 42 volts here and this comes back with 20 volts, right here you have 62 volts, and let's say your transistor is only rated for 48 volts. What happens to your transistor?
The smoke gets out.
You let the smoke out and you end up buying a new amplifier because you just overvoltaged your transistor. So most transistor amplifiers today will actually sense what is happening in the world, whether or not they see signals coming back. And when they do see signals coming back that they know are going to generate problems, potentially the death of the equipment, they will intentionally limit the amount of current that can go out and the amount of voltage that can go out to generate power. And they will and this is known as fold back. And it's essentially very fast acting circuitry which can sense a big problem and kill the transmitter output before it destroys itself. Because the one thing that destroys devices, what is the biggest thing that'll destroy a device?
Overpowering it.
Overpower, and that generates heat. You basically overheat something, you over voltage something, and you let the smoke out. Smoke is the magic stuff inside a component that allows it to work, and once you let the smoke out, you can't put it back in. So this prevents the smoke from being let out, hopefully. And that is why if you use an antenna tuner, which is an impedance matching device, essentially, as far as the transistor output is concerned, as far as the transmitter is concerned, the world looks like 50 ohms. The power never comes back. It might be bouncing back and forth out here, and it might be heating your cable, but the transistor amplifier is happy. And it won't die. It won't die a premature death.
So would you recommend then, if you're shopping for equipment for your first base station, that you actually get an antenna tuner, or can you carefully buy antennas and connect them carefully so that you know the impedance?
I think it's always essential to have an impedance matching device of some kind. I mean, you don't absolutely need it. What I would say is that many radios today, internal to them, will have an ATU, which is an antenna tuning device, antenna matching device, built into the radio. But now what I will say is that typically these are good for a mismatch, because we're going to get to SWR this afternoon, of 3-to-1. So for a 50, basically if you have a 50 ohm characteristic impedance that you're looking for, this will be able to tune a mismatch of like 15 to 150 ohms, which is not terribly wide, especially if you're one who likes to experiment with antennas and feed lines and things like that. If you know you're going to be operating with 50 ohms, you can get away without it. But for instance, I use my antennas for lots and lots of different bands, and I never really know what the impedance is. So I actually have an antenna tuner built in, but I also have an external antenna tuner which has an impedance, which has a matching range of like, 4 to, let's say, 600 ohms. So that's a much wider range. That's like a 12-to-1 mismatch, and I can still use it. So for me, it's really, really helpful to have that external match. And I think for most people, if you want to use antennas for multiple purposes, you end up doing that.
Question.
Yes.
Does a ICOM 7300 have a antenna matcher? Like
It does. Yeah,
Okay.
it has an internal tuner, which is great for, again, for about a 3-to-1 mismatch.
Okay.
So, but I have, that's what I have. But I also have two external tuners for my antennas because I use them for lots of different frequencies. And I have found times when the internal tuner can't match it. Whereas I've never found a situation where I couldn't match it with an external tuner because the matching range is so much wider.
So is that what you do if you're like space limited and can't have a whole bunch of antennas? You just kind of repurpose them and take the power hit.
Yep.
And
because no antenna is worse than a bad antenna, and a bad antenna is worse than a good antenna. But if you have no antenna, again, I would rather have a bad antenna because at least you can do something with it.
right.
Okay, let's see. Resonant or tuned circuits. I think this is the last thing. We're just going to cover this part before lunch. Here we go. Resonant and tuned circuits. Okay. Why won't it let me zoom? There we go. Okay, which of the following is a resonant or tuned circuit? That would be an inductor and a capacitor in series or parallel where the impedances basically cancel each other out. That's a resonant or tuned circuit, which is combined with an inductor to make a resonant circuit. Resonant circuit is always a combination of an inductor and a capacitor. The function of an SPDT switch, that's a single pole double throw. Single pole means that it's a single circuit. Double throw means it can go one way or the other way. There are two active circuits. So a single circuit is switched between one of two other circuits. A single pole triple throw would be one circuit where you could go to A, B, or C. I have an antenna switch that actually has 6 poles. I have one radio and it hooks up to antennas A, B, C, D, E, or F, depending on the position I switch it to. A relay is an electrically controlled switch, basically using a coil of wire to pull in a contact. So it's kind of an inductor combined with a switch. A meter displays an electrical quantity as a numeric value. A device that combines several semiconductors and other components into one package is called an integrated circuit. Basically, any computer chip that you buy is an integrated circuit. Your standard old logic circuits, a timer circuit, like if it has 16 pins, that's going to be an integrated circuit. A device that's used to protect other circuit components from current overloads is called a fuse. And a reason to use shielded wire. Yay, shielded wire. Okay. The reason to use shielded wire is because every wire that's carrying a current generates a what, everybody?
Electromagnetic field.
A magnetic field. Okay. A wire that is sitting in a magnetic field will have what induced on it? So if a current makes a magnetic field makes a
Current.
current.
Magnetic field. Yeah.
Okay, so if I have two wires that are parallel to each other, what will happen if I have a current flowing through one?
It could induce a current in the other one.
It induces a current in the other one. So if I have a microphone cable that's carrying my voice, what will show up on this other cable? On this other wire?
Your microphone.
My voice, yeah. And what if I don't want that to happen? What I then do is I put a shield around this, which basically makes a closed system so that the magnetic field that's inside it stays inside. And I also shield this one so that if anything leaks out, I can catch it before it gets to the inside. That's why you use shielded cable. Okay. And I think that's all I've got for now until after lunch. Anybody with any questions before lunch? Any comments?
I've got one. I've got a quick one.
Go ahead.
Considering all the different components you've described and gone through
Yep.
that make up a radio.
Yep.
If there's a power outage and you want to run your station off battery power, does it matter if the inverter you use is sine wave or not sine wave?
That is a good question. Sine wave?
This,
It probably, I mean, personally, if I have a choice, I'm
sh-
going to run a pure
yeah.
sine wave
yeah,
inverter.
I understand that, but if if something happens in an earthquake or something and your sine wave inverter is damaged and you have just general ones to back up, I was just curious if it's going to do any damage, because I know charging cell phone batteries, satellite phone batteries, you want pure sine wave to use, otherwise you can hurt that battery. But going in the other direction, the battery out, I was just curious if you knew if it made any difference given the sensitivity of the components in the radio.
You know, a lot of it depends then on what you're actually, the quality of the power supply. All right, so you see this right here? Everybody see that?
Yeah.
Okay, so I have out in my garage where my station is, which gets very cold and very hot, unfortunately. I have my entire station on one of these. I have a power supply that runs through a charge controller. I can also hook up a solar panel to it. That is continually charging this big battery, which is essentially a 100 amp hour gel cell. So when they say 100 amp hours, that's either 10 amps for 10 hours, or 100 amps for 1 hour, or 1 amp for 100 hours. And I actually run all of my 12 volt equipment directly off of this. As far as inverters, the cost of a true, I mean, like I don't have to use an inverter because all my equipment runs off of 12 volts, except for my computer. Would I trust my computer to run off of a non-true sine wave inverter? Probably, if I had to. I mean, I would rather run it off of a true sine wave inverter.
Yeah, exactly.
Here, let me see how much these go for now.
I've got a 3,000 watt pure sine wave.
Wow, that's a big inverter.
I run solar and wind generators, small units to charge it. But if there were an emergency or a power outage and I wanted to run a radio, I would certainly run it off the sine wave. But if something happened to that and I had to back it up with inverters that were not, I was just curious if I damage any of the.
Probably not. Okay, let's. Okay, so what I'm going to do is, oh, geez, look at that garbage.
Okay. Don't take too much time.
No, here we go. This is actually significant. Okay, so what is that, everybody? What does that look like? That's a sine. That's a somewhat crude sine wave. Okay, so what is this? What does that look like?
It's not as smooth.
Yeah, it looks pretty crappy, right? So this is a piecewise sine wave, I guess you'd call it. Right? So this is what, when you digitize something, this is what it looks like. The better the inverter, the closer it will get to a sine wave. I mean, and this is actually the problem. When we used to have something called a frequency synthesizer, it would actually do this because the computer that was running it wasn't all that fast. It would actually generate individual levels And that would be close to a sine wave. But what you'll notice is that it's not really a sine wave, it's a choppy sine wave. And that choppiness generates other frequencies at much, much higher frequencies than in this case. Let's say it was 60 hertz. If you had a frequency synthesizer that was running at, let's say, 2 megahertz, and it looked like this, you would have a frequency representation that, here, okay, here's your 2 megahertz signal. You would have harmonics that are like this. You would generate all kinds of other harmonics frequencies. So that noise shows up in the spectrum and basically it looks dirty.
Yeah.
That is essentially what's happening if you have an inverter that's not a really good sine wave. You're generating other frequencies. So a lot of it depends on the ability of the power supply that you're running with it or the device you're running with it to reject all that other garbage coming out of it.
Thank you. Appreciate that.
Everybody ready for lunch? Half an hour? Half an hour.
All right.
Anybody with any comments? I'll stick around for a few minutes because it won't take me that long to make it. Is anyone's mind like totally fried right now?
Mine is.
Is it? Okay.
Ain't no doubt.
Lally, did your husband make it today?
No, he got to the part on decibels in the book and got completely confused and lost interest. So
okay.
He doesn't have enough reason to push through. That was the book really poorly explains that concept.
Yeah.
I don't think they say anything about the logs and or
well, no, and actually
they mention it just as a ratio, but it was
Well, that's why that's why I use the book as a basis for what I'm teaching rather than read the book.
You did it much better.
Good, thank you.
Yeah. So I think it's going to be something that I have the potential to use with the kids, and so it's really important for me where he doesn't have that motivation.
Yeah, well, we'll get him there. I'm not going to let him off the hook that easily.
But my dad was thrilled that I was doing it too.
Cool. And what's his call again? KP2?
KP2 BU.
BU. Okay, cool.
Yep.
All right. Well, I hope it hasn't been completely overwhelming for everyone. I'm going to go get lunch.
Definitely need lunch.
Remember to hit record. All right. Well, everybody ready to keep going after lunch?
Ready?
I had leftover turkey. Anyone else have leftover turkey?
Had a graham cracker.
Graham cracker? Okay. I had leftover turkey with stuffing. So.
Have ours tonight.
Okay. Yeah, well, I'm sure we'll be eating leftover turkey for days and days and days. And I know that the at least part of it is going to make its way into soup in a couple weeks probably. So
Well, give it to your wife or kids.
Oh, she's the one, yeah. She's the one who makes the soup.
Didn't somebody define eternity as two people and a turkey?
I like that. All right, here we go. Radio wave characteristics. We are on page now 39 of the PDF. And it looks just like this. Radio wave characteristics. And fortunately, I think we've already covered this. The two components of a radio wave, given that a radio wave is an electromagnetic wave, are electric fields and magnetic fields. Electric and magnetic fields are always at right angles to each other. Remember, you can do it with your right hand. The velocity of a radio wave traveling through free space, everyone?
Speed of light.
Speed of light. What is the approximate speed of light in meters per second?
3 million.
Oh, 300 million.
Oh, sorry.
300 million meters per second. Okay, and now what we're going to do is we're going to write our little formula in the circle or the triangle format for figuring out wavelengths from frequencies and vice versa, you can always go back to 300, F, and lambda. Where F is in megahertz, notice that 300 has a bunch of zeros missing. By the virtue of taking that as megahertz, we've made those zeros go away. So this is the same thing as we do for for Ohm's law. We never don't know 300. If you forget 300, I can't help you. You have to remember that part. So let's say, here we go. We want to figure out the approximate, we want to figure out the length of a wave on, let's say, 50 megahertz, 50.0 megahertz. So what we would do, we don't know the wavelength. We take 300 divided by 50, and what do we get? 6 meters. And lo and behold, if you look at your frequency spectrum chart, which is on another screen, if I can find it, band plan, you will see that the 6 meter band starts at 50.0 megahertz. So there you go. It makes sense. Now, the other thing that's important to note is that we call frequency bands by the number of meters in a lot of cases. Sometimes we'll call 70 centimeters 440, right? Sometimes, but we almost never call 2 meters 146. I don't know why, but virtually every other band is known by the wavelength. And the wavelength is usually approximate. So as an example, we will take the very excellent 15 meter band, which I really, really love. 15 meters is a great band. So we're going to take the same formula, 300, F, and lambda, and we know that F is 15. Sorry, let's get rid of that. We're going to say this is a question mark, and this is 15 meters. All right, so here's our circle. We don't know the frequency. F is equal to 300 divided by 15, which gives us 20 megahertz. Well, let's go back to our frequency spectrum chart and realize that that is not completely correct. That, in fact, we would find that on the 15 meter band, it's actually at 21 megahertz, and it goes up to 21.45, which is actually about 14 meters, but we just call it 15 because it's convenient. Why they couldn't have fixed it and said we're on the 14 meter band, I don't know. They just call it 15. Okay. Carrying forward. Okay. So, given the fact that we have an inverse relationship between frequency and wavelength, wavelength gets shorter as frequency goes up. The same way that light is a really, really, really short wave. Really, really short, very, very high frequency. This has also really significant impacts because the wavelength that we're on determines how big our antenna is going to be. Here's the approximate wavelength in meters as what we call our frequency bands. 2 meters, 15 meters, 10 meters. Now, very importantly, we have these things called bands that we use. And what we're going to do is share this one. Okay, so notice these are split up, and I'm focusing on 3 megahertz, 30 megahertz, and 300 megahertz. The reason I'm focusing on those is because these are the lines of demarcation for the frequency bands we call HF, VHF, and UHF. Right? You have to unfortunately memorize these, but once you memorize them, you'll never forget them again. HF covers 3 to 30, VHF covers 30 to 300, UHF covers 300 to 3000 megahertz, and by changing the units, we change that to 3 gigahertz. So again, HF 3 to 30 megs, VHF 30 to 300, UHF 300 to 3000. I can 100% guarantee that one of those will be on your exam. I can't say which one, but one of them will be on your exam. Okay. RF stands for radio frequency of all types. Okay, now we get on to how radio waves travel. This is where we'd start to have fun. At least, I think it's fun. Hopefully you'll think it's fun too. All right, so propagation modes. We have HF, VHF, and UHF. And we also have microwaves and infrared and light waves and things like that. So given the fact that radio waves are much longer than light waves, we actually find that radio waves, in particular VHF and UHF, they go beyond the visual horizon considerably because the atmosphere reflects radio waves slightly and the Earth doesn't look as curved to those waves as it does to light. UHF signals are rarely heard beyond the radio horizon because it's time to draw the ionosphere, everybody. So what we're going to do is start with where we live, which is on the ground for most of us. So we've got some green and some blue, and I don't have brown, but basically here's the surface of the Earth. And fortunately for us, we are surrounded by this thing called the atmosphere, which extends out to, let's say, 600 miles and maybe even a little bit more. All right. Now, the atmosphere has many different layers. The one we live in is called the troposphere. And above that, we have the stratosphere, which is if you take an airplane flight, the air is getting thinner as you go. And then there's a few other things, like the mesosphere and stuff like that. But what's really important is then we get to something called the ionosphere. And this starts at about 30 to 50 miles up. And this actually has different layers as well. We have something called the D layer, and then we have the E layer, which goes up to about 100 miles. What? So that's like 50 to 100 miles. And then above that, we have two layers called F1 and F2. F1 is the lower of the two. And these areas are so called because they didn't know if there was anything below the D layer, so they started at D, and they only got up as high as F2. Because, figure, why wouldn't they call them F and G? Well, it turns out that at night, the F layers combine into a single F layer. They're slightly different during the day, and at night they combine. All right, so what we are talking about in the case of the ionosphere is the fact that the Earth's atmosphere is largely made up of these two things. So we have nitrogen and oxygen. Together, these make up about 99% of the Earth's atmosphere. Up here in the sky, at about 93 million miles, we have this bright orange ball, which is the sun. And the sun, in addition to generating light and heat, also generates large amounts of X-rays and ultraviolet rays and lots of other different things as well. Well, so as these rays come down to Earth or travel through space and eventually strike the Earth's atmosphere, what happens is that they eventually hit, if we're lucky, you'll eventually hit nitrogen and oxygen molecules. And what happens is that these are basically diatomic molecules, and what will end up happening in some instances is that you will end up with an electron that gets knocked off of the nitrogen molecule, and you'll end up with a nitrogen ion, and the same thing with oxygen. And these are actually happening. This is actually happening at all levels of the atmosphere, and obviously, your most of your rays are going to be, they're going to be eliminated. For instance, if the atmosphere wasn't here, the Earth would be a sterile place. There would be nothing alive down here. So we're very lucky in a lot of ways. But basically what ends up happening is, as a side effect, you end up with a concentration of ionized nitrogen and ionized oxygen at different levels, along with electrons that are floating around. I'll just put some minus signs. Okay. Now, you will remember that we basically have currents, right? And a current is a flow of electrons. Well, so it makes sense that our electromagnetic waves would somehow interact with the electrons that are up there. Well, and in fact, when we send radio waves up into space, we find that they do in fact interact with things that they strike in the atmosphere. So let's just draw a radio wave heading up into space. Okay, so in order to get into space, you'll notice that those radio waves actually have to pass through a lot of different stuff. There's a lot of clear air. There are some positively charged atoms, and there are some electrons floating around. Well, if you take enough electrons floating around at a particular frequency, what will happen is your signal will get up to a certain point and it will go like this. And disappear. So the D layer absorbs up to about, let's say 3 megahertz. Might be a little bit higher depending on the time of day. All right, so the D layer absorbs everything up to about 3 megahertz. The E layer, if something makes it through the D layer, tends to bend or reflect or refract, depending on how you look at it, from, let's say, 0 to 10 megahertz. Frequency dependent. Well, guess what? It gets sent back to Earth. The F layer can actually refract signals from, let's say, 0 up to about 30 megahertz. All right, well, the only problem here is, of course, what happens to the stuff below 3 megahertz during the day? It ends up being trapped by the D layer.
So in essence, it wouldn't go anywhere then.
Have you ever listened to the AM radio in your car or truck or whatever?
Not years, no.
Well, but I mean at any point in time.
Yeah.
Okay, if you listen to AM radio, what happens during the day? What stations do you hear?
All of them.
Well, no, you only hear local stuff.
Yeah,
Yeah.
the close ones.
Okay, how about at night?
You can hear it on the X. You can get it from a long way away.
Yeah, the reason being that the D layer is the densest layer, but it's one of the first to form when the sun comes up and one of the first to disappear when the sun goes away. So it dissipates very quickly right after sunset. So all night long, the D layer basically disappears. Which means that at night, AM radio, which is at roughly 1 megahertz, is no longer absorbed. So at night, you can actually hear your AM radio stations from hundreds or thousands of miles away, whereas during the day, all that energy just gets absorbed and heats the sky. The E layer is essentially dull to us, except that once in a while, you'll get the E layer acting on, once in a while you'll get the E layer acting on signals up to 50 to 200 megahertz. And that's known as sporadic E. and it is like a big party when it happens. The signals get really, really strong and very, very spotty, and then the propagation will completely disappear. So it's great when it happens, and it's completely unplannable. So very unreliable, very unpredictable, but a lot of fun when it happens. Now, what is reliable and predictable is the fact that the F layer is going to form, and during the day, what ends up happening is that the signals that are above 3 megahertz will tend to pass right on through the D layer and the E layer up into the F layer. At which point, what you end up with is a condition where you have ionized particles up here. Again, you've got all your electrons floating around, but the air at 500 miles up is not really very thick. So you really don't have that high a density of electrons floating around. What happens is that areas that are under more sun have more ionization occurring. Areas that are under less sun have less ionization occurring. This changes between day and night. It changes from season to season because the Earth is tilted 23 degrees on its axis, which basically means that because the higher levels of ionization can support higher frequencies being bounced, what you end up with is seasonal and day and night changes to the ionosphere that essentially cause certain bands to be able to propagate back, from long distances, or suddenly, die out and stay dead all night, or stay dead all winter and come back in the summer. We also have this thing called the solar cycle. Every 11 years or thereabout, the sun basically goes from high levels of ionizing radiation to much lower levels, and everywhere in between. So all of these things factor into whether or not we're going to be able to bounce signals at certain frequencies off the ionosphere. During the day, what happens is that, let me share this. The upper reaches, so during the daytime, 20 meters and up to 10 meters, will typically be propagated. At night, those bands will start to fade, and you'll switch to 20, 30, 40, 80, 160 being alive. And this happens day and night, season to season, and top of the peak of the sunspot cycle versus the bottom of the sunspot cycle. So an interesting thing to look at is that there is a mode that we're going to talk about called FT8, and there's a program on the web called PSK Reporter. And so, all right. So, oh wow, 10 meters is really open right now. Okay, so looking from the northwest, we're going to look at all bands. These are all automated signal reports that have been taken in the last 15 minutes. Let's see what we've got. Come on. Come on, waiting for this thing to liven up. Ah, here we go. Okay. So the hot pink color, those are the 10 meter band, which is roughly 30 megahertz. And then you've got other colors. So like the green, this I believe is, let's see, 30 meters. Yeah. Okay. So this is 14 megahertz. These yellowish orange dots. The green ones are 10 megahertz. And notice that even though the path is largely in night, they still exist. We can still talk into Europe. Now, also notice that we can also talk across into the southern hemisphere. There are people talking to Japan. Now, what would be interesting is to see what it all looks like from Europe. So we're going to pull up a map from Europe, and we will see that it's been nighttime there for a while. And hopefully this comes up and is interesting to us. There we go. Okay, so notice the colors are very, very different. We've got a lot more green. Those are 10 megahertz. We've got a lot more blue to Japan. Those are 7 megahertz. These dark pink ones, those are 3.5 megahertz. And these closer in ones, these are basically just above the AM radio band. So that's at 1.6, that's at 1.8 megahertz, which is the 160 meter band. So those bands are dead as a rock during the day. And notice that they're the only things that give propagation at night. So propagation, HF propagation in particular, is a really interesting thing. There are people who spend their entire careers studying it. Okay, so why are UHF simplex UHF signals rarely heard beyond the radio horizon? They're not propagated by the atmosphere. They typically pass right on through. VHF signals sometimes vary greatly when the antenna is moved only a couple of feet. All right, so what we're gonna do right here is talk about a little bit of geometry. What is, if we have our 300, F, and lambda, what is the approximate wavelength at 146 megahertz? Okay, well, 300 divided by 146 is about 2 meters. We call that actually the 2 meter band. So what would you expect the wavelength to be on the 2 meter band? This is not a trick question. I hope it's 2 meters.
You would think.
You would think. Okay, so if it's 2 meters, how big is that in feet?
6.5.
About 6.5 feet. All right, now what's cool about this is that when you're dealing with light, the light waves are basically, minuscule. They're microscopic. We can't see spaces. But when we're talking about radio and we're talking about wavelengths that are actually measurable, like with a tape measure, we can actually do stuff with them. So what we can do is we can draw this wave. How long is that wave in space? About 6.5 feet.
2 meters?
Yeah, about 6.5 feet. If I draw another one, that's about another 6.5 feet. Okay, now what we're going to do is we're going to go from point A to point B. And here's the end. All right, so we've covered 1, 2, 3, 4, 5 waves, okay? Now, we are going to do a little magic here. This was a straight line, and we're going to realize that the shortest and most functional distance between 2 points is a straight line, but it might not actually be the only one that's working. It might also be that somebody has a truck parked over here, like a semi-truck. And that semi-truck might provide a reflective surface for a radio wave that could actually do this. Okay, so part of that radio wave gets bounced off the truck and ends up at the end point. Start drawing waves there. 1, 2, 3, 4, 5. Uh-oh. How long is that?
A wavelength and a half.
I have no idea. But what I do know is that if we start drawing these waves and we start looking at the wave that arrives at the end point and we draw them at the same, based on the end point, it might look like this. And what happens if you add those two together?
Cancel out.
Mm-hmm. Exactly, you get cancellation. This would be called destructive interference, where they actually arrive phase shifted by, in this case, 180 degrees. This is basically how noise canceling headphones work, by creating another signal out of phase with the first one. There's no guarantee that it's going to be the same amplitude, but it is going to adversely impact things. Now, what we do have is the ability to, depending on what we're doing, move. we have the ability to move. So let's say we move a little bit and we make it so that this signal goes this way. And this signal now has to take an even longer path. And it turns out that our new wave looks like this. What do we have then?
Stronger signal.
We have constructive interference. So by moving just a little bit, because we're talking about macroscopic waves lengths, we can actually go from an area of constructive interference to destructive interference or vice versa. For those of you who, as soon as you get on 2 meters, happen to have a 2-meter radio, if you're listening to a distant station like a repeater, what you'll notice is that there are certain spots in your room, unless you're really close to the repeater, where a signal is really loud, and at certain spots in the room where it's really scratchy. And if you move around the room, you'll find a nice, you'll find a nice strong spot, and you just put the radio down there and listen. And that's literally because you're moving from an area of destructive to an area of constructive interference, and using something called multipath propagation to your benefit. Okay, and that is known as multipath. Okay, the next, picket fencing. That is basically rapidly changing multipath because you're in a moving car. And what you'll hear is you're rapidly going from an area of constructive to destructive interference, and it'll literally sound to somebody on the other end like you're fading in and out really, really fast. And that's known as picket fencing, like you're trying to talk through a picket fence. If you have multipath propagation, we can also send data over the radio. If you were sending data over the radio, the same way that your interference listening to audio will sound worse, your error rates on your data will likely go up as well. If you're using a directional antenna, you might be able to intentionally bounce a signal off of a nearby building in order to hit the repeater, whereas you might not have a direct sight. So it might actually be that if you have a beam antenna, you point it off that, off that reflective glass building on the corner, and you can actually get to the repeater better than you could directly. What can allow radio signals to travel beyond obstructions between receiving and transmitting stations? This actually comes down to a part of physics where we start looking at radio waves using something called the wave-particle duality. We basically have a sharp mountaintop, and what happens is that a wave that hits the mountaintop, believe it or not, will actually send some of its signal this way and some of its signal this way. It will actually diffract. Even though you'd think it would just get absorbed here, if it's a sharp enough edge, it'll actually turn into kind of like if you ever see a ripple in a pond, it hits for instance, it hits a log that's sticking out of the pond, it'll actually sort of like bend around it. This is a very similar thing. So it's entirely possible that somebody here on the left side could actually talk to somebody on the right side just by using this thing called knife edge diffraction off of a sharp mountaintop. It's not the most reliable thing in the world, but it sometimes does work. Okay. A condition that could impede the transmission of VHF and microwave signals is heavy vegetation. So if everybody thinks about your microwave oven, essentially your microwave oven is a 2.4 gigahertz radio transmitter operating at 1,000 watts inside a box. So what is the one thing that can get in the way of your microwave oven transmitting all that power? What's the one thing you can put in your microwave oven that absorbs energy really well?
Water.
Water.
Metal.
Well, metal will cause a short circuit. But water absorbs energy really well at that frequency. Water is a great absorber at microwave frequencies. So if you happen to have, let's say, satellite TV or satellite radio or something like that, you may have noticed that when it gets rainy, it doesn't work so great sometimes. That's because the atmosphere is getting in the way. Water absorbs microwaves. And trees and in particular leaves tend to contain a lot of water. So during the summer, UHF and microwave signals can get absorbed by leaves quite easily. Okay, we're now on to antenna polarization. So the most commonly thought of thing that we deal with polarization is polarizing sunglasses. And a lot of people have had experience driving with polarized sunglasses and really like them. The reason being that if we put the sun up here, the sun generates energy with the electric field going this way, and some of it's going this way, and some of it's going this way, and some of it's going this way. The electric field basically is the direction of the field as it oscillates back and forth. Some of it's going into the page, some of it's coming out of the page, all different magnitudes. This is known as random polarization. As soon as it hits a reflective surface, like the hood of a car, the hood of a car can better reflect certain polarizations than others, which can cause a considerable amount of glare. Well, so what you do is you basically have your sunglasses made of a material where all of these, if you want to think of it, slits in the sunglass material is aligned so that it only allows light to come through with the electric field that's going up and down instead of horizontally. So when that energy comes in with the electric field going side to side, and it tries to get through slits that are oriented just up and down, what ends up happening is that none of it makes it through. This is a practical application of polarization. Another way that we use polarization is with liquid crystal displays, where we have light that is polarized, and depending on whether or not crystals are turned on or not, that changes the polarization of the light, which will make the segment appear black. So if we are talking about polarization, polarization is the the orientation of the electric field. Electric field defines polarization. So this wave right here, if it had an electric field that was going horizontally, that would be known as a horizontally polarized wave. If the electric field were going up and down, that would be a vertically polarized wave. If the wave were continually changing so that it was like this, and the next time you looked it was like this, and the next time it was like this, and it's rotating, that's known as a circularly polarized wave. For the most part, we don't deal with circular polarization as far as this class goes. That's typically something that you may get into if you do satellite communications. For the purposes of this class, we're talking about horizontal and vertical. Now, here's an important thing to note, that if you have a wave that is horizontally polarized, the antenna that made it is typically oriented like that, if this is the ground. The antenna that makes a horizontally polarized wave is parallel to the ground. The antenna that makes a vertically polarized wave is perpendicular to the ground. So that is polarization in a nutshell. If the polarizations of two antennas don't match, let's say that we have somebody operating with vertical and somebody operating with horizontal, and their line of sight to each other, they will basically not hear each other at all. Maybe slightly, but it'll be greatly reduced effectiveness. Okay, so for long distance communications on VHF and UHF, we will typically use polarization that is horizontal. The reason being that if I were to make an antenna that's horizontal, and here's my directors, it's horizontal to the ground, we basically end up with ground reflection that works really well. So you get direct path as well as ground reflections. So for CW and single sideband, these are known as weak signal modes and some digital modes as well. We typically use horizontal polarization. For FM, talking through repeaters, well, one thing that's important to note about this is that if I were to look at this antenna and draw it from above, it would look like this. So where would most of my signal be pointed? What direction? That would be that way, with only a tiny little bit coming off the back. So this is a very directional antenna. Now, let's say you wanted to talk to just, somebody in general in a place where you didn't know. This would not be a very good start, would it? Because what if they're over here? So for that purpose, what I'm going to draw is the roof of a car. I'm going to put an antenna right here in the middle of the roof of the car. So we're looking down on the roof. So for the most part, this antenna, we're looking at the end of the antenna looking down onto the roof. Which direction is going to be favored most regarding the pattern that we send out by looking at this? What do you think?
I think it goes straight up.
Nothing goes straight up. Okay, here's an important thing. I'm going to draw an antenna side view. This antenna, so this is, we're looking at it from the side, puts out a signal in this direction and a signal in this direction. And some of it comes toward us and some of it goes away. So if I could draw a little bit better, that would look like a donut. So actually none of the signal goes straight up and none of it goes straight down. It's all perpendicular. It's like a figure 8 perpendicular to the antenna.
Oh, I see.
Okay, so now let me draw that again. We're going to draw the top of our car. And here's the antenna right in the center. What directions are going to be best?
Well, it's going to go in all directions except up and down.
Yep, go all directions except up and down. So how much gain is there going to be in any one direction? Essentially none. But it's going to be almost omnidirectional. Right? Well, this has some very significant benefits. Let's say that you're trying to talk to somebody somewhere and you don't know where they are. You're going to be sending out signals in all directions, right? If somebody's over here or over here or over here, you're going to hear them equally well. Similarly, if we were to take this antenna and instead of putting it on the roof of your car, we're going to put this on a tower, on a hilltop. Right? We're looking straight down on it. Which directions are going to be favored from there? And the answer is none, right? It's going to work equally well in all directions. This is exactly what you want. If you think about it, let's say that your goal is that I'm going to build a repeater station. A repeater station is supposed to receive signals from everywhere at a really high spot and take them and retransmit them to everyone who wants to listen. Which means that a perfectly omnidirectional antenna, meaning it receives equally well in all directions with no, essentially, minimal preference of any one direction, is going to be exactly what you're looking for. This is the basic reason that people use vertical antennas, because they don't have a preference in one direction versus another. Okay, let's see.
Just
Okay.
this little quick just if I can interject
Yeah,
here.
sure.
I guess you have to be aware if you have a vertical antenna, you have to be aware of conducting elements that are nearby because that could change the performance of your antenna. Is that a correct assumption?
I mean, okay. So here's the thing. In every antenna is tested in what we call an anechoic chamber, which is essentially, the walls extend forever. Your signal never bounces back. This is why antenna modeling is so much fun. Like we have these incredible high power tools available just to the general community, right? They were actually developed for Lawrence Livermore National Laboratories for modeling of antennas using some very heavy, high powered computer code. Because we all have computers now that are so incredibly powerful, we basically have the ability to run almost like a supercomputer on our desktop and do antenna modeling. And what we find is you can model all kinds of different parameters. And you know what you can't model? You can't model the fact that there are trees over there. You can't model the fact that, your house is over here and there's a car and there's a car in front of your house and a truck just drove down the street. So
and you have metal gutters.
And you have metal gutters. Well, actually, you can model those. You can actually include them if you know that they're going to be there. But, what it really does is it really gives you a starting point, and then from there, you control what you can and you just sort of guess on the rest. Which is why, antennas to me are some of the most fun that there is to do in ham radio, because you start with something that you think should work. I mean, a couple of years ago, I built a 2-element driven vertical array for the 20-meter band. Didn't work worth a crap. I still have no idea why. I did all the math. I modeled it. It should have worked. But I also built it on my deck. I'm not really sure what happened. I could try to figure it out, but it just never worked.
Did you try putting it out in your yard?
I never even did. I gave up at that point. I was like, okay, I need to get this working by today because it was for field day, and it didn't work. I'm like, all right, I better just, go with something else. So I started cutting up wire and ended up with something else. And then I have antennas that I've put up that, I can't really explain why they work. I just put them up as high in the trees as I could and fed them power, and they seem to work. So I'm like, okay, I mean, I've gone through and done some modeling, but there's no obvious reason why it should work any better than anything else, but they seem to. Antennas are sort of like, 50% science and 50% magic.
Question.
Yeah.
I live on the backside of a hill surrounded by trees. Am I best off getting like a Yagi or a dish and pointing it at the nearest repeater?
Depends. I mean, when you say the backside of a hill, I mean, what frequencies are we talking about? Are we talking about well, where do you live, first of all?
Winchester Bay over on the coast of Oregon.
Okay. So what I would recommend doing is I'm going to share a site right here that I use. There we go. Not that one. Radio Mobile Online. Let's see how fast they load today. There we go. Radio Mobile Online. Okay, this is something that somebody in Quebec put together. So it's written in kind of like Franglish. But essentially what this is... Oh, stop. didn't like my password. I wonder what my password even is. If this doesn't work, I'm going to give up. Nope. Okay. But basically what this is you create an account, and notice it's called towercoverage.com, and it uses Google Maps with relief maps. You indicate how much power you're running, where you're running it from, and essentially it does ray tracing for your entire area. And it goes around and around and around and around 360 degrees every like however much, like whether you want like every degree out to, infinity, and looks to see what the signal strength is that's being helped or hurt by everything in between you and a point. And what it does is it gives you a coverage map from wherever you are to all these other places. And if it turns out that one of those green spots is a repeater, you can also do one for the repeater site if you know the details. You can see what the coverage map is for the repeater and when you're in it, or if you're in it, or how high your antenna has to be to make it work. So really, really powerful tool, which I can't seem to get into.
But a directional antenna tends to work best for that situation.
It depends. I mean, a vertical might be fine, but you can basically play with the units of gain and see whether or not you need a vertical or whether or not you need a beam to get into it.
Thank you.
And again, that's Radio Mobile Online. Very cool tool. Okay. Let's see. What else? Where are we next? Let me go back and share this because I lost my train of thought a little bit. Okay, here we go. Interesting propagation phenomena. Which of the following types of propagation is most commonly associated with occasional strong signals on 10, 6, and 2 meters? Okay, that would again be called the sporadic E. Sporadic E because it's sporadic. Notice occasional, sporadic. And that's when the E layer basically, for whatever reason, builds up very high levels of ionization and can refract back or reflect back signals on some bands that typically are never used for over the horizon. Once in a while, 10 meters will come alive. 6 meters, it takes a lot of sunspots. It takes a lot of solar radiation to make enough ionization to do F layer propagation on the 6 meter band. And because the E layer is lower than the F layer might be good for 2,500 miles on one bounce. The E layer is good for about 1,000 miles. A characteristic of VHF signals received via auroral backscatter. So imagine that you're basically looking at into the aurora. And I know somebody had a picture of the aurora as their background. What does the aurora look like? Mike, what does it look like?
You can see, yeah, I've seen it actually look like that. It looks like a big shifting curtain of colors in the sky. Sometimes it's green, sometimes it's red. It's spectacular.
And more importantly, too, it's always moving, right? Now, imagine you're trying to speak into and get reflections out of a moving curtain. And you're trying to basically bounce signals out of a moving curtain. That's what aurora backscatter sounds like. It's all distorted. It's very interesting sounding. And it's one of those, I've never been able to do it. I know people who've recorded it. I know people who've done it. Basically, we look for ion trails, electrons floating around to bounce signals off of. 6 meter band is really good for auroral propagation. The 6 meter band is also good for meteor scatter. When a meteor storm happens, you end up with like a whole bunch of shooting stars in the sky. Every time one of those little rocks burns up, it generates a lot of heat. That heat causes an ionized plasma to exist in the form of a trail. If 2 stations are aiming at the same point, you can bounce a signal off of that. And that's known as meteor scatter.
Scott, is there a scientific reason why the 6 meter band is particularly good at that kind of scattering?
You
Is
know,
it-
I don't know, but I
Okay.
know somebody I can ask. His name is Nathaniel Frizzell, and he runs an organization. He's a professor of physics and electrical engineering at University of Scranton.
Okay.
And he's also W2 NAF, and he runs an organization called HamSci, which is the
Okay.
basically ham radio science citizens organization or institute.
Huh.
And he basically collects from other hams who are interested all kinds of propagation information and does scientific studies of the ionosphere based on all the data that people collect.
Cool.
It's very cool.
Yeah, since it's between 2 and 10,
Yeah.
it doesn't seem like it's because it's big
No.
or because it's small.
You know, and it could just honestly be due to, the densities. It might be that the plasma density at that level caused by a meteor isn't heavy
Okay.
enough to. I mean, obviously 2 meters would work better. 70 centimeters would work better than that because you can focus your beam tighter.
Mhm.
But at the same time, if it requires higher and higher levels of plasma to be able to bounce the signal down, it might just pass right on through at that point. So it might be that, 6 meters is your perfect intersection of
Right.
a tight beam and a heavy enough plasma generated for that to
Okay.
work.
Thank you.
Yeah. What type of propagation is responsible for allowing over-the-horizon VHF and UHF communications to about 300 miles? That's known as tropoducting. Has anyone ever been driving down the road and noticed what looks like a mirage in front of their car about a quarter mile down the road?
Yeah,
What causes that?
beats me.
Yeah.
Differences in air density.
Differences in air density causing differences in refractive indices of the air. So what you end up with is a hot road surface where you have heated air, and then above that you have cooler air, like this, and you are basically looking at the sky up here. And what happens is that you are looking into this area, and basically you end up with a duct between which is hot and cold layers, which form areas of different refractive indices. Remember I said that light travels in a straight line, right? It takes the shortest path between 2 points. But sometimes what ends up happening is that if you have ever looked into a glass that is half full of water and you put a spoon in it and the spoon gets bent, your spoon is not actually bent. But what's happening is that the light travels at different speeds through there. So the light that comes down here can hit this layer and actually curve. And if it works that way, you can actually end up with a duct that forms in that layer.
So
And-
if you're driving down the highway and you see what seems to be a puddle of water or even a lake, that's what this is?
It's a reflection of the sky.
Okay.
It's basically what we would think of as a mirage, and it's caused by temperature inversions in the air.
Okay.
Now, the thing about radio is that the wavelengths are a lot bigger than light, right? So the inversions are typically a lot bigger. So let's draw what looks like land, and then let's put the ocean. So what'll happen is you basically end up with these temperature inversions where you have warm, and then maybe you get a cool layer, and then a warm layer, and what'll happen is you might have another cool layer above that, and your signals might actually be able to go like this. Like, whoop, wait a minute, and then exit somewhere. And this is known as a duct. And the best one I've ever personally listened to was when I was in college, and I lived on the 9th floor of my dorm. And one Sunday morning in May, I turned on the TV and was flipping around the radio, flipping around the UHF radios, the UHF TV stations, 700, 800 megahertz. And I was actually able to see TV signals from Connecticut, from Maryland. That's 300 miles. Just using rabbit ear antenna. Like, well, that's weird. So I hopped on the radio and got on 2 meters and was able to work into repeaters up in Connecticut using 5 watts and a handheld radio. A distance of 300 miles by using that very same duct. So it was very cool.
How long did it last?
Another thing that can happen is that these will form very readily in the summer months over the Pacific, in particular between Hawaii and California. And you typically have trouble getting signals up into the duct, but if you go up on a mountaintop on both ends, you're basically very close to the duct. And if you shoot signals up into the ducting area, you can get signals on VHF and UHF that go all the way from Hawaii to California over the ocean. And they've done this at up into the gigahertz range, microwaves, which is really kind of mind-boggling because that's supposed to be line of sight. Okay, let's see. Okay, so temperature inversions. What weather condition might decrease range at microwave frequencies? That would be rain. Water absorbed microwaves. And on the 10 meter and 6 meter bands, those are low enough in frequency that there is essentially no effect from fog and rain. Okay, HF propagation. This is the around the world propagation. HF and VHF signals are bent by the ionosphere. HF communication compared to VHF and UHF. Long distance communication is very, very common on HF, whereas it's very uncommon on VHF and UHF. The 6 and 10 meter bands, when you get a sunspot peak, can actually be refracted by the F region. Again, when it's not, essentially, we're looking for a lot of ionizing radiation coming out of the sun. So during the sunspot peak, that's what happens. Okay, which is generally the best time for long distance 10 meter propagation via the F region. So this is actually a year ago. When I did this class, I would have said wait a year. As of right now, this is alive right now. We're getting to a good spot in the sunspot cycle, and the 10 meter band is good and open to big chunks of the world, as we saw on that map. Those were those pink spots. So all over South America from North America. And the cool thing is that it takes almost no power, and because the 10 meter band is the the shortest wavelength HF band, your antennas are nice and small too. So you can take an 8-foot long cut down CB whip, stick it on your car, and talk to people 10,000 miles away. More likely, 1,000 or 2. But if the conditions are right, when we're at the top of the cycle, it works. It's very easy to do. And as technician class licensees, you can actually use 10 meters. So,
Question.
Yeah.
Does that rework off the repeaters too?
Nope.
Just has to be direct to your radio only?
Mm-hmm. Yeah, all these things, repeaters are just FM and usually VHF, UHF. But one of the big things that we like doing on HF is DXing. It's working very long range communications with almost no power, sometimes a lot of power. But my longest contact that I ever worked was myself. Anybody want to ask why?
Seriously, it went all the way around the world?
It went all the way around the world. I was in college. I was pointed along what's known as the gray line. Excuse me. There we go. The gray line is the area between daytime and nighttime. And you typically get some very interesting propagation right along that line. And of course, it goes all the way around the planet, because half of the Earth is in sunlight and half is in darkness. So if you aim right along the gray line, you can get some very interesting propagation effects. One of which was, if you're running enough power, I was running about 100 watts, and I had a 6-element beam on the roof of the dining hall at the University of Maryland on top of a hill. And I was pointed right along the day-night terminator to Japan. As soon as I let go of the key, I heard my own signal. Like, no. I did it again just to prove it. It had gone, all the way around the planet.
That's pretty cool.
Yeah. I've never heard it since. But it was pretty amazing. And it was, you know what? You think of radio and light and electromagnetics and the speed of light being infinite. This proves to you that it's not infinite. It took about 140 milliseconds to get all the way around the planet.
That's still pretty fast.
It is pretty fast, but it's not zero. Which of the following? Oh, here we go. Likely cause of irregular fading of signals propagated by the ionosphere. Okay, well, a lot of people will think of the ionosphere as a reflective mirror, but in effect, it's not a mirror, like a smooth mirror. It's all bumpy and rough. So you get some signals that have to travel a little bit further than others. And for instance, I can tell when I'm on the air which signals are coming over the pole and which are not.
How can you tell the difference?
Because signals that come over the pole have a warble to them. They've traveled. They literally sound like this. They talk, fading in and out really, really fast. Okay. And then on top of that, all signals, depending on how they're traveling, can have a fade that, like every 15 seconds they'll fade out, start to come back, and then they'll be good for 30 seconds and then start to fade away.
Got it.
And you never know if they're really going to come back. Maybe that was the last time, because you're basically relying on something that's, 500 miles up and you have no control over it. It's actually a lot of fun. Okay, let's see. So random combining of signals arriving via different paths because the ionosphere is not a smooth reflecting mirror. Signals propagated by the ionosphere are elliptically polarized. That means that they have vertical and horizontal and every other combination of polarization built into them, which basically means you build your antenna and you either receive the vertical or the horizontal and you don't care because they both work. All right, so we're going to move to antennas and feed lines. Do we have any questions before we go on? Speak now or forever hold your something. Okay, here we go. My most favorite part. Antennas and feed lines. All right, because this is something that we can actually draw. Okay, this is a half-wave dipole. This is a half wave long. Each part of the antenna is a fourth of a wave long. Typically fed power in the center with part of it going left and part of it going right. So a simple dipole oriented parallel to the Earth's surface is a horizontally polarized antenna because the wire is going horizontal. The electric field will be traveling in the horizontal direction. A dipole radiates energy broadside to the antenna. So if I have this antenna that's over the ground, some of the energy will be coming right toward me, some of it will be going away. Unfortunately, where will some of the other power be going? Remember, it goes
used up with inefficiency.
Well, yeah, but I mean, a dipole is actually really efficient. But where will some of the power be going? Some of it's coming toward me, some of it's going away from me, but it's going in all directions perpendicular to the wire. What does that include? You have to think in 3 dimensions. Some of it's going straight into the ground. And where's some of it going?
Straight into the sky.
Straight into the sky. The stuff that's going straight up doesn't do me a whole lot of good. So, but for the most part, a dipole is a very, very good antenna. It's a very good starter antenna, and it is directional, right? There's virtually no radiation that comes off the ends. of the wire. It's almost all perpendicular to it. Okay, so that's a dipole antenna, which is a fundamental electrical antenna. All right, so a dipole radiates the strongest signal, what's known as broadside to the antenna, which basically means perpendicular. Okay, a dipole is also a great antenna because it's a very simple and easy to build antenna. Not only is it easy to build, it actually makes sense. So I'm going to make this half-wave dipole. All right, so I'm going to pick a 6-meter dipole. So we're going to use our formula. Actually, we don't even really need to use our formula. So it turns out that it's the 6-meter band. We're gonna look at it anyway, just because this is the right thing to do. So we're going to look at our frequency chart and see that the 6-meter band covers what frequencies? Starts at 50 and goes up to 54. So we will pick 50 megahertz just for the heck of it, because I want to operate on the low end of the band because it's more fun for me. So we're going to pick 50 megahertz. All right, that's the 6-meter band. Okay, 300 F lambda. Whoop. Okay, so 50 megahertz. Lambda is 300 divided by 50 is 6 meters. Yay, it's the right thing. We did it right. Okay. Now, what we're going to do is say, how long is our half wave, I just gave you a hint, dipole antenna?
3 meters.
Right? Okay, so it's a half wave long. So our antenna was 6.00 meters. A half wave antenna is 3.00 meters. Okay. Now, here's the one thing you have to remember. You basically have to take about 95% of whatever you got. The reason being that, remember I mentioned that when you build an antenna, it's not always what you think it's going to be. It doesn't always work. That's a key to making it work. Because in the real world, if you look at an idealized piece of wire, what is the resistance of a perfect piece of wire? How many ohms of resistance will it have?
0.
0, yeah. And also, what is the diameter of a perfect piece of wire? Ideally, nothing, right?
0.
Yeah. And it's copper and doesn't have any insulation, but when you go and actually get a piece of wire, it might have insulation on it. And it also has a finite length and it has a finite diameter, and that means that it has something called self-inductance, and it also has self-capacitance. So basically there's some other things at play. So what we do is we take account of all that, and we take our antenna wire and we take whatever length we got and we shorten it by 5%. So this ends up being 2.85 meters. And then we have 39.36 inches per meter. And we get 2.85 times, oh, come on, 39. I get 112 inches. And in fact, that's what the book says, that our antenna should be 112 inches long. And that's how that works. And that is, now, here's another good rule of thumb. If the book says, and your calculations say your antenna should be 112 inches, how long should you make it?
95% of that?
No, that's including the 95%.
Oh, that's including 95?
Yeah. How long should you actually make it?
112.
No, I wouldn't start there.
Make it longer because you can always cut. It's harder to add.
Yeah, I'd go about 115 because I can always trim it. When I start doing my tests, I can always cut it down. If you made it too short, you got to start over. because the one thing you want is antenna wire that's still flexible. And as soon as you solder something to it, it's not really flexible anymore, and that'll be where it breaks. So always start with an antenna that's too long and shorten the thing, and not the other way around. Okay, how do you make the frequency of an antenna go up? How do you make the resonant frequency of an antenna go up? What do you do to it?
Shorten it.
You shorten it, just like a musical instrument. You tune your flute, you shorten the tube so the tone goes up. Okay, so how do you make the frequency lower?
Lengthen it.
You lengthen it. Now,
Or
one
over,
thing
yeah.
one thing you can do is I have an antenna that looks like this. And this has a lead that starts here and allows you to basically short out pieces of it on purpose. This is it's a center-loaded vertical antenna. So essentially, by changing the position of this tap, I can make the antenna longer or shorter based on what I need. And you can actually build an antenna that you can do that. You can have a multi-frequency antenna for that.
But really, it just makes it appear shorter or longer, doesn't it? Because it
No.
changes the impedance.
No,
It actually makes
it
it shorter or
does.
longer.
It actually makes
Yeah,
it
okay.
shorter and longer. Yeah, it changes the length of the antenna. It doesn't change the physical length, but it doesn't change the physical length much, but it changes the electrical length.
Question.
Yeah.
How much compensation can you do with an antenna tuner?
Depends on the tuner. Depends on the frequency you're operating on. As far as compensation, you mean like if you have a really bad mismatch?
Yeah.
A built-in one, typically 3-to-1, a 3-to-1 impedance mismatch. If it's an external, 10-to-1, 12-to-1, some are up to 20-to-1. Depends on the quality of the device. Okay, here we go. The second most important antenna is something called a quarter wave vertical. Anyone want to guess how long a quarter wave vertical is?
A quarter of a wavelength.
A quarter of a wave. Excellent answer. Okay, so this is a quarter wave. So this is a quarter wave long, and we're going to pick it for 146 megahertz. All right, so somebody tell me what to do. I want somebody to direct me through it. What's the first thing we do?
I would, from your frequency, figure out your wavelength and then
300,
take a quarter
F-
of that.
Yep, okay, 300 F lambda. So 300, 146 in lambda. We get lambda is 2.05 meters. Okay, and we take a quarter of that, right? Which is about 0.51 meters. Okay, so that's a quarter wavelength. And what do? Got to shorten it.
Is it still 95% for the quarter
Yep.
wavelength as well?
It's for basically any dipolar quarter wave. Because I will explain this in a minute. A quarter wave is actually just a half of a dipole. So 95% is about 0.48 meters, which is roughly 19.5 inches long. So there you go. 19-inch antenna. Fits on a car quite nicely. Okay, so now here we go with the the really interesting part. We're going to make a ground plane. This is the roof of your car, for instance. A ground plane is a perfectly conductive surface. So we have one wire coming here, and we have the shield of our cable going here to a plate. Now, this actually works without help from drilling a hole. You can actually use a magnetic mount. Somebody explain to me why this works if your magnetic mount looks like this. If it's got a metal plate right here.
Would that be that it's grounded?
It's not grounded.
Okay.
What do you notice about this plate? What do you notice about? Sorry, go ahead.
Is it insulated?
It is insulated from ground. It's insulated from the roof.
It's also parallel with the roof.
Yep. What does that look like? We just talked about it this morning.
A capacitor?
That's a capacitor. And what do we know about a capacitor for very high frequencies? It looks like a
Short circuit.
short circuit, which basically means that the other side of the antenna cable is essentially shorted through capacitance to the roof of your car. Pretty cool, right? Even though there's no physical connection. Okay. Here we go. Now, we've drawn the top part of the antenna. So, we know, unfortunately, that there is no such thing as just a simple quarter wave antenna. If I drew an antenna that looked like this and made it a quarter wave long, that would be a horrible antenna, right? If I drew a dipole, that's a nice balanced antenna. A quarter wave antenna, not so good. So what we end up having to do is put this over a ground plane. Now, this is a bit of a thought experiment, which I like to bring up just to make people think, to say that if I am way out here and I look at the top of the antenna, right, I will see the top of the antenna. Will or will I not also see this? If this is a perfectly reflective surface. Yeah? Okay. Well, who is to say that I, as the observer, have some idea that that's a perfectly reflective surface? If nobody told me there was a perfectly reflective surface there, what would I think?
You would think the antenna was twice as long as it actually was.
And it was a full half-wave dipole, right? Because I'd see this part right here. And I'd also see this part. And for every part above, I would see an equal part below. As far as I'm concerned, from the distance, that is a perfect half-wave dipole. So this is basically evidence for the fact that what you really have is that it's indistinguishable from that, which is an antenna over a ground plane. Essentially, it has a radiation characteristic that is actually a little bit better than a dipole because it's above the horizon instead of below. And whereas the feed point impedance of a dipole is 72 ohms, because it's only half of an antenna, this is actually 36 ohms, which actually it turns out can be fed pretty well using plain old 50 ohm cable, which is something that we're going to get to. So that is a quarter wave antenna. So those are the two most important antennas that there are. And you can build them yourself, which is great. You know, I tell people, you know, a really mediocre radio with a great antenna is a great performer. A really great, you know, $4,000 radio with a crappy antenna is a crappy performer. So the biggest bang for your buck comes out of your antenna system because it works on transmit and receive. Okay, next, antenna loading. Okay.
So sorry, if I can, just one quick question about the antenna. I don't want to go too far afield, but I was reading through some antenna theory stuff last week, just trying to get up to speed on all this. And I think I remember reading something about the reason you make it shorter than the exact fractional multiple of a wavelength is something about the voltages at the end not being zero. Is that a thing, or did I get that wrong?
Okay. Well, all right. So here's something that I often draw, but I wasn't going to, but now I'm going to. Okay. I'm going to ask this question. What is the current at the ends of the wire?
Well, isn't it zero?
It has to be 0, exactly. So if I were to draw the current at the end, it has to be 0. Well, if I put a wave into this and it's a half wave long, there's a half a wave. Here's the other half waves extending into space. Where do I find my peak? Where's the highest point?
Right in the middle.
Right in the middle. That's my feed point. Okay, so I'm going to now draw the approximate voltage waveform. Not exact, but it's going to be out of phase with the current. Well, so if my current is high at the feed point and my voltage is low, it's not 0, but low, and I have Z impedance is equal to E equals IZ, and then Z is equal to E divided by I. Empirically, what I have is something that is high, something that is low divided by something that is high. And what is something low divided by something high?
Something even lower.
That's low, right? So that's a low feed point impedance. Now, what if I were to instead move my feed point so that it was like way over here? What is my current? My current is low, and my voltage is
It's relatively high.
relatively high. So if I do my Z again, Z is equal to E over I. I get high over low, which is high. So this over here, this could be on the order of 50 ohms, 50 to 70 ohms. And this one on the left could be on the order of 2,000 ohms. Which one can I readily get cable for a direct connection?
About 50 ohms.
Yeah, so what we're going to talk about very soon is feed lines and characteristic impedance of feed lines. This right here, 2,000 ohm cable, it doesn't really exist. But 50 to 70 ohm cable, you can get that anywhere. So really easy to feed. So is this antenna a winner or not? Trick question. It's a trick question.
Well, I guess if you can match the impedance, it's fine.
Yeah, exactly. And in fact, it's very, very, very popular. The reason it's popular is because we can build one of these. You ready? What does that look like, everyone?
A transformer.
That's a transformer. Well, a transformer, as it turns out, can transform voltages and currents. But let's say that if V equals NV and I is equal to I divided by N, let's use N in 1 and 2. Well, it turns out that Z is equal to Z over N squared. So guess what? The turns, the turns ratio in there, the square of the turns ratio changes the impedance too. So you can use it as an impedance transformer, not just a voltage and current transformer. And what's cool about that is that if I have a ratio of 49 to 1, and I have 2,000 ohms up here, I end up with roughly 42 ohms here. And guess what? I can feed that with a piece of cable. And this is actually known as an N-fed half-wave antenna. Very popular these days because you only have to have one real good anchor point. You can put the other end pretty much anywhere. Whereas with a dipole, you really need 3. You need 1 for the center and 2 for the ends. Still a half-wave antenna, but it's fed differently.
Very cool. Thank you.
Yep. Moving on. Okay, what defines antenna loading? All right, so I started to draw that, but here we go. Here's a full-size antenna. Now, we said for 2 meters, a quarter wave antenna is 19 inches long. Now, I'm also going to show you a quarter wave antenna, which is on my radio right here, which looks like this, which is 7 inches long. This is actually a quarter wave antenna, and this is a quarter wave antenna. How in the world did that work?
Is it the thickness of your antenna?
Nope. Inside here, you basically have all the wire is coiled up inside. So electrically, it is the proper length, but physically, it's shortened. Now, part of the problem is that the part of an antenna that radiates effectively, is the part that's carrying current. The amount of energy that's transmitted well is basically transmitted by the peak currents. So if I were to draw and say, okay, well, I know I have 0 current at the end. It's a quarter wave long. So here's a quarter wave. Its peak at the very bottom of the antenna. But then I did something horrible. I take the bottom of my antenna wire and coiled it all up so that I only had a little stub sticking up. I would just basically have this little bit of current right there, and the rest of it would just kind of all be mashed together and not doing a whole lot of good. So what happens to my efficiency?
Goes out the window.
It goes out the window. But let's say that my gain in this antenna is negative 10 dB. But at the same time, most of the time that I'm operating, I am standing right below the antenna tower. And I have something on the order of, 40 dB of excess gain available to me. Do I care that I have a minus 10 decibel gain, 10 decibel loss? I do not.
I wouldn't think so.
I do not. It doesn't matter to me. Now, if I instead were not there right at the base of the antenna, but instead I was trying to use this radio to talk to a distant repeater way out here where my available clearance on gain was like 1 dB. Well, then this antenna would be the difference between being heard and not being heard. And that's why some people have multiple antennas. If they're going off into the woods or something, not only do you have a bigger antenna that fits directly on the radio, but maybe you have something that you have that's portable and you can unroll and throw up in a tree with a short piece of cable because it's got significantly more gain. And by putting it up in a tree, you probably gain another 4 or 5 dB also. All kinds of fun stuff. Okay, a beam antenna. A beam antenna is an antenna that concentrates signals in one direction. Antenna gain is the increase in signal strength in a specified direction compared to a reference antenna. So it's important to note that there are really 2 different reference antennas. One is a dipole. The gain is known as dBd. The other one is an isotropic radiator. Okay, and to explain what an isotropic radiator is, dBd is dB with reference to a dipole, right? And that has that characteristic donut-shaped pattern around it, right? Okay, dBi is an antenna that is a point in space that has equal signals in every single direction, independent of the direction. Do you think this antenna actually exists? There is no such thing as an isotropic radiator. It does not exist. A dipole has a 2.05 dBi gain. In other words, a dipole, just by virtue of being a real antenna, has 2.05 decibel gain over an isotropic radiator, which isn't real. So when you go to get an antenna, you look at the specifications. Maybe it's listed as 7 dBi gain or 7 dBd gain. These are different. The thing that says dBd is actually more impressive because a dipole is already better than isotropic. So if you were to actually do this measurement, this antenna right here would be a 4.95 dBd. because you have to include that in it. Okay. Which of these antennas offers the greatest gain? A 5/8 wave vertical is okay. An isotropic radiator, if you can build one, it's still terrible. A J-pole is basically like a quarter wave vertical, and a Yagi. I would go for the Yagi. What is the disadvantage, now that we've talked about it, of the short, flexible antenna supplied with most handheld radios? Everyone?
Doesn't work very well.
Low efficiency, exactly. But again, if you're really close to where you are trying to talk to, maybe it doesn't matter. Why should you not bother using a handheld radio inside a car?
Signal won't get out.
Signal won't get out. Now, you can open up the window and stick the antenna out the window. That works okay. But yeah, basically you have the car basically functions like a shield. The advantage of a 5/8 wave antenna over a quarter wave, it has considerably higher gain on the order of 3 to 4 dB compared to a quarter wave antenna. The disadvantage, of course, is that a quarter wave antenna on 2 meters is 19 inches long, and on a 5/8 wave is about 46 inches long. I can pull my car with a quarter wave antenna into the garage. I cannot pull my car with a 5/8 wave antenna into the garage. It always hits stuff. Okay, feed lines and connectors. How about a 5-minute break, everyone? Think about your questions. And by the way, it only gets easier from here.
We'll see.
Oh, yeah. Okay. Everyone formulating those wonderful questions?
Yeah, I got one question. It's kind of off the beaten path.
Oh, there's so many of those. I love it.
Okay. RG58 used to be the standard for all cable for radio CB. What is it now?
Depends what you're talking about. I mean, we're going to cover cable like right now.
Okay.
So it's a loaded question because it's very application specific.
Okay.
And here I will let me pull up that chart. Everybody ready? We're
Ready.
going again. We're going to have some more fun. You know, this is exhausting but fun for me. I like this.
You're doing great. I mean, I used to teach courses for IBM, and I would find at the end of a full day of having to talk to people, I was pretty tired.
Yeah, it's exhausting, but it's very rewarding, I think, because I end up learning a lot of new stuff myself that I'd never thought of. You know what I mean?
Well, they say
of
you don't really.
teaching.
Yeah, they say you don't really know it until you can teach it.
Well, yeah, but even then, I come up as I'm teaching. And this is like the 31st class I've done.
Are you serious?
Yeah.
Well,
Students make you learn.
They do. You know, I mean, I never thought of something that way before. So, you know, there's all kinds of questions that come up. And I think it makes me better at teaching it because it forces me to look at something in a different way, which forces me to teach it in a different way. And maybe that new way is better than what I had. So, you know, I'll be honest, I actually switched up my delivery this time a little bit. I switched up the process slightly. In a way that I thought made better sense than I'd done previously. So I hope it's working out for everybody. I know everyone's mind, a lot of people's minds are probably kind of toasted, but you know, that's what overnight is for. Okay.
no,
So
you're keeping it interesting. So that's really awesome.
well, good. Okay, here we go. Feed lines and connectors. All right, we're doing feed lines and connectors. Okay, so this is really important because feed lines and connectors are how we get power from one place to another. Why is coaxial cable the most common feed line for amateur radio systems? That is because it is easy to use and requires few special installation considerations. You can bury it, you can mount it to a wall, you can hang it from an eave. You can do pretty much anything you want. And because it's a sealed system, much like cable TV cable, the signal stays inside. One thing you have to be careful about is that you waterproof it properly and make sure that it's UV proof if it's going to be exposed to the sun. Because if it's not UV proof, it'll crack and then it's not waterproof anymore. And water in your cable is the easiest way to destroy a cable and have a station that doesn't work. Okay, impedance. Impedance is the opposition to AC current flow. The unit of impedance, again, is the ohm. Most common impedance of coaxial cables used in amateur radio is 50 ohms. Okay, notice it says RG58 and 213 are two common types of cables. 50 ohms is the most common characteristic impedance of cable. Now, we need to cover something a little bit, and that is the fact that this is something called characteristic impedance. Now, what is a characteristic as opposed to a property? It's a little hard, it's a little bit of a tough distinction. So if we think of something that's 50 ohms, right, and that's a resistor, what does a 50 ohm resistor do? It converts what into what?
Electricity to heat.
Electricity to heat, correct. Okay. Now, what we're going to have to do is define this thing called characteristic impedance. Characteristic impedance. Okay. So let's say we have a resistor that's 50 ohms. This is known as our load. Right? So this is typically going to be 50 ohms pure resistive. No guarantees, but that's the ideal. All right. So now we can connect our transmitter, we'll call that our transmitter, directly into it, and it transmits all the power, right? No problem. But more than likely, our transmitter is going to be somewhere else. So here's our RF transmitting device, and it's going to look like this. And somehow it's going to have to transmit energy from this point to this point so that the antenna is our load, which is 50 ohms, is going to get all the power. But we want it to continue looking like 50 ohms. If we just used a piece of wire, that would probably not be 50 ohms. That would actually be something else. So what we end up doing is having this thing called a transmission line. A transmission line can be modeled as something that looks like this, unless I screw it up. Okay, there we go. So a transmission line is basically something that is a device that moves RF energy from place to place while making sure that a load of a given resistance or given resistance or impedance looks the same by the time it gets here. So if I were to take a look at this feed line, every certain chunk of it that I were to look at would be identical to every other single chunk of it. It would have like two inductors and a capacitor in this. I guess you'd call it like the letter pi, the Greek letter pi, because it looks like this. Kind of like the Greek letter pi. And so each chunk of it is identical to the next one. And these are characteristic values. And in a perfect piece of cable, the inductors and capacitors don't have any real loss. They don't burn up any power in a perfectly good cable. They're just there. And the reason that they're just there is because every piece of wire is itself an inductor. It has inductance. And if I were to draw this around it, this shield, right? Between the shield and the center conductor, what do you notice here? What is this area? It's empty space. And what do you call an area with two electric lines and empty space? What is that?
Capacitor.
That's a capacitor. So basically, this transmission line, it has capacitance because it's two different lines, and it has inductance because it's made of metal. Everything that's metal has an inductance. So basically, it doesn't really burn up power, but what it does have is effectively capacitance and inductance. And because of that, you have to actually include those in what the transmission line looks like. And because a transmission line, like a piece of coax, the capacitance and the inductance are proportional to the dimensions, like if you had the same diameter inductor, it's diameter cable in the middle, and you had a bigger shield, that would have a different impedance than the one that's on the left. So these two cables, even though they're both coaxial cable, would have different impedances. This one could be 50 ohms, and this could be 18 ohms. Because the surfaces are further apart. Capacitance would be different. Similarly, I could do a cable where the conductor was really, really fat, and that would change the inductance, and it might also change the capacitance. And now this cable might be 60 ohms. So what's really important to note is that if I were to take a look at two different kinds of cable, that this one is a perfectly scaled up version of this one. And this one is 50 ohms. This will also likely be 50 ohms because everything has been maintained in proportion. And that's why, for instance, you can have, we were talking about like RG58. This is your classic small 50 ohm coax. And then there's RG8, which is basically your classic large 50 ohm coax. And then there's RG8X, which is like a medium. And then you can have RG174, which is tiny, but also 50 ohms. So realistically though, how are these all different if they all have the same impedance? If I hook this up, any of them, between my antenna, between my transmitter and my antenna, and everything's 50 ohms, everything will be fine. What makes one different from another? And here's what makes one different from another. And here's my feed line. And here's my antenna. And this is 50 ohms. And this is 50 ohms. And this is 50 ohms. Okay, everything is perfectly matched. Everything is a 50 ohm impedance in this system. If I put out 100 watts, or let's say I put out 1 watt, and there is no loss in this system, I will get 1 watt going out into the world. So what difference does it make if I use 58 or 174 or 8 or 8X or 1 5/8 hardline? We'll call it Heliax. What difference does it make if I use any of those? And here's where it makes a difference. Can everybody see that?
Yep.
Yeah.
Okay, this is super important. Super, super important. So notice here in the second column over is RG8X. So let us say that we are going to be operating at 144 megahertz and we're using RG8X. This is loss per 100 feet. So let's find the intersection of 144 megahertz and RG58. How many decibels of loss do we have?
5.5.
Okay, so 5.5 is almost 6, right? So we go back to what we learned about decibels. 3 decibels is how much power? You only got to know 2 things. 10 decibels is 10 times. 3
Yeah,
decibels
double, yeah.
is half,
Double.
right? 3 decibels is twice. So if we lose 6 decibels, we lose 3 and then another 3. How much of our power did we lose? We lost half of it with the first 3 dB, and then we lost half of that.
Yeah,
How much are we left with?
0.
No, you're left with a quarter.
because it's half and half again, right?
Yep,
Yeah.
it's half of what's left. So you're left with 25% of your transmitted power, which means you put out 100 watts, 25 watts makes it to the antenna, and how much gets burned up in the cable? 75 watts, right? So let's pick a different frequency. Let's go with the same cable and go down to 20 meters, which is the 14 megahertz band. What's our loss down there?
1.7.
So less than 2 dB. So, you know, we could actually do the calculations, but I think we could safely say that we're not going to lose even half our power. We're probably going to lose, 20%, 30%. So just by changing frequency, we've changed from losing 75% of our power to losing about 20%. Because we picked a different frequency to operate on. So the same cable may be perfect for one application, but not for another. The other thing is, let's say that we have that same cable and we're operating with 1.7 dB of loss. So we lose 20%, but let's say we want to run a kilowatt and we lose 25% of our power. How much power goes into the cable?
250 watts.
250 watts, which is potentially enough to damage and melt the cable. So it has a power handling capacity as well, based on heating and based on the amount of current going through the conductor. So let's instead pick, let's go with LMR 400. Let's go back to 144 megahertz and let's go to the very expensive but very well made LMR 400. What's our loss?
5.23.
On 144 megs.
Oh, the 40. I'm sorry, wrong
Yeah.
column. 2.7.
1.44. So we're basically down at about 15% loss of power. Whereas before, remember, we were at 75% loss. So by just changing from a small cable to a big cable, we reduced our losses from 75% to 15%. And that works on transmit and receive, which basically means we're going to have a much more potent signal. And we're also going to be able to receive things better. So that cable probably costs 10 times as much. But if it's a question of your station working versus not working, maybe your decision comes to that.
So would you know off the top of your head roughly how much, like how many dollars per 100 feet it would be?
For LMR 400? Let's see. LMR times microwave LMR 400. Here we go. Let's not go to Pasternak. Let's go to gigaparts. $75 feet, $130.
Gosh, that's not bad. I mean, you can't buy powering your transmitter that cheaply.
No, you can't. That's exactly true. But let's say you're putting up a repeater and you decided you want to put up a repeater that operates at, where is it? At 440 megahertz. So even LMR 400, it's still 3 dB roughly. So you're still losing half your power. So you say, okay, well, that's still, too much loss. I don't want to do that. And so you go to, for instance, you make the investment to get this stuff. You see 1 inch heliax, 1 1/4 inch heliax. And notice what that costs.
Is that a foot?
That's
or is
per
that a
foot.
meter?
That's per foot.
That's a foot.
That's per foot. But
yeah, that's getting up there.
But let's say that you've got a tower and you can't get your transmitter up on the tower, and you've got available to you a 300-foot tower. So, or let's say a 100-foot tower, right? And you need 100 feet of this stuff. So it's $1,400, but it's the difference between having a station that kind of works and a station that really, really works. So, you know, it's entirely possible you might also be able to pick this stuff up secondhand from a tower that was decommissioned, in which case, you know, as long as it's in good shape, this is obviously a much better solution. It's also really, really hard to work with, by the way. I've seen it before.
Steve, can I go back to the chart you were showing before?
Yeah.
It was based on a 100-foot cable. But if
let me
you
pick up the right one. There we go.
Okay.
Yes.
What if you only need 20 feet?
Then you can
on
cut
your
that down
transmission
you
line?
can cut it down by a factor of 5. It's linear.
Yeah, it does cut down.
Yep.
You know,
Which is another interesting one. Somebody else recently in our club, we have a weekly tech net on the air. And the question was, I've got a dual band radio, 2 meters and 70 centimeters, and I've got a 100-foot piece of cable of which I only need 40 feet. I don't really want to cut the cable. Should I cut the cable? What do you think the answer was?
should be able to.
Well, no, it's a question
yeah.
of wanting to.
Oh, want to.
He didn't want to cut the cable. What did we tell him to do?
Got it.
Cut it.
That is.
Good.
Yeah.
Why would you have another 60 feet of cable that's just there attenuating your signal?
Yeah.
It's the only thing it's doing is attenuating your signal. And you can always get connectors and put it back together.
So you just cut it and put a connector on it then?
If you want to have, you know, longer cable again, you just put connectors on it, and then you have a 40-foot piece, and then you've got an extra 60-foot piece. You typically will cut your cable to the length that you need.
Okay,
Actually,
when you cut it, what do you put on the bare end?
Either a PL259 or whatever you need. Which is actually one of the things we're covering right now, PL259. There you go. Learn how to solder if you don't already. And PL259 is good for HF and some VHF. And here's your end connector. If you're doing UHF or doing microwave, this is what you would use. And that's known as an end connector. And sometimes you don't have to solder them. Some of them are mil-spec crimp as well.
Can you use N for HF?
You can, but you typically won't find any HF radios that have end connectors, you know, mating end connectors built in, because they're totally unnecessary. I mean, it's
right. So then you'd need an adapter, and then you have the impedance of the adapter.
Right. Okay. Let's see, where were we? Right there. Okay. Now everybody should be able to answer this. What is the most common impedance of coaxial cables? 50 ohms. Okay. What happens if the frequency of a signal in coaxial cable increases? What happens to the loss?
Increases too.
Increases too. What's the electrical difference between RG58 and RG213?
Yeah, 213 is less lossy.
213 has much less loss because it's just a fatter, bigger cable. It can handle much more power. Which of the following types of feed line has the lowest loss at VHF and UHF? And that would be air insulated hardline. That's the $14 a foot stuff. Which of the following is a source of loss in coaxial feed line? Water, SWR, and multiple connectors. Every time you add a connector, you increase it, you add an impedance bump, which causes loss. High SWR, if you have a bad match for whatever reason, that increases loss. Water intrusion, that's the killer of cable. Which of the following causes failure of coaxial cable? And that would be water. Water, water, water. If the question is what causes cables to fail, it's water. And why should the outer jacket of coaxial cable be resistant to ultraviolet? Because if the cable cracks, what happens?
Water.
Water. There it is again. Keeps coming up. What's the disadvantage to air core coaxial cable? most coaxial cable is filled with foam or a solid polyethylene. Air core is filled with air,
Air.
right? And what happens
Yeah.
if you don't seal off your cable properly? What does that air become filled with?
Water.
Water. There it is again. So you have to really, really be careful. Like a lot of stations, like commercial TV and radio stations, they actually have pressurized nitrogen that basically blows dry air into their cables. PL259s are the most common type of connectors. What is true of PL259s? They're great for HF and VHF. They're really easy to use. They're really cheap. They're everywhere. And they are easy to put on. They're good for HF and VHF. But they, interestingly, these also have another name. The PL259, and maybe this is your way of remembering it, the PL259 is also known as a UHF connector. But they're terrible for use at UHF. So, which of the following RF connector types is most suitable for frequencies above 400 megahertz? Hey, while we're talking about this, does everybody remember the limits for HF in megahertz?
3 to 30,
3 to 30. How about VHF?
30 to 300.
30 to 300
And UHF?
to 3,000.
300 to 3,000, which is also known as 3 gigahertz. Okay. So the 400 megahertz limit would fall in UHF. Don't say UHF, right? Because the answer is type N. N connector is much better for use at really, really high frequencies, all the way up to microwaves. Okay, so we haven't really covered standing wave ratio, but we're about to. What can cause erratic changes in standing wave ratio? Well, if you have a loose connector, that can definitely do it. Basically, you have an impedance mismatch. Impedance mismatches lead to unstable SWRs, or at least high SWRs. If it's loose and making and breaking and making and breaking, you'll definitely notice. Okay, standing wave ratio. Standing wave ratio formula. Okay, and this is why we're only going to mention this in passing. Everybody see that?
Yep.
Okay, that is the ratio. That is the formula for standing wave ratio.
Yeah, let's do pass on that.
Yeah. That is the formula for standing wave ratio. Now, you can actually measure using a directional wattmeter forward and reflected power and calculate the standing wave ratio from it. Easier thing to do is get a meter that has a forward directional wattmeter and a reverse directional wattmeter and look and see where the two needles cross. That was something like, when I go back to the MFJ 949, there's that cross needle again. Notice the cross needle, it's got a forward and a reflected meter. Nice thing about that is that all those lines, the vertical lines, those are indications of SWR. They're basically taking those two numbers and doing the calculation graphically. Okay, standing wave ratio is, in general, a measure of how well a load is matched to a transmission line. A perfect impedance match is 1-to-1. Let me put this up on the screen. There we go. A perfect impedance match is a 1-to-1 match. That means you have all your power that's going in is going out the other end. An SWR of 4-to-1. SWR is always going to be a positive number compared to some value 1. So 1-to-1 is perfect. 4-to-1 is a serious impedance mismatch. And that's when you start getting into your transmitter protecting itself by reducing your power output so that it doesn't fry itself. The benefit of low SWR is reduced signal loss. Now, even with an antenna tuner, that's true. The bigger the mismatch, the higher the SWR. The higher the SWR, the more power is lost in the feed line. And what happens to power that's not transmitted? Where does it come out? It comes out
Warm
as heat.
stuff up.
Warm stuff up. Why do most solid-state transmitters reduce output power beyond a certain SWR? That's to protect the output amplifier transistors. Which of the following should be considered when selecting an accessory SWR meter? So an SWR meter, again, is a combination forward and reflected power meter. They operate at a certain range of frequencies and power levels. I have a meter that's good up to 10 watts. I have another one that's good up to 2000 watts. I have one that's good at 144 megahertz and 440 megahertz, but doesn't work on HF. I also have one that's good everything up to 144 megahertz. So not every meter will work perfectly at all frequencies and power levels. You can use a directional watt meter to measure SWR, forward and reflected power, and do the calculations. Where should an RF power meter be installed? You want it to be in the feed line between the transmitter and the antenna, ideally as close to the transmitter as possible, so you really get an idea of what's happening. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? That would be an antenna analyzer. Has anyone ever seen an antenna analyzer? I'm guessing maybe not. Okay, there's a couple of different things that are available today. Essentially, what an antenna analyzer does, if I can share the right thing. Here we go. An
I think
antenna
I've seen one
analyzer.
of these.
Hmm?
Oh, I think I've seen one of these.
Okay. An antenna analyzer is basically a device that, okay, legally speaking, where are hams allowed to transmit a signal? Where do you think? What bands?
Depends on your license class.
Well, right, but in a ham band, right? We're not allowed to transmit signals outside of a ham band. No ham is independent, right? Now, let us say that you have an antenna analyzer, such as a Rig Expert, or a Nano VNA will work as one, or I have one of these. You basically have frequency ranges, and it has an SWR and a resistance meter. There's lots of different choices out there. You could build your own. You can do a lot of different things. So what is the point of having an antenna analyzer? So let's say that you are looking at a range of, let's say, 12 to 15 megahertz. There is a ham band that goes from 14 to 14.35. So 14.0 to 14.35. Well, okay, let's say that somewhere in this range we do some tests and we find that our antenna has an SWR that looks like this. All right, we managed to do a test here, and we find that here's 1 to 1 and here's infinity to 1. We find that it looks like this. Here's our test. We tested it in the ham band. Does that tell us anything other than the antenna doesn't work? Is that useful at all?
I don't see it.
Oh, can you guys see the? Can you guys?
No,
see
no, I
the
don't.
white-
See, I don't see its usefulness other than telling you
Oh
it
yeah,
doesn't work.
yeah, exactly. We don't know that it's useful at all. We don't, other than the fact that it doesn't work. However, the reason that we can't see what it's really doing is because we can only look at this tiny little frequency band because we can't transmit anywhere else. But let us say that we have a very, very low power device that we can sweep on all these different frequencies, including those which are not part of the ham band. And we can transmit, let's say, 1 milliwatt legally because it's a Part 15 device. It's a non-licensed transmitting device. And we have a receiver built into it that's sensitive enough that it can actually give us a chart that looks like this. What can we say about our antenna?
We should use it at a different frequency.
That's right. Or if we're just building it and it's resonant at 13.0, it's obviously too long. We made it too long. But we would never know that if we could only look at this range. So the power of an antenna analyzer is that it can basically legally sweep a bunch of frequencies that we can't legally transmit on because it's operating at such low power. For those people who are building antennas or testing cables and things like that, it's an invaluable tool. Okay. What is the major function of an antenna tuner or antenna coupler? It matches the antenna system impedance to the transceiver's output impedance, and typically that's going to be 50 ohms. So what is the purpose of a dummy load? A dummy load is a phony baloney 50 ohm load, a purely resistive 50 ohm load that's made to simulate a perfect antenna. So you can very often transmit a kilowatt into a dummy load for 30 seconds and have it just turn your energy into heat, heats up the room a little bit, and then that's it. It doesn't transmit any signal anywhere into the real world. A dummy load consists of a non-inductive resistor mounted on a heatsink. So why is it important that it's a non-inductive resistor? Everyone? Let's say that our dummy load.
So you don't have an impedance mismatch.
Yeah, let's say that we had a wire wound resistor that looked like that, and it was 50 ohms. Well, it's 50 ohms DC. What does this little part do? Remember that impedance thing? We have our resistance, and then we have plus J2 pi FL. That basically takes our impedance and puts it here, and then it continually, as we increase frequency, it moves it higher up this line. And our impedance is whatever this magnitude is. So at different frequencies, we will have different impedances, which is not much good for a test device, right? You want it to be 50 ohms purely resistive. So if you don't, when they say a non-inductive wire wound resistor, that can be just a block of ceramic, or it can be wire that is built like this. No full turns of wire. If it doesn't make any loops, it doesn't make much of a magnetic field. It doesn't have much inductance. Non-inductive wire wound resistor. Now, I would like to also point out that this was, okay, here we go. This is actually really significant, I think. So here's our ATU, our antenna tuner, and here's our transmitter, there's our antenna tuner, and here's this. Okay, so here's our antenna tuner in here. And we have an antenna that is, let's say, 10 ohms, and a cable that's 50 ohms. This mismatch is a 5-to-1 impedance mismatch. So by the time it gets down to here, we adjust our antenna tuner so that it looks like 50 ohms. Including all the cable and everything. Let's say we tune it up. What is our impedance mismatch up here? This is a very important distinction to make.
Still 5-to-1.
It's still 5-to-1. That's right. We still have a terrible impedance mismatch up there. Ideally, that's what we're going to fix, but sometimes you just can't. So what happens at this point is that your power goes out. The transmitter never sees it again because it gets up to this point and some of it goes out and some of it comes back. When it gets here, none of it goes back to the transmitter. It just gets bounced back up to the antenna, and some of it goes out and some of it comes back, and then it gets back here and it gets turned around and some of it goes up and gets transmitted out, And some of it comes back. And
So it just goes in a vicious circle.
Yep. Until what ends up happening?
Well, it all gets attenuated down to zero through losses.
And what will cause the signal to basically eventually disappear?
It's all been translated into heat.
Or, if 20% gets out each time and some of it gets lost, then it's the sum of all these arrows that are going out. Right? So basically you're going to have the sum of all those arrows going out and the sum of all the losses in this cable. Your transmitter's happy, but the lossier your cable, the more impact high SWR has, because the signal ends up going up and down and up and down and up and down the cable multiple times.
But your transmitter will think it's
gone forever.
But your transmitter will see that you've got an SWR of 1 to 1.
Correct. Magic box. Except that it allows your transmitter to function, but it doesn't make the system work any better. It makes it work a little better, maybe. But so there's a couple things at play. The higher the SWR that you have, the worse the match you have, the more trips up and down the cable that signal will take. The lossier the cable, the more energy you lose every time it goes up and down the cable. So basically, high SWR exacerbates bad cable and vice versa.
So your best bet is to buy a 50 ohm cable then.
Well, that might actually not be the problem, though. What if the antenna is only 10 ohms at a certain frequency?
Well, I don't know about that.
Well, right. And the problem is, let's say that I have an antenna that looks like this, and I am using it. It's designed to be operated on 14 megahertz or something, right? And you say, you know what? I just need to transmit. I'm going to operate on 18 megahertz. And if I draw the signal, maybe it looks like this, right? Where I'm not feeding it at a particularly advantageous spot anymore. And it's not 50 ohms because I'm not feeding it at the right, at the frequency it was designed for.
Mm-hmm.
It's something totally different. And I've never really planned to use it at that frequency, but I'm doing it anyway because I want to. Well, I don't know what's going to happen. So basically, I do have a mismatch up there. So what I end up doing is what I have on my station is I have a 2 single dipoles and I have ladder line, which has a loss of like 0.5 dB per 100 feet. As opposed to, let's say, 3 dB per 100 feet. Which basically means that every time, even if I have a really bad mismatch up here, every time it makes another trip up and down the cable, my losses are really minimal. So most of the signal is eventually going to go out. So, again, high SWR is exacerbated by high loss cable and vice versa.
Yeah.
If you can eliminate either one of those, that helps.
Question?
Yeah.
Each time you're changing frequency, how much are you playing with that antenna tuner?
I'm retuning it every time. Now, if you have an automatic tuner, like the one inside a radio, you hit a button and it goes and it's done. Whereas if I'm going to a different band, I'm switching modes, keying up, and adjusting the knobs.
One question I've got, if the signal is going up and down and up and down, what does the individual at the receiving end hear?
Nothing appreciable. It happens really, really fast.
Okay, so there is no distortion in the signal?
No.
Okay, good.
However, let's say that you're a TV station and you're transmitting a high-speed TV signal. That's bad. If you have signals going up and down your feed line, that would end up in the past causing ghosting. because the TV signals do happen and they have a high enough bandwidth, you know, they are affected by that continual echoing. But audio, no one notices. But good question though.
So is this, I don't forget if this is covered later, but I was wondering about balanced versus unbalanced in feed lines.
Okay, so like ladder line is a balanced line. Coaxial cable is by nature unbalanced because you have a circular symmetry, but you don't have the same overall currents everywhere in the line. So by switching from an unbalanced line to a balanced line, you use something called a bow-un transformer. You can also do an un-un, which basically is a transformer that forces currents to be equal on both sides of the antenna. Because you might not have equal currents on both sides, and because your pattern is generated by the currents on your antenna, your radiation pattern, if they're uneven and you really care whether or not you have a pure looking antenna pattern, then it might be worth it to put in something that actually forces the two sides to have the same amount of current. You get a nicer looking antenna pattern. All right, other questions before we go? Okay. Amateur radio signals. Okay. Modulation. If we've ever heard the term modem, modem is a modulator demodulator. The act of modulation is what we do to basically take a signal that is a carrier signal and put information on it. That is the act of modulating something. What type of modulation is commonly used for VHF and UHF repeaters? That would be either FM, which is frequency modulation, or phase modulation. Either one works fine. The same thing for VHF packet. Packet is basically data over FM. We use FM, which is frequency modulation, or phase modulation. Amplitude modulation, another type of modulation. Basically, we just change the bigness of a signal. We change the amplitude of the signal to make it bigger or smaller. We change its amplitude. And you know, I think it's time to draw. I think we're going to draw. All right. Because a picture's worth 1,000 words. All right. We're going to be looking over time. So this is time, and this is amplitude. So if I have a sine wave, this is a carrier wave, high frequency, where the amplitude is basically unchanged over time. This is just a pure frequency. It has no information on it. However, if I were to take this signal and instead do this with it, what do we know about that signal now?
It's carrying information.
Right. Well, it's getting bigger and smaller over time. Right? The fact that it's getting bigger and smaller means that, like you said, it's carrying some information. The information is that it's getting bigger and smaller. That means something, right? We've told it to mean something. So if we could, for instance, take this away, that would be an envelope. If we could do this and take away the top and bottom, that would be a modulated carrier signal. Now, one thing that's interesting about this is that this is not immediately obvious, but if I were to take a signal that looked like this, that had the same amplitude forever, let's say I was better at drawing these things, and it had the same amplitude forever. If I were to look at a frequency spectrum representation, and I had a center frequency that looked like this, if I had a pure sine wave of one particular frequency, it would look like a perfect little spike of some amplitude at some carrier frequency, FC. What I can do with this signal by changing what it looks like amplitude wise is I can make it do this. I can make this single spike, which represents a single frequency, just by changing the amplitude. I can make this signal spread out. And what will happen is that this center frequency will become smaller because now some of that energy that we had is now moved into these things called sidebands. And because this is the positive side, this is the negative side, this is the upper sideband, and this is the lower sideband. Now, if I have drawn this correctly, what you'll see is that the upper sideband is a mirror image of the lower sideband. I can now take this signal, which is called AM, or amplitude modulation, and if I'm creative about it, I can do this, and I can selectively filter out before amplifying the lower sideband. And I can also say that this is just a reference point. I can kick that out of there. And now what I have is just simply upper sideband. This is a form of something called single sideband. What we have done by doing this is we've eliminated that other half of the signal which wasted power and made the signal take up 6 kilohertz of space. By killing the carrier, that also increased our efficiency because there's no information on the carrier itself. It's just a reference marker. So by doing that, we've saved power, which increases efficiency, and we've taken this signal, which was 6 kilohertz wide, and made it about 3 kilohertz wide, which means that we can have more of them. We can have more of them filling the same space. And we can put all of our power into that smaller space, which means that our power spectral density, which determines how loud the signal is on the other end, goes up. So single sideband is much more efficient than AM for that reason. And that's why everybody uses it now. Now, there's another thing we can do, which is we can instead of modifying the amplitude, we can do this. We can keep a basically constant amplitude and modify the frequency based on some modulating signal, which is either voice or data or something like that. This is known as FM, where we modulate the frequency. We don't change the amplitude, we just change the frequency. And what this does is it generates a signal that basically looks something like this. Where now we have on the frequency spectrum from minus to plus, we basically fill in a space. And so this information, the amplitude might change a little bit, but by the time this gets to the other end, what we're really looking at is the fact that we have these frequency components which are changing from the center frequency, and these might be a little bigger, a little smaller, and so maybe now the wave looks like this. And again, this is in frequency, not in time. So the amount of bandwidth that this fills up is between 10 and 15 kilohertz. So it's a considerably wider spectrum. It takes up a lot more room, which is why we typically don't use this on the high frequency bands, because we don't have that much space available to do it. What we get from this, however, is we get a little bit of increased fidelity. And on top of that, we get immunity to noise. And the reason we get immunity to noise is if we look at our time representation of this as opposed to our frequency representation, we have something that looks like this. So what we do is we basically cap the plus and minus when we're looking at it, which means that it doesn't really matter what the amplitude is because we're transmitting it all. It's all being received, and all we're really looking for is the frequencies that are contained inside. What happens at this point is that we can use a lesser transmitter. We don't need the same kind of linearity that we would need for sideband. So we can use a less efficient, more efficient, less effective transmitter to transmit it. And then when it gets to the frequency side, if we're looking at something like this, let's say our signal looks like this. Well, okay, let's say we have a static crash. What static does is it increases everything by a certain amount. Well, if it increases everything by a certain amount, it increases everything by the same amount in the frequencies, which basically means we're still able to hear our signal. And this is largely why FM radio is immune to noise, immune to static crashes, which is why if you're in a thunderstorm and you're listening to the AM radio, you'll hear crack, crackle, crackle. On FM radio, you won't hear anything unless it's like right on top of you, because it essentially has built-in immunity to it. Okay. So now, that being said, which of the following is a form of amplitude modulation? That would be single sideband. Long distance weak signal contacts. FM is not very efficient as far as weak signal goes. It tends to, FM suffers from something called the capture effect, and it also tends to require more power to transmit it. So we typically use single sideband for weak signals. A single sideband can be upper or lower sideband. By convention, anything above 10 megahertz, which is the 30-meter band, uses upper sideband. That is by convention. So 10 megahertz, which is 30 meters, is the dividing line. Anything higher in frequency than 10 megahertz is upper sideband. A characteristic of single sideband compared to FM, single sideband signals are much narrower. A typical single sideband signal is 3 kilohertz. A VHF FM repeater signal is between 10 and 15 kilohertz. And here's the thing called the capture effect. So if you have 2 FM signals being transmitted into a repeater at the same time, what will happen is the winning one completely obliterates the losing one. FM receivers are not good at being able to discern between 2 different signals. So this is one of the reasons that that aircraft, if anyone ever listens to aircraft flying overhead, they still use AM. And this is one of the reasons. You might have 2 aircraft on the same frequency, and if they were using FM, the weaker one would never get through. No one would ever hear it. So that's why they still use AM. So this is known as the capture effect, where only one signal can be received at a time. And very often, if they're of equal amplitude, both of them lose. Nobody wins. AM fast scan TV actually takes up about 6 megahertz, not kilohertz, megahertz. So you basically have the color burst frequency, you have all your colors, and you have FM audio built into it. We actually have frequencies that are allocated for use for amateur television, fast scan TV, 6 megahertz NTSC fast scan TV. As you would probably guess, given the fact that they take up 6 megahertz of bandwidth, if we take a look at this, you would probably agree that most of these, because like let's say the 2-meter band is only 4 megahertz wide to begin with. The 70 centimeter band goes from 420 to 450. We have one high-speed television channel there. On the 33 megahertz band, 33 centimeter band, we can do high-speed TV. On the 23 centimeter band, we can do high-speed TV. Interestingly, does anybody fly drones? So are you familiar with first-person view?
Yeah.
You know that FPV requires, depending on the channel that you're on, actually requires a ham license.
Does it really?
It does. Because the 5.8 gigahertz band is a shared band between unlicensed and ham radio licensed services. And a lot of those channels of the equipment coming in from overseas actually falls on amateur frequencies. So in order to do FPV video, you actually need a ham license if you're operating on certain channels from certain manufacturers. Okay, let's see. Back to this. Okay, CW. Well, let's just make sure NTSC is National Telecommunications. I can't remember what it stands for, but basically it's analog fast scan TV. NTSC is fast scan television. That was your old analog TV stations. CW is continuous wave. Basically, it's known as on-off keying. Morse code. By turning a continuous carrier on and off, that's our modulation technique. We use it to encode Morse code. It also has a very narrow bandwidth of about 150 hertz, which is why, if you think about it, we're going to start looking at something called power spectral density a little. So we're going to take our bucket of water. This is our power available, and we're going to take a signal, which is our single sideband signal, and then we're going to take our FM signal, okay, we're going to take our FM signal, and then we're going to take our Morse code signal, and we're going to fill these up so that they have the same total volume. So here's our Morse code signal. Here's our single sideband. And here's our FM. So these actually have about the same overall area, right? The same. Let's imagine we had a bucket of water to fill each of these. The question is, how high would each one get? Okay, so notice that here's our FM signal down here, and it only gets this high above the ground. Our single sideband signal makes it to about here. Our CW signal, Morse code, and this is actually true of a lot of digital modes as well, makes it all the way up above. So if it's a case of these signals are all transmitted at the same time, they all go through the same channel, they all suffer the same losses by going through space, and anything above this line will be receivable at the other end. Who's going to win?
Yeah, it's going to be the CW.
It's going to be the Morse code, which is why people still use Morse code, because it's a very efficient way. Like if this represents 100 watts, and this represents 100 watts, and this represents 100 watts, my 100 watts in Morse code is going to be a lot more effective in making sure that the signal gets to the other end. Now, there are other signals that we do. There's another one called PSK, which has a bandwidth of 31 hertz. That's even more efficient. There's another one called FT8, which in addition to being very efficient bandwidth-wise, it's about 65 hertz wide, uses some serious, really serious error correction algorithms. And so that would be FT8, and that's an incredibly useful. It's actually used for very, very, very weak signals. Like you can literally have half of the transmission disappear and still be able to talk. Now, as you would expect, the data rates are very, very slow. But if your goal is to just get a message through, if it takes 30 seconds, who cares, right? If it makes it through versus not making it through, then it's a winner. Okay, an electronic.
Just a quick question about FT8. Is that what people use for like contesting? Just because
There are FT8 contests, but FT8 is it's really, really slow, and it can be used for contesting. Actually, there's in 11 minutes, if everybody sticks around, which I hope they do, in 11 minutes, there's a worldwide Morse code contest that's starting up. And I would like to take that opportunity to, because I'm going to operate like crazy. I'll flip over to a web SDR, and you can see just how many signals are packed into a band. I think that would be very interesting to see. An electronic keyer is a device that assists in manual sending of Morse code by doing dits on one side and DAs on the other. Okay, digital modes. We talked about this very slightly with FT8, packet, PSK31. Which of the following is a digital communications mode? Packet radio is basically your old AX.25 protocol that we use on the internet still. IEEE 802.11, that's also known as Wi-Fi. And FT8, that is that's the mode that we use that's got a ton of error correction built into it. Those are all digital modes. Digital is basically the transmission of ones and zeros over the radio. We use it a lot. I mean, we're doing it right now. What we're doing is all ones and zeros, everybody. Even though I sound analog, I'm not. Which of the following is included in a packet radio transmission? There's a checksum. So let's say I'm sending a message across, and the sum of all the characters that I'm sending is 26. And if you received a 25, that means that there was a mistake somewhere. That's a checksum. A header that contains the call sign of the station to which it's being sent, and automatic repeat request in case there's an error. My checksum was wrong. You better send it again. So it automatically resends. ARQ is an automatic error correction system where the receiving station picks up an error and says, I need it again, automatically. It doesn't have to have manual intervention. APRS. So this is APRS. And I don't know if anybody can see that yet. I'm going to have to share differently. Okay, this is APRS, which is the Automated Packet Reporting System. This is just looking at Western Oregon. These are all the stations that hams have that are on APRS. Notice we have weather stations, we have cars, we have some people that are hiking. Basically, if you're carrying a radio and it's transmitting on packet on 144.39 megahertz, there's somebody's car. It'll indicate how fast he's going, how high he is, etc., etc. All this information is used for real-time processing of data with geographic information systems. You can use it for tracking balloons, use it for tracking runners on a race, bicycles, etc., etc. Pretty cool combination of technologies. Okay, that's APRS. The kind of data that can be transmitted by APRS, you have GPS, you have text messages, weather data. All right, next is PSK, which is phase shift keying, similarly to the way we could do frequency shift keying. So this would be frequency shift keying, as I share the whiteboard. Okay, so this would be frequency shift keying. If I have a signal here, and this is at frequency A, and another one at frequency B, depending on what's happening, I could shift my signal over to frequency B. I could also, if this was part of the code, shift over to C, and then back to A, and then over to B, and then back to A. So that would be known as frequency shift keying. If I were to look at this on a frequency spectrum, or sorry, on a time spectrum, it would look something like this. So here's one frequency, and then whoop, here's another one, and here's another one. They're very obviously different frequencies. So very often these are actually not, quite as abrupt as I'm showing there, but that's essentially what it would look like. Phase shift keying uses a single frequency, and by changing the phase of the signal, whoops, we got a call for a discontinuity. I'm going to do a 180-degree phase shift. So instead of going up, I'm going to go down. And whoops, we got to the top. I'm going to change my phase. This abrupt change, this indicates some kind of signal being sent. So that's known as phase shift keying, or PSK. Nice thing about it, it usually takes a very, very small bandwidth. Okay. Digital mobile radio, DMR, is digital signals. We actually do a lot of voice over internet protocol on the radio. So essentially, we have digital voice using something called DMR. In one single repeater channel, which is 12.5 kilohertz wide, we can actually time slice them so that one group of times receives channel A and the next one receives channel B, A, B, A, B, A, B. And each receiver is synchronized up so that they never hear the other channel. So basically, by programming their receiver to pick up just one channel, we can share a channel twice. WSJTX, that's basically the software suite that runs FT8. We can use it for Earth, Moon, Earth. We can use it for weak signal propagation beacons, like that graph that I showed you guys this morning, or the map of everybody receiving station signals from everywhere else in the world. Those are all done using WSJTX. And we can do meteor scatter. It has something like 20 different digital modes built into it. FT8 is a digital mode capable of low signal to noise operation. And mesh. Okay, so we also have something called ARDEN, which is the Amateur Radio Emergency Digital Network, that uses mesh networking. Mesh networking is basically the use of Wi-Fi equipment with modified firmware to put together a self-healing, basically a self-healing, how can I put this exactly? It's a self-healing network where a signal that's supposed to go from one point to another will basically propagate through the system and find the best path to get from one point to another. So even if a node goes down, it will automatically be able to reroute itself. The system will basically be able to reroute itself so that the message gets to where it's supposed to go. And that's done using just modified Wi-Fi routers.
So that's mostly microwave stuff then, right?
Actually, a lot of it is on Arden. Yeah, it's usually 2.4 gigahertz. So like, it's a modestly sized dish, like, a 2-foot dish up on a mountaintop. Electrical safety. Okay, we're into amateur station safety. What health hazard is presented by electrical current flowing through the body? It can heat up cells, destroy cells, cause muscle contractions because we're really just electrical. In the United States, the black wire is the hot wire. That may not be true in Europe. That is true here. How do you guard against electrical shock? If you don't have 3-wire cords, because you don't have 3-wire plugs, I'm really sorry. That's part of code now, having 3-wire cords. All AC powered station equipment goes to a common safety ground and install mechanical interlocks in high voltage circuits. Every so often, in order to generate, let's say 2000 watts of RF, if you have a tube amplifier, you have a tube that operates at 3500 volts DC. Typically when you open the lid to your amplifier, there'll be an interlock switch that kills the power. Some people decide that they want to stick their hand in while it's powered up, and some of them end up dead, even now. So don't do that.
Question.
Yeah.
What do those mechanical interlock switches look like?
It's
so we would know what to...
Well, I mean, you'll know. I mean, it's like a micro switch. Sometimes there are 2. If it's me, I'm putting 2 of them in there with some kind of fail-safe for the fail-safe.
Well, a quick question I had, if you go back a little bit.
Yeah.
I just want to make sure I'm understanding what's being asked here about the common ground. Is that like the copper pipe that you strap all the chassis to?
Yes. Yes. Now, there's a distinction that I want to bring up, which is between ground and ground. All right. Ground is by reference 0 volts. So here's our 0 volts reference. So if we look at 60 hertz, this has a wavelength of 5 million meters, right? That's a pretty long wavelength. That's like between the US and that's like between Oregon and Maine, right? So that's one wave at 60 hertz. But now let's take a look at, let's say 10 megahertz. That wavelength is 30 meters long. That's about 120 feet. Now let's take a look at 30 megahertz. That's 10 meters long. That's about 33 feet. What if my station is right here and I have going down to the pipe a 65-foot piece of wire? Is that ground anymore? It's a safety ground. Is it an RF ground? No. The reason being that if my wavelength is 33 feet long, I can actually say this is going to be at 0 and here's my current, and my current exists on my wire. By the time I get up to my station, I have no idea what the voltage is going to be. I can still get an RF shock from that. It's not going to kill you, but it'll make you really uncomfortable. And it might make your computer reboot and do things like that. So there's a difference between RF ground and safety ground. That's a very distinct difference. Okay, the purpose of a fuse in a circuit is to remove power in case of overload. Where should a fuse or circuit breaker be installed? In series with the hot conductor only. You want that to blow. Why should you never use a 20 amp fuse instead of a 5? Because more than likely the person who built it knew what they were doing and they put it in there for a reason, and if something isn't working right, it's because something else isn't working right. Excessive current could cause a fire. What hazard exists in a power supply after turning it off? Capacitors hold charge. They store charge even after the power's off, unless they have a bleeder resistor in them. This was also true of people who used to open up old television sets. Like an old tube TV set could have 20,000 volts on the picture tube for years after it was turned off. That could cause a really nasty shock, 20,000 volts. 12 volt storage battery, if you short the terminals, it can blow up. It generates hydrogen gas plus oxygen plus spark equals explosion with sulfuric acid flying everywhere. This can also be caused by charging or discharging a battery too quickly. You can cause heating, you can cause hydrogen gas to be evolved, and that can go kablooey. And this is the last thing we're going to do today. Yes, it is, I think. Okay. Everybody still good to hang around for a minute? Okay.
Yeah.
I've got to go make some phone calls. I'll thank you very much and be on my way.
Okay. So we're
Thank
just
you,
doing
Steve.
safety. All right. Here we go. Antenna and tower safety. Look for power lines. Don't put anything up that's going to hit power lines. If it falls, it has to be at least 10 feet away from the power line. Don't ever use a utility pole unless it's your utility pole and you have some say over it, because it's not yours, and because that power line that's up there could be at 12,000 volts and could really ruin your day. You should also make the antenna, put the antenna in a position, whatever it is, that nobody can touch it, because it can cause an RF burn. Radiation frequency burn, or radio frequency burn, can actually put a nice little hole in your skin. It hurts a lot. What's required when climbing a tower? Have a hard hat, get a harness, tie off to the tower, and make sure that you really know what you're doing. Every so often, and when I say every so often, it's a few times a year, some ham dies climbing a tower. Because sometimes they choose to do it themselves. What happens if you get stung by a bee when you're up on a tower, or have a heart attack? And if there's nobody else to help you, you're going to die up there. So never go up on a tower all by yourself. Always have somebody on the ground watching. If you're using a crank-up tower, you have to put locking pins in it. Alternately, you can retract it and climb it in a safe position. A turnbuckle to tension a guy line. A turnbuckle is basically something that pulls a cable in and puts tension on it. Wind tends to vibrate them, which tends to loosen them. So we have a safety wire that goes through a turnbuckle to keep that from happening. Grounding requirements: follow local electrical codes wherever you live. The proper method for grounding a tower: one ground rod 8 feet long for each tower leg bonded to the tower and to each other. Another thing, don't ever use long wires or bent wires to ground a tower. Lightning likes to follow curves. Lightning also likes to go the shortest path possible. You want short and direct connections and no sharp bends. And finally, what should be done to all external ground rods or earth connections? You want to bond them together with a heavy wire or conductive strap that isn't going to melt when it gets hit by lightning. So that means don't solder anything, because if you solder it, the solder will melt and then it's not a connection anymore. And finally, a lightning arrestor. If you're going to put it in a coax feed line, you want everything, all your feed lines to be grounded together, and you want them on a single plate, and then the single plate gets grounded. And you know what? We'll just do that next part tomorrow morning. We're in good shape. Questions?
Yeah, just one quickly. I was looking at the outside of my house where the previous owners had like a cable, had like a satellite TV dish mounted. And I'm trying to think, where am I going to put an antenna? And I noticed that the satellite TV mast was not grounded in any way. And that horrified me a little bit.
Well, I mean, what's it attached to?
A coax that runs inside the house.
Okay, but what's the mast actually attached to? Is it
The
attached to like
chimney?
Yeah, I mean, it's probably
all
a
right?
good idea. It's probably a good idea
Right.
to ground it.
Okay, so what if I put up my ham antenna? If I take the dish down and put my ham antenna there, should I again be running grounding cable? And who do I get to do that? Is that just an electrician who can do that? Or
Electricians can do that. I mean, if you know other hams in the area, they could conceivably come in, and basically what you're going to be doing is pounding a ground rod into the ground and running a grounding cable from the mast down to it. Conceivably, you're also taking a look at depending on how big the antenna is, essentially in your cable, you've got something that looks like this, and the center conductor will come to a point inside, and there'll be a tap on the outside, which is like a bolt. And what'll happen typically, these are sold by names like Transitrap and things like that. What happens is you basically have, between the center conductor and the outside, you have a gas-filled tube. So the shield is basically goes like this, and then you have a gas-filled tube that connects the two. And normally the gas is inert, and it can handle 1,000 volts or something. And if you get a direct lightning strike, what'll happen is you'll get 20,000 volts coming down your line, which when it hits here will ionize the gas, and hopefully, if everything works right, shunt the lightning to the outside. And since you've basically taken all of these lightning arresters, and if you've done it right, hopefully, you take all of them and you mount them to this plate, and this plate is then tied to ground. Hopefully what will happen is that lightning will be shunted to ground through the lightning arrestor and through the plate. And
so
it won't make it into the station.
Right. Nonetheless, I guess during an electrical storm, I should probably disconnect my transmitter from the coax.
Yes, disconnect everything. That is the safest thing to do. If you know it's coming, disconnect everything. I've actually gone so far as to take my coax, and depending on if I knew where it was and if I knew it was coming, I'd toss it out the window.
Would you really?
Yeah. If I could go retrieve it easily and I didn't worry about it getting wet. I've on field day, I've done that. So, all right. Any other comments? Questions? I hope it's not too much. I know it's a lot of material.